I request Selvamurthy sir. I request Professor Selvamurthy sir to please come on the dais. I request Professor B.C. Das sir to please join the dais. I invite Professor Marina Krutz to kindly be on the dais. Honorable VC ma'am, Professor Dr. Balwinder Shukla ma'am will be joining us shortly. I request Professor Vineet and Professor Subrajit Biswas to be on the dais, please. Respected Chief Guest, Professor Jacques Poysiger, CNRS Research Director, Nice, France. Honorable Founder President, Dr. Ashok K. Chauhan, sir. Honorable Chancellor of Amity University, Uttar Pradesh, Dr. Atul Chauhan, sir. Most respected Vice Chancellor, Dr. Balwinder Shukla, ma'am. Dr. W. Selvamurthy, sir, President ASTIF. Campus heads, all the esteemed guests, esteemed scientists, dignitaries, head of the institutions, faculty members, and all the participants from across the world who have joined us online as well as offline for the inaugural session of 4-day India EMBO lecture course on tumor metabolism, current understanding and opportunities for novel drug discovery. We extend a very warm welcome to all. Devi Saraswati, an epitome of true knowledge, is regarded as the source of endless learning and represents the free flow of wisdom. Keeping up with the tradition at Amity University, I invite all the dignitaries for lighting of the lamp and Saraswati Vanna. Kindly join near the lamp.
ॐ भूर्भुवः स्वः तत्सवितुर्वरेण्यं भर्गो देवस्य धीमहि धियो यो नः प्रचोदयात् धियो यो नः प्रचोदयात्। जय जय हे भगवती सुरभारती जय जय हे भगवती सुरभारती तव चरणों प्रणामा तव चरणों प्रणामा नाद ब्रह्ममयी हे वागीश्वरी नाद ब्रह्ममयी हे वागीश्वरी शरणं ते गच्छामः त्वमसि शरण्या त्रिभुवनधन्या सुरमुनिवन्दिता शरणा नवरसमधुरा कविता मुखरा स्मितरुचिरुचिराभरणा जय जय हे भगवती सुरभारती तव चरणों प्रणामा जय जय हे भगवती सुरभारती जय जय हे भगवती सुरभारती जय जय हे भगवती सुरभारती।
The Saraswati Vandana was beautifully sung by students and research scholars of AIMS, sir. Thank you, Professor Chaya and Dr. Nilanjana for coordinating. Thank you all. This workshop is organized to provide a platform where leading national and international scientists will deliberate on the frontier areas of tumor metabolism and will provide a glimpse of what future beholds for the healthcare. Professor B.C. Das is the chairman and head of Amity Institute of Molecular Medicine and Stem Cell Research, officiating director, Amity Institute of Biotechnology, Dean of Health and Allied Sciences, AUUP, and Vice President of Amity Science, Technology and Innovation Foundation. It's my immense privilege to humbly invite Professor B.C. Das, sir, to deliver his opening remarks about the workshop. Request you to please come over, sir.
Well, very, very good morning to one and all. At the outset, I welcome our most honorable founder president and the very great visionary and founder president of the Amity Group of Education Foundation. He is, you can see on the online, he has joined. And I also seek the blessings and the best wishes from our dynamic chancellor, Dr. Atul Chauhan, and our vice chancellor, Professor Dr. Balwinder Shukla, who is on the way, would be joining very shortly. And all the most importantly, the chief guest of this today's the lecture course of the MBO lecture course on tumor metabolism and current understanding and opportunities for novel drug discovery being organized by the MIT Institute of Molecular Medicine and Stem Cell Research. Welcome, madam. So welcome, madam, and also we welcome our chief guest, Professor Jacques Passaguer, CNRS Research Director, NES, France, and also member of EMBO. We'll have the round of applause for our founder president and the chief guest and our vice chancellor to welcome all. And also in the dignitaries on the dais, the Professor Dr. Selvamurthy, with the president of MIT Science and Technology Innovation Foundation, we call it STIF, and our other, the organizer of this workshop, my colleague, Professor Vineet Kumar, and the colleague who is the director of this AMSR, Dr. Subhrodit Viswas, and also one of the organizers there are several organizers. We have just selected one or two in the dais. So one is Professor Martina Kreutz from the Germany. And all most importantly, the participants of this lecture course, of the EMBO lecture course, and the experts, speakers who has come from all over the world. The majority are from the abroad, from different countries, and there are organizers from different places. So among them and the speakers who are like Professor Heather Christoph from the David Groen in the School of Medicine, UCLA, Professor Michael Lesanti from the University Salford, UK, Jacques Passaguer, who is the chief guest today, and he will also give a lecture in the as expert lecture in this the lecture course. CNRS, which is the famous organizations in France, and Professor Sarah Maria Fent from Belgium, and Martina Kreutz from the University Hospital Rosenberg, Germany, and also from India, Professor Apurva Sarin from INSTEM, DVT, NCBS, Bangalore, and Professor Sushil Kumar for IIT Bombay, and there are several other of my colleagues who are from the MIT Institute of Molecular Medicines, and also there are several from Portugal, Dr. Fatima Balcha, and also there are others. I will not take everybody's name. It is difficult to take everybody's name. So I, on behalf of the MIT fraternity and my own behalf, welcome you to this 4-day-long the India EMBO lecture course at MIT University. And starting from today, so just to have a brief, about the cancer metabolism. This is actually the topic today, the cancer metabolism. What is cancer metabolism? Why we are having that big lecture course here? Why the EMBO, European Molecular Biology Organizations, has chosen to have this workshop or the lecture course at MIT University. And it is because of the fact that the cancer is, as you know, the most important, complex and multifactorial and multi-step disease, but then which has now surpassed the cardiovascular disease, which was the number one, particularly in the developed countries. But the middle income countries like India is not far off, and very soon it is going to be is so in the middle income countries, and it may be possible because of the ever increasing high incidence and mortality of the cancer in India, and it has become serious public health problem of the world as well as in India. And very soon it may be possible that the way the cancer is increasing in India because of its inherent several reasons and the factors, that cancer may be very soon become a cancer capital of the world. India could be a cancer capital of the world. One thing we know, we have studied, that the cancer is a genetic disease. It means there is a specific mutation in the somatic genes, like in the somatic cells, the genes 2 to 8 or maybe more or maybe less, that these are all called driver genes. And if there is a mutation that leads to the cancer progression, but then, and their drug resistance. But then we know now that the metabolic, it is also known as the metabolic disease or the mitochondrial metabolic disease. So cancer show increased consumptions of the energy or glucose, and that leads to the glycolysis, which we know as Warburg effect. And it is because of the, in presence of oxygen, this becomes that there is a metabolic reprogramming in the cancer cells that leads to the cancer progressions. We also know the immunology or immune system is also involved. How it is involved, the cytokines can also alter the metabolism and interfere with hormones that control appetite, that causing the further loss of body weight. We know that if there is a cancer, we start losing the weight. Somatic mutations, and this is, we know, but then, and this is generally caused during the somatic cells in the DNA replication, during DNA replications, or it is a random mutations in the normal non-cancer stem cells or progenitor cells. So there is a link. Certainly there must be a link between the metabolic reprogramming or metabolic the cancer metabolism or the cancer cell metabolism and the gene mutations. Yes, there is a link between the energy metabolism, which is reprogrammed or programmed by the proliferations inducing oncogenes or the defecting tumor suppressor genes. And the most important today is that if we can understand, and we will be deliberating for the next 4 days, and different experts will share their knowledge, and we will deliberate, and these participants will interact to understand how this metabolic programming mechanism, which the cancer cells develops the chemo resistance or the radio resistance, and then if there is an approach or the target can be developed for the chemosensitization, that will be most important for the drug development. That is the molecules to medicines. That is the aim of this workshop, to my understanding. And with this background, I once again welcome, and I wish all the participants to have the academic feast rather for the next 4 days. And if anything is any problem from our side, for the organization side, I would request you to pardon us or suggest us to improve upon that. And we are there to help you if there is any problem in the stay or any other things. We have taken all the initiative to make it your stay very comfortable. And we would, there are many people on the online also. And so I would all to concentrate and to have this the conference fruitful and try to have the maximum knowledge gained with this, and also have the connections and the interneting with all the experts available here during the tea breaks and your lunch and dinner. So we are all together for the 3 times open times, and we can have the sideline discussions anytime and with personal level or in groups. So we could look forward this, and with this QR, I once again welcome and thank you very much for your participation with this lecture course. Thank you very much.
Thank you, Professor Das, for your kind words. Now I invite Professor Vineet Kumar, the main organizer of this workshop, to give a briefing on the program. Dr. Vineet Kumar.
Thank you, Dr. Yogita. So, very good morning to all the respected dignitaries, esteemed guests, experts, and head of the department, faculty members, and all the participants from India and abroad, those who have joined offline and online. On behalf of Dr. Ashok K. Chauhan, Founder President, MIT Education and Research Group, and Honorable Chancellor Sir, Dr. Atul K. Chauhan, and Honorable Vice Chancellor, Professor Balwinder Shukla, I express my sincere gratitude and welcome you to this 4-day India EMBO lecture course on tumor metabolism, current understanding and opportunities for novel drug discovery. So the very first day of this 4-day program will be focused on tumor metabolism, its historical prospects to the current status and molecular biology aspects, and glycolytic phenotype, which is the important parameter. In the next second day of this course include the concept of clinical significance of tumor glycolysis, the transporters, different enzymes, cofactors, and tumor microenvironment. The third day of this course, participants will be benefited and will gain knowledge on tumor glycolysis significantly, specifically on cancer stem cells and cancer stem cell metabolism, drug discovery, bioinformatics, and therapeutic opportunities arise from it. And in the last day of this course, the significant aspect of tumor glycolysis and its close relation with the immunity, which is emerging now very important aspects in order to decipher the immunity and metabolism and how to target that for therapeutic applications. And also some interdisciplinary subject, for example, machine learning and artificial intelligence, which is also very important these days in any area of research. For this 4-day program to cover all key topics related to tumor glycolysis, we have 28 experts with us from different part of the globe. And each day we have 2 sessions, morning and evening, along with 1 oral presentation and 1 poster presentation session. And one essential and very important aspects that we have included is there will be interaction of the participants with the eminent speaker, which is one of the main objective of this lecture course. So the main aim of this course is to share and disseminate old and recent knowledge on tumor glycolysis, immunity, drug discovery, and to share the recent advances, challenges, and opportunities in the field of tumor metabolism and drug discovery. So I would request all the participants, especially for PhD students, so please make the most out of it, as we have expert speakers line up for 4 days. Some of them are online and most of the speakers are offline. And I hope you will enjoy this interactive sessions and all the key lectures. So thank you.
I request Dr. Marina Krutz, co-organizer of the workshop, to kindly share her thoughts.
Good morning, everybody, ladies and gentlemen. I also would like to welcome you here for our conference and lecture course, Tumor Metabolism, Current Understanding and Opportunities for Novel Drug Discovery. Even though I'm listed as a co-organizer, I have to emphasize that the main workload was on the side of Vineet Kumar, He had the idea for this conference. He applied for the money and he did most of the work. So thank you for that. I think we all agree that tumor metabolism is an extremely important topic. Almost 100 years after the discovery of Otto Warburg that glycolysis is accelerated in tumor cells, there is still no drug available that targets tumor glycolysis. Even so, for diagnostic purposes, a Warburg effect is used in positron emission tomography. No drug is available. There are several trials with other tumor metabolism targeting drugs, such as IDO inhibitors or IDH, but glycolysis there is still a challenge to find novel drugs for cancer treatment. I hope that this conference will lead to fruitful discussions among students and the faculty and the speakers, and exchange of ideas that promote drug development in the near future. Thank you.
Thank you, Professor Vineet and Professor Marina, to kindly share your words. We are humbly graced by the auspicious presence of our leader and great visionary, Honorable Vice Chancellor, Professor Dr. Balwinder Shukla Ma'am, at this inaugural ceremony. Professor Dr. Balwinder Shukla Ma'am is the Vice Chancellor of Amity University, Uttar Pradesh, Noida. She pursued her MTech from IIT Kharagpur and doctoral degree from Queen's University, UK. She has over 25 years of experience. Dr. Shukla heads more than 20 committees as chairperson within Amity and outside. She is on the advisory board of many companies, is a member of several professional bodies, and is closely associated with many corporate social responsibility projects. I know ma'am has to go for a meeting, so I request her to kindly share her words.
Most respected Honorable Founder President, our Honorable Chief Guest, Professor Jacques Sanders, the CNRS Research Director, our President, Amity Science Technology Innovation, Dr. Salamurthy, our Chairman of AMSR, Professor B.C. Das, Professor Marina, Crudis co-organizer, Professor Vineet Kumar, and Professor Subhajit Biswas, Director AMSR, and all the participants from across the globe, members of Amity Education Group. First of all, on behalf of Honorable Founder President, Honorable Chancellor, all the deans and head of institutions, extend very warm welcome to all the participants for India EMBO lecture course on the theme Tumor Metabolism, Current Understanding and Opportunities for Novel Drug Discovery. I would like to congratulate Dr. B.C. Das and his team for organizing this very, very important topical lecture course in collaboration with the EMBO. As we all know that cancer is the second leading cause of death worldwide. Despite significant advances in technological developments in modern medicines, there are still many issues that must be addressed to improve the cancer therapy. The European Molecular Biology Organization is a professional non-profit organization of more than 1,800 life scientists, and its goal is to promote research in life science and enable international exchange between the scientists. And this is one of the organizations which produces highly prestigious journals and have also some of the Nobel laureates have published their prestigious research papers in these journals. And any cancer biologist or any cancer scientist always look for the research references from these journals, because you do not find that high level of such publications which the AMBO journals provide an opportunity to the scientists. The first AMBO lecture course, which is being hosted by AMSR, has brought together eminent researchers and experts from the diverse disciplines of the cancer biology to share and discuss the recent advances, challenges, and opportunity in the field of tumor metabolism and drug discovery. And I can see the many young participants, the subject experts from the various countries like USA, Germany, France, Italy, Netherlands, Portugal, Belgium, Russia, China, Japan, and of course from India are part of this course lecture. And I'm sure that during these various lecture sessions, during the tea breaks and the lunch break, I'm sure all of you are going to get the opportunities to discuss, interact with each other. And our Honorable Founder President's vision is that to build a relationship and bring the synergies in the research to solve the societal problems and the global issues. And they cannot be the better way than the building these synergies and collaboration and cooperations. And since the cancer is the biggest cause for the the worldwide deaths, and finding a solution for this requires resources, requires the brains, requires the team work. And I'm sure with this sessions, I think many of you will find the people with the similar interests, people with working in the same areas, and where all of you will be able to find a collaborator to further the research and find the solutions. And our Honorable Founder President, Dr. Shokhi Chauhan, always says, that no work, no activity is good unless you drive the outcome from that workshop, short-term outcome and the long-term outcome. And I think that with that objective, the Amity Institute of Molecular Medicine and Stem Cell Research was established by Honorable Founder President, where our Dr. B.C. Das, as chairman of this institute, is leading to find the solution for the cancers. And I'm sure that this workshop is going to give many opportunities for all the participants for working jointly, maybe for the research projects or publishing the joint research papers and collaborating for the future work. With this, once again, I extend very warm welcome to all of you here at Amity University. And I'm extremely thankful to the AMBO team for collaborating with Amity University. And our founder president have always said that, that once somebody comes to Amitians and becomes the Amitian, once Amitian, forever Amitian. Therefore, this relationship is not just for this workshop, but the relationship is the beginning for the long-term collaborative research and finding the solutions. And our Honorable Chancellor, Dr. Atul Chauhan, have always said that let's join together, let's, have our synergies to change this world and to make this world a better place to live. And I think that eradicating the cancer disease can be the biggest mission to make this world really a truly happy world. With this, once again, I extend a very warm welcome to here at Amity University, and our team at AMSR at Amity University is there to extend all the support, whatever you need. And please have a happy and joyful state and state in India, and also have the outcome driven this workshop. So thank you very much and wish you all the best.
Thank you so much, ma'am, for your kind words. Your energy, passion, wisdom, and guidance has always been an inspiration for all of us. The research environment in our university, as big as and as divergent as Amity, best flourishes if it is provided with a strategically designated framework of research and innovation. Dr. Silva Murthy, President, Amity Science, Technology and Innovation Foundation, Director General for Amity Directorate of Science and Innovation and Chancellor, Amity University, Chhattisgarh, is promoting and coordinating research and innovation in all Amity institutions. An outstanding researcher, Dr. Silva Murthy, has served DRDO Government of India for 40 years and is now playing a pivotal role in catalyzing scientific and research innovations in Amity University. It is with great honor that I request Professor Silva Murthy to please share his thoughts about EMBO workshop with the audience. Sir.
Most Honorable Founder President, Dr. Ashok Chauhan, who is on the screen right from the beginning, for whom research and innovation is passion, life, the great unparalleled leader who has created this Amity Universe today, with 12 universities in India, 18 campuses abroad, 200,000 students, 10,000 faculties, 5,000 PhD scholars. Founder President, welcome to the inaugural session of this EMBO lecture course on tumor metabolism. We are also fortunate to have Professor Jacques Poisega, the CNRS Research Director from France, one of the great scientists in the field of cancer biology, molecular medicine, and the person who has done a lot of research on hypoxia, the pH, how does it lead to carcinogenesis, the pathogenesis of cancer. You have made outstanding contributions in this field. Let's welcome Professor Jacques Poisega on this podium today. Professor Marina Cruz, the co-organizer who has helped us to plan this session, along with Professor Vineet Kumar, our colleague. Thank you so much for giving a lot of valuable guidance in organizing this architecture of this 4 days event. Professor B.C. Das, my colleague, one of our outstanding global scientists in the field of cancer biology, who has worked with the Nobel laureate in Germany for 10 years. And he's an icon in the field of cancer, particularly the cancer metabolism. And we call him fondly the father of HPV, leading to cancer cervix, because he is the one who brought the human papilloma virus concept in the genesis of the cancer cervix. And we call him the father of the HPV, leading to cancer cervix. And my own colleague, Professor Biswas, and all the very distinguished speakers who have joined us, thank you so much for being with us in this very important lecture course organized by EMBO at Amity University today. And also all the delegates, my young PhD scholars who have joined us. And you are going to have a very intellectually enriching experience for the next couple of days. I must also place on record our gratitudes to the EMBO, the European Molecular Biology Organization, for having recognized, honored this Amity University by giving this responsibility to host this EMBO, the lecture course on the tumor metabolism. So it's a great honor for us, and we would like to do many, many more very close interaction with YEMBO and with all the members, the life members and the official office bearers and the scientists who are connected with YEMBO, because it's a great organization who is rendering a yeoman service to the scientific fraternity in the field of molecular medicine, molecular biology. So thank you, YEMBO, for giving this great honor to us. This seminar or this course is being organized in India at a very opportune time when we should look at a revolutionary change to be brought in the diagnostics and the therapeutics for cancer. Why I am saying it's the most opportune time, because today India is now, we are celebrating this year the 75 years of independence. We call it as Azadi Ka Amrit Mahotsav. That means 75 years of glorious journey of independence where India has made a mark in science and technology. And a begging bowl, which was India at the time of independence, is a breadbasket today through Green Revolution. We are number one in milk production. We are top 3 in agricultural production. And we are also strong in space technology, military technology, defense technologies, and also a knowledge power today with 1,100 universities and 65,000 colleges and a few lakhs of schools churning out the future global citizens in the form of knowledge workers to the whole globe. So today India is an economic power growing at the rate of 7.5% GDP. We are growing at that rate. We want to reach double digits soon. And we are going to be $5 trillion economy, adding every year $1 trillion economy to our economic structure, the growth. So that is India today. And we are also at the verge of entering into Amrit Kal, that is next 25 years is going to be very critical for us. So we are now rolling up our sleeves to work, commit ourselves with determination to make India a developed India through science and technology. That is why this YEMBO workshop or the YEMBO conference is very important for us. And when we look back in science and technology, today we are number 3rd in publication. We are number 9 in patents. And we in Global Innovation Index, we just pole vaulted from 81st position to now 40th position. And we want to be in top 20 at least soon. So that is how the India is growing. So this YEMBO conference is very important for us to learn from you. And whatever India is today, you have contributed. All the people who have come from different parts of the world and who are online, and you have made this proud for our country. And Amity is making this significant contribution in our whatever merit list I said, publication. We have 40,000 research publications in the last 1 decade. We have filed 1,900 patents today in Amity University. And we have our H index is more than 125. So we are growing. Amity is contributing to whatever transformation is India under the able leadership of Dr. Ashok Chauhan, the founder president, and the chancellors, Dr. Atul Chauhan, Dr. Asim Chauhan. So that is why this is an opportune time. When we sit together with 25 countries, participants coming from 25 countries, that how do we make a difference? As Chancellor Dr. Atul Chauhan says, can we join together as a consortium and then work to the good of the humanity, particularly to formulate new therapeutics, new diagnostics. So that is why this conference is important. So whenever we organize any event here today, we would like to have a sustainable, the revolutionary outcome, not just incremental advancement in knowledge. So I'm sure we'll have a lot of discussions in the sidelines of this conference to work out a consortium. Because Amity has started research clusters. Dr. Ashok Chauhan said, how do we bring synergy of minds? So there is a mission synergy in which we would like to connect within the group, Amity group, because we have 200,000 students and 10,000 faculties. So cancer biology is the first research cluster out of 20 clusters which are active in Amity. So cancer biology is the strongest cluster today. So that is hosting this particular event. And then now I give a clarion call to all of us here that let us make a Amity Global Consortium on cancer biology. The research cluster which we have made within the Amity group, how do we connect with all those experts who have come from different fields in the molecular biology, molecular medicine, stem cell research, regenerative medicine. How do we build a consortium? So I give a clarion call to everyone to consider Amity Global Consortium, in which we would like to make a significant contribution to development of early diagnostics. It could be simple field screening tests so that you can screen a large number of people, and also a new therapeutics as well as the drug delivery system. Now with this, I would like to give a little glimpse of Amity. Having come, you should also know a little bit about Amity, the host institution. So I'll give a little glimpse in the next 5 to 7 minutes. So welcome all the experts who have come to the tumor metabolism, the current understanding, opportunities for novel drug discovery. This is the forecast with the New Scientist magazine, which has made that India, the next knowledge superpower. India, the next knowledge superpower. So this was forecast by our founder president in 1996, when he was addressing in a school that India will become a knowledge superpower. And this is also echoed by this New Scientist, India, the next knowledge superpower, in which we will generate new knowledge, secure the knowledge through IPR, and also apply the knowledge for solving the problems, generating wealth to the country, and also bringing out new innovative solutions to the societal needs. We are third in research publications. We are third in number of PhDs in the world, third in the startup ecosystem, and also 7th in patent filing and 5th in the trademarks, and 40th in the Global Innovation Index, which we moved from 81 to 40. And we are 45th in the innovation output. And there are more than 1,000 scientists in the top 2% Stanford survey, in which they identified top scientists, 2% scientists in the world. And we are also top 5 in the space exploration. We are growing. So this Dr. Chauhan, who spent 28 years in Germany, he thought the society can be transformed through education, research, innovation, philanthropy. That is how he invested all that what he brought, the knowledge of the best of the West, and he invested here to create a blend of best of the East with the best of West to create the Amity universe today. And for him, it is when God pushes somebody, inspires somebody, leads somebody, no power in the world can stop such a person, including himself. He is the person driven by God himself. And we're also driven by the young charismatic leaders as chancellors, Dr. Atul Chauhan, a product of London School of Economics, Dr. Asim Chauhan, the Wharton Business School product, and they are driving the whole Amity group in terms of the higher education, and Dr. Mrs. Amita Chauhan driving the 28 schools, which we have in addition to the universities. These are the landscape and the beautiful architecture of our 12 universities in India, and also 17 campuses abroad, including Dubai, Mauritius, Singapore, London, Romania, China, USA, Romania, Amsterdam, and many other countries, Kenya. And I was just there a couple of days ago in our New York Long Island campus, 175 acres facing the Atlantic Ocean. We are creating Amity Global Research Hub, which is the vision of Dr. Ashok Chauhan and also the Chancellor, Dr. Asim Chauhan. So this is how we are building. And in United Arab Emirates, we are the #1. And in the Long Islands, we are bringing verticals including cancer biology, Indian systems of medicine, yoga, Ayurveda, Ayurvedic biology. And we are also bringing Amity Global Research Hub to connect with all the EMBO scientists, as well as the scientists across the globe. And in the niche areas, we are creating verticals, including sustainable development. And we are running also 3-continent program today. 60 of our distinguished the students are there in the study abroad program, 3-continent program. So this is the Amity Global Research Hub. And we run about more than 300 undergraduate, postgraduate, doctoral program. You name any course, it is there. It's a multi-dimensional university and also multidisciplinary university, where seamless connectivity between departments and faculties exist here. And today, even though the university is 18 years young, in the national ranking, we are number 22 as a university. 1,100 universities in India, we are number 22, and we want to be in top 10 soon. Pharmacy, we are number 17. We have vast accreditation from USA. The Time Higher Education put Amity in top 3%. And also we have QAA and also many other accreditation which are required for an institution like Amity.
The Indian Intellectual Property Office of the Government of India has conferred the National Intellectual Property Award 2020 on Amity University for Top Indian Academic Institution for Patents and Commercialization, a reflection of Amity's commitment to research and innovation.
It was one of the recent accomplishments received by Dr. Ashok K. Chauhan, the founder president, who is here with us on the screen. Was joined us virtually. We also got a special award for appreciation for the IPR. This is the glimpse of our achievements. And today we have 700,000 alumni across the globe. Imagine the force, the future global citizens Amity will be churning out soon in the next decade. You can imagine the logarithmic progression of alumni. Today, the number is close to about 700,000 in different countries, including US, Canada, Japan, Europe. And so we have 1,890 patents, 30 technologies transferred to industries, and 400 ongoing research projects. And we are connected to Nobel laureates and honorary professors. And we would like to have you associated as well with Amity as honorary professors. We have both nationally funded projects and international projects like DFC Germany, Bill and Melinda Gates Foundation, Wellcome Trust projects, now the EMBO program, which we are hosting over here. And we created the all ecosystem required, the right ecosystem for research and innovation to blossom, like the seamless connectivity with universities in India and abroad through MOUs, industry, laboratories, and the society. Then we created the IPR cell, Technology Transfer Directorate. We enabled the technology through a technology enabling center funded by the government of India, and also entrepreneurship development, because we want our children to not only seek employment, but to generate employment. So we are focusing on entrepreneurship development as well. And we have brought senior people like Dr. Das, blended with young people like Dr. Vineet, and also Ramalinga Swami fellows like Manoj Garg, and many people we brought. So the blend of senior people with experience, wisdom, knowledge, expertise, blended with the young, energetic force made the difference for Amity. And we also keep on connecting with the honorary professors, honorary doctorates, awardees from Amity University across the globe, including the Nobel laureates, and we connect with them. And our faculties go and work with these Nobel laureates, with the honorary professors from Stanford, Cambridge, Brown, Cornell, Kyoto, Singapore, NUS Singapore, Toronto, and many more. So we have honorary professors across the globe. And we brought such very senior people, which some of you see on the dais, some of them off the dais over here. And we also brought youngsters, the Ramalinga Swami fellows who spent almost a decade or so or more in Europe, USA, as well as in Japan and other countries, South Korea and so on. So this worked a great change for Amity. These are the young faculties who are joined us from across the globe. This is the Technology Enabling Center for maturing the technology from low level of TRL to higher level of TRL. Then we created an incubator, which has incubated more than 300 companies. 70 startups are doing very well. We have taken equities in these 15 to 20% equities in these companies. And our founder has set a goal, next 10 years, we should be incubating 1,000 companies to be incubator. And then these are some of the very successful incubators who are now, I hope some of them will transform into unicorn soon. And then founder president created missions to drive this. Mission Impossible. How do we augment the research outcome exponentially, 10x? So we created the Mission Impossible and we achieved it. And the Mission Connect, we are connecting with all the members of EMBO now, all those who are present here as well as online. Mission Synergy, Mission Outcome. So these are the ones which drives the Amity group. So we would like to give this experience to all those participants who are here. And also we have a strong connect. We have brought industry to our campus. Not only we are connected to industry, but industries are co-located in our campus. That brings seamless connect between industry, our students and faculties. We created state-of-the-art facilities. I invite all of you to visit whenever you have off time, visit some of our wonderful state-of-the-art labs. This is Dr. B.C. Das lab, molecular medicine and stem cell research lab, where he has sophisticated equipments like fax and also the many other equipments. I'm just giving a glimpse just to show that after having brought people, created the ecosystem, we also created the necessary research and development infrastructure. The US Department of Defense funded a major project from DETRA, Defense Threat Reduction Agency, on nuclear security. So we are doing a major project. And now I was in the US talking to the Department of Defense because I have connectivity with them. And I was in the Pentagon earlier and also with the National Academy of Science, Engineering and Medicine. I had interaction with them. So we, and Air Force Research Laboratory at Dayton, Ohio. So we have a very strong connect with the US Department of Defense for research and innovation. And we have strong MOUs, which are functional, both at national and international level, like Indian Council of Agriculture Research, Indian Council of Medical Research, Council of Scientific and Industrial Research, DRDO institutions, and many other international universities like Johns Hopkins, Iowa State University, and so on. This brings up force multiplier effect. We have created verticals, specialization in our 12 universities in computational biology, cancer biology, as I said, very strong, which we are going to deliberate, translational research, molecular medicine, stem cell research, genome engineering is a young department which we have created, neuroscience and public health, click chemistry is yet another. John Moses is our partner from US. And so we have drug design, and discovery separate. The vertical we have created, Indian systems of medicine and atmospheric ocean science and technology. Data science, artificial intelligence, machine learning, deep learning, nanotechnology, robotics, space science, astrobiology, spintronics. So these are some of the verticals we created. Food and agriculture with post-harvest as one of the focus areas, bioenergy and so on. And there are a number of innovations, but I would like to mention a few of them just to give an idea. In cancer, Dr. Das' group is working on triple conjugate. See, everyone attacks cancer cell, but we are attacking cancer stem cell so that the cancer doesn't recur again. So what we are doing is a development of a triple conjugate, a known anti-tumor agent, curcumin and folate. Together, we are able to create a triple conjugate. And then the curcumin tones down the adverse side effects of the chemotherapeutic agent. Folate gives the signature of the cancer stem cell. Ultimately, you have this in vitro, in vivo studies. We have been able to demonstrate the beneficial effects for the cancer treatment. So we will be taking it forward to the phase 1 trial after completing the safety trials, which is now going on. Dr. Das will explain more about it. A number of programs is going on in molecular biology. I have not been able to put everything. I've just given a little glimpse. We will give you the presentation to you so that you will be able to see. So, genome editing approach to cleave viral oncogene mRNA by CRISPR-Cas, and also the Cas13a system in cervical cancer. And we are developing a nanohydrogels for the drug delivery and drug targeting. This is again done by one of our click chemistry group, and also miRNA microconjugates for targeted therapy in liver cancer. We are also working on survivin as very important, the system as a therapeutic agent. And we are also looking at early biomarkers as well as both in liquid as well as in the solid biopsy, which we have been able to arrive at some of those early biomarkers, so which our colleagues will be presenting it. We are also looking at the herbal medicine approach, not only curcumin, but we are also looking at the Unani herbs medicine also for the treatment of cancer. So these are some of the glimpses on the cancer biology, and you will learn more about it. And one I will pick up in this slide, the sphingolipid signaling in tumor progression is a very important area which we are doing it in a very focused manner, this area. So I will just mention again in this slide, one take repurposing of the drugs. We are also doing And the hydrogel nanotubes, which I have shown here, are the nanostructures for not only cancer, but diabetic wound healing. We have also developed an AI platform for downstreaming the potential candidates for vaccine. So this is done by our bioinformatics group, and we have worked with a US laboratory on this particular field. And we have developed L-DOPA herbal, and I will quickly go through these are some herbal medicine on the water purification, which may not be of great interest to you. And we are working on the energy, bioenergy, as well as creating energy from wastewater and water purification by nano silver. So all these areas. In agriculture, we are looking at the productivity per hectare to be increased by using microbial technology. We have identified a root endophyte, which is known as Piriformospora indica, which can augment the abiotic stress tolerance. We are also working on post-harvest technologies, zero energy cooling chamber, and also amicule sensor development, and also the reversible blocking of ethylene receptor using MCP1. So these are some of the glimpses. And we are also looking at doubling the income of the farmer using photovoltaic in the field itself. Very strong space science and technology. And this is our chancellor getting this inauguration done at Amity, Dubai on the space technologies. We are also preparing the CubeSat we are going to launch this year. And also the first biological payload from India to space is going from Amity University, Mumbai, where we are putting a callus of a plant as well as a bacteria into space for the biological experiments from Amity. And these are some of the other areas like we have materials, spintronics materials, click chemistry, and we are developing the Amity Global Research Hub. These are the technologies which are transferred to the industry. There are more than 30 technologies which have gone to the industry. And now finally, in the COVID, we developed a number of frugal innovations which will help even the people at the bottom of the pyramid. Again, I'll take one here, the low-cost portable ventilator, which is easily accessible, affordable to even people at the lower socio-economic strata. Many of our scientists, faculties, they get awards, recognition. Just to mention, Fellow of the Royal Society of Chemistry, Fellow of the Royal Society of Biology, and also the Agricultural Leadership Award, and also Indian Council of Medical Research Awards, many, many more, including Curie, Mary Curie fellowships our scientists have got, our faculties have got. 24 Amity faculties are in top 2% of the global researchers from India. That's a great honor for us. So I welcome all of you once again, and I hope that we'll have great opportunity to work together. Enjoy your stay here, and we are making your stay very comfortable and fruitful with sustainable outcome. I'm sure we'll have occasion to talk to each other, build connectivity, network with each other for long-lasting partnership. Because Dr. Chauhan always says that once you are in Amity, you are Amitian forever. So we hope to welcome you not only in Noida campus, but we have in 12 states in India. Wherever you go, please let us know that we'll give you an opportunity for us to visit there. Similarly, in 18 countries, we have presence now. But the founder president has put a goal that we should be in 50 countries. So our goal is from 18 to 50 in next 10 years. Similarly, from 12 to 29 in next 10 years. So founder president, we will achieve with your blessings. And thank you so much for everyone. Have a wonderful day.
Thank you so much, Professor Silva Murthy, for your kind words. We have the profound privilege to have Professor Jacques with us today. Professor Jacques' group studies the mechanism of action of growth factors and has characterized the major signaling pathways, controlling cell proliferation, nutritional stress, and aberrant metabolism, and key targets induced by nutritional stress and hypoxia in tumors. He has received several awards, including Lounsbury Prize of American and French Academy of Sciences, Leopold Greffel Cancer Prize, Sir Hans Crabbe Medal, and Carl Corey Lecture Award. It is with great honor that I request Professor Jacques to please share his thoughts about the workshop with the audience.
Well, thank you very much. It's first, welcome to all of you. It's a pleasure, an honor to be here. And in particular, after listening to the president, I can say that I'm really impressed with what Amity University is doing. So I will be short because my talk is already made advanced, okay? But what I want to say is my fourth time in India, and already, of course, we can see the big change. My first visit was in 1927, and you can see all what has changed here. So what I would say, I would like to congratulate Professor Vinit Tumour for the invitation and all the organizing committee for making this workshop possible. And this is a great honor to be here, I tell you, because as a NEMBO member, I'm very pleased to see that you are joining the Alliance, the EMBO Alliance, and this will be a very great advance for many PhD students in this country, and also to share the idea, the progress, like in different type of labs, and like in Germany, like I done when I was a young PhD student and going and to see for all practical course. Practical course is one of the bases for advance in research, and I'm very glad that this university has obtained this alliance with EMBO. So for this, I will go more, and then when it's ready, I will do my presentation. I don't know if it's now. Okay.
Thank you, Professor Jacks. He is going to give the speech after we hear Honorable Founder President. So let me have the pleasure of giving a brief glimpse of our Founder President, Dr. Ashok Chauhan. He did his master's in chemistry from a university nearby, Meerut University, then went to Germany on a German scholarship, did his doctorate in chemical engineering there. He became an entrepreneur. He first became a chief of an R&D in a laboratory. Then he owned many industries there, and he employed 6,000 Germans and other internationals in his payroll in the companies which he acquired there. So when the reunion happened between East and West Germany, he was the largest non-European investor there, with the Chancellor of Germany saying, I brought stability, political stability to my country, Germany, but Dr. Ashok Chauhan brought the economic stability to my country, Germany. So this is what, to quote the Chancellor, German Chancellor said. So that was the history of Dr. Ashok Chauhan. Then he brought all those, what he learned there in 28 years of his stay there, and learned all the work ethos, culture, success by compulsion, the philosophy, all that he came along with the money which he saved there of working hard there. Then he brought and invested in education, research, innovation, and philanthropy, the four verticals on which he brought a change in our country today. The top global brand in education, research, innovation, Amity is today. It's because of Dr. Ashok Chauhan. For him, innovation is research, and innovation is life, his breath, as well as junoon, passion. So this is with that, he gives a lot of importance for research and innovation, science, technology, innovation. He has created a S&T war room, science, technology war room, to work with such a speed so that we'll be able to address many societal needs. Thank you, Founder President, for joining us. We would like to listen to you, your words of wisdom, as well as blessings to all the participants who are over here. Dr. Ashok Chauhan. Let's give a big clap to Dr. Chauhan.
I'm so glad to be part of this lecture course, because what we are doing today is something unique in the history of our committee group. There are more than 1,000 conferences workshops, seminar, but I'm so impressed that European Molecular Organization, Molecular Biology Organization has found a way, which is my obsession, which is my dream, the outcome, the result. I have known from Dr. B.C. Das, Dr. Vineet Kumar, that what is the system of EMBO? It is something amazing that every step is concentrated on quality of this lecture course, and everything is concentrated on result and outcome. I have never seen ever anywhere such organization which is so much focused that every effort, every investment, and every time they have positive outcome and results. I have read tonight everything about EMBO. I think I know everything. And secondly, EMBO is also very close to my heart because when in 1967, I flew to West Germany on a German scholarship, my first station was Heidelberg. I had a polishing course of German language at Collegium Platinum, and now after that, EMBO came. That time it was not there. So that is really a pleasure for me to again have my Heidelberg, where I spent quite a lot of time as a student, that I am facing that big organization today. Professor Marina Kreuz, if you allow, I can say, meine herzliche Begrüßung. Ich habe sehr gefreut, von Deutschland Sie zu sehen, und ich würde Sie bitten, geben Sie uns immer Ihr Rat und zeigen Sie uns den Weg, forward zu kommen. Dr. Sulmamurthy, Dr. Marina Kreuz is from there, therefore I have spoken to her in German language, telling her welcome. I would say that most of the things have been told. I heard Vineet Kumar, Dr. Sulmamurthy, Dr. B.C. Das, our Vice Chancellor. So I think they're all right. Innovation, research is the life of everybody, every scientist. And I'm very glad that such a big number of participants and 28 speakers, I have read biodata of most of the speakers, astonishing their worthiness, their work, their research acumen. I think that is a great value addition for me personally, and for Atul Chauhanji, our great Vice Chancellor, and also Dr. Sim Chauhanji, who is also a great Chancellor, that we follow the principle of EMBO to do the things which brings quality and research and forward way. So I would say that I will not speak much because the time is getting short, but I would say that I will, in between sometime these 4 days also come for a few minutes again. But all those who are attending, I must compliment them, I must congratulate them, I must bless them. You are facing today an environment here of such worthy persons, which you rarely find. All these 28 speakers and the participants, those who have been selected, Dr. Vineet Kumar told that they have not just come here. There was a great list of interested participants, and the EMBO committees have selected who should be selected for attending this EMBO lecture workshop, lecture course. Just the name lecture course tells everything. I have never heard this connotation lecture course. I would say that let us spend these 4 days very valuable, and Professor Jacques Pony-Gur and Professor Marina Kreuz, please compliment the organizers, all organizers, you are one of them, and also all at the helm of the affairs of EMBO. EMBO is changing the world, not only in the area of tumor metabolism, but in all other scientific areas. I am very proud that Vineet Kumar's proposal could be accepted, because I know from other universities that a lot of people apply, But if the proposal of Dr. Vineet Kumar under the guidance of Dr. P.C. Das is accepted, it gives me a lot of pleasure that my scientists have that acumen, that capability, that EMBO also recognizes them. So once again, to my participants, those who are listening, offline, online, I am so proud. I think together with the synergy of brains, this has been my slogan since decades and decades. These 28 scientists and my great scientists in all my universities, I think we can do wonders, which I don't think anybody else in the world can do. Because for people hardly think of synergy of brains. They are doing individual research in their own labs, but I think this today lecture course will show us the path to achieve excellent result. Dr. P.C. Das is an exceptionally qualified, experienced cancer researcher. So I would say my compliment to everybody and my thanks for coming here. And I take the pledge that with the help of you, with the guidance of you all, I think we should do wonders which others cannot even imagine. Dr. Naudi, thank you very much. Dr. P.C. Das, thank you very much that we are sitting together in four days to try to begin a lot of work in the cancer area. Thank you very much.
Thank you, Founder President. Dr. Marina will respond to your German language, what you swear.
Great.
So, thank you very much. Vielen herzlichen Dank für die Einladung zu dieser Konferenz. Ich fühle mich sehr geehrt. I'm honored to be here and I'm grateful. Ich bin sehr dankbar, dass ich meine Ergebnisse hier präsentiert habe, that I'm able to present my data. Thank you very much.
Rena, we are so erfreut that Sie here with uns sind. We are so erfreut. Thank you.
Thank you, Founder President.
Thank you, sir. Thank you for your blessings and for your motivation. I am sure each and every participant is motivated, and we all Amitians greatly admire your vision and firm commitment to nurture academic and professional excellence. So with this, we have reached the end of the inauguration ceremony. I kindly invite lecture back, please. So we are all waiting for the lecture to begin, but for this, the inaugural ceremony has to come to end. So for that, I now invite Professor Subhrajit Biswas, Director, AIMSR, for proposing the vote of thanks.
Thank you. I'm Professor Subhrajit Biswas, Director, Amity Institute of Molecular Medicine and Stem Cell Research. So it's a vote of thanks for introduction also, though we are starting the scientific session. So just no need to introduce the IMBO. And as a researcher at Amity Institute of Molecular Medicine and Stem Cell Research, I want to give one small fact. In 2012, that is John Gardner and Wamanaka received Nobel Prize for the stem cell work, all of you know. And they published several papers, or both of them have a publication, how they prepare the stem cells from the adult somatic stem cells. But they cited that, especially Gardner told, that is the Nobel Prize is not due to the all publication, the key publication, one is from IMBO, one is from PNS. This is the UCITE papers. So that is the IMBO, all of you know. I want to thank the entire IMBO teams in the world for the support this IMBO conference in our Amity Institute of Molecular Medicine, especially Amity University campus in Uttar Pradesh. I want to thank and express my gratitude to our Honorable Founder President, Sir, Dr. Ashok K. Chauhan, Sir. And with his vision, we are not only live in India, not only living in UP, we live in world and basically in the universe. And Shilmamuti sir already mentioned about that. That is, we have a all platform, scientific platform throughout the world. And many, many thanks to the organizer, Dr. Vineet, Dr. Marina Cruz, for the step forward to organize sorry about that. So many thanks to Dr. Binit, Dr. Marina Cruz for step forward and organize this EMBO conference in our platform, and thanks to other organizers, Dr. Reshma, Dr. Prakash, Dr. Manoj Garg, Dr. Binder, and special thanks to Professor Jack Kusnagar, who came from the CNRS and is the president. And thank you, sir, for coming and be with us. And with your guidance, the conference will continue. I want to thank full of our mentor, philosopher, Professor B.C. Das sir and Shilvamurthy sir. And with all of your guidance, we'll organize this prestigious meeting in Amity University. We're thankful to Chancellor sir, Dr. Atul Chauhan sir, as well as Ashim Chauhan sir, VC ma'am, Balvinder Shukla ma'am, and their blessings. Professor Shodhi sir and Dr. Dargan sir, thank you very much for your team for support the audio-visual system in the hybrid system. So throughout the world, the program to be telecasted. And apart from that, I express my thank to the all speakers, chairperson in the conference, research scholars, and the student volunteers. And please excuse me if I left somebody. And thank you very much. Thank you very much to all of you. Sure.
Very well, Vishwas. Very well, Vishwas. I'm proud of you.
Thank you, sir. Your blessings. Yeah. So now we are inviting all of you for the tea break, and after that we'll start the scientific session. It's in the long. Thank you, Founder.
Can you also tell the time, how many minutes, so that they are here? Break, tea break.
Oh, it is 15 minutes breaks for the tea break. We are coming for this.
So please join us at 11:20 sharp.
Sure.
So there is a small change in the program. Please have a coffee break, and then we
several publication, high impact journal. She has several patent in her credit. Particularly, the list of her publication and patent is very long. I'm not going to read all the publication and patent. The most fascinated her paper is she published in Blood, Cell Report, and Cell Metabolism that is related to this theme. And her patent, I am really interested and fascinated with this work, that is alkalization for the tumor environment to suppress the immunotherapy. So I invite Dr. Marina, please take over this session.
Yeah, hello again. I'm happy and grateful to announce the talk of Jacques Puisigueur, a respected colleague, collaborator, and friend. We met several years ago at a conference in Mainz and started a, I think, fruitful collaboration. Jacques is a kind of scientific role model for me, and I think you all know him. His work is famous. He started to work on tumor metabolism years ago when this was not en vogue. Nobody did it. So he is a pioneer in this field. And I'm very happy to have him here and looking forward to your talk, Jack. Thank you.
Every time I move away, how would you remove this? Okay, that's okay. We have already this always. Okay, and this let me see. For that, okay, but it's you have to put. Well, before starting, it's again I say a real pleasure to be here. And again, I want to congratulate and thank all the organizing committee, in particular, Professor. Okay, but this one doesn't go. Okay, yeah, both. Yeah, and Professor Vinit, yeah, Tumour for organizing such a fantastic MBO course. We see, but the program is excellent, and again, a pleasure to go now. Okay, so you have the title here. We have a little change because we cannot get from computer from the Macintosh the same what we would like anyway. So you excuse me for this. So this is the Talmar Jack during my first discovery of India in 1997. Then we, of course, you have to go to that palace. It's so beautiful, and when you know the love story behind this possession is marvelous. Of course, I went there with my wife, Vivian, and you see already an Indian, going there very well. And then now we enter. So you know that the life starts in hypoxia. And when we look in history on the old bacteria, the Ecce bacteria, you can see many metabolisms, but the glycolytic enzyme are already present. So even before photosynthesis, we can see on the archaebacteria. So what my way of seeing, the fermentative glycolysis is strongly imprinted in the hypoxic form of life from the beginning. And very important for the vascularization. And also, you see in the seawater, we still have the solution of salt running in our circulation, in our vein. It's a very strong imprinting. Now, life appeared in this 3.5 million years ago, and you can see here the first cyanobacteria that invite an algae in order to make the photosynthesis. And both start to integrate the CO2, to capture the CO2 in the ocean, and then to stimulate the chemistry of carbohydrate, and then release oxygen. And the release of oxygen, of course, is even more stronger when the life went to the chloroplast on the continent, with the chloroplast that's very much more active. And here the CO2 capture, chemistry of hydrocarbon, and then you release oxygen as a waste. But as a very important molecule for life of the animal domain. And the animal world has connected like a symposia to the vegetable here. And for this, you release a CO2 as a waste. And we know now all that if we cannot control the animal life on this planet, we are in trouble. And because the not control, then we won't have the control of CO2. So this we all now have that in mind. Now, just to start for the vascularization and the role of hypoxia or the oxygen, this is very important for the vascularization. I will show a very simple experiment done in the, that was published in the Science 79, a very old one, but you will see how you could learn. When you implant a piece of tumor in the mice cornea, then in this case, you will see the capillary start to grow, and you see better, day 10, there is a tropism of the capillary going to the piece of tumor. And the reason for this is that the piece of tumor, well, this is, okay. Oh, wait, it doesn't work, I'll try that. But when you go to day 12, then it doesn't need any explanation. You see that the capillary reach the tumor, bring the nutrient to the tumor, and the tumor grows. And the reason for that is that you have in this hypoxic environment here, you have the secretion of the vascular endothelial growth factor that is capable to stimulate the migration and the division of this capillary. And because we are here in hypoxic condition, and this capillary possesses the receptor for the vascular endothelial growth factor. Vascular endothelial growth factor is a key growth factor that makes vascularization possible. And I want to mention for this, I've been to many meetings, but Judah Folkman, that passed away by heart attack, but is a surgeon that was always in the surgery hospital. And when he was not in surgery, he was on the lab to see how to stimulate the growth of vascular genesis. And then VEGF was isolated by Napoleon Ferrara, was in sabbatical in San Francisco myself, and he was doing with the lab of Gospodarovich, he was purifying like crazy this growth factor and find the VEGF. And then the VEGF-A, he make, of course, as you expect, an antibody against the VEGF, and then it was recruited to Genentech, close to the San Francisco University, and then he demonstrated that when you inject a tumor in mice, then the co-injection of the antibody against VEGF stop the growth of the tumor. And that was the beginning of a big area of clinic, try to start on the clinic with anti-angiogenic approach. Now, just in my lab, just a little experiment we made. The mouse embryonic stem cell that you see here is like a galaxy of cells with the CD31 that you have. But when you add VEGF-A, then you see here immediate VEGF growth, differentiation of vascular endothelial cells, and but in fact, it's not the human VEGF-A. The VEGF-A does this. This is a snake VEGF analog. A postdoc from Tunis came to my lab. He isolated 90% homologous VEGF in the venom gland of a vipera. He came to my lab to see whether it is angiogenic. This VEGF-A is a VEGF analog of the snake venom. And of course, you don't want to have in the evolution to have an angiogenic compound in the, but there is another characteristic for the VEGF is the permeability factor. So when the snake bites, okay, the prey, you want to send the toxin right away to the brain. And the best way to that is that the VEGF is capable to permeabilize the vascularity. This has been evolved. 2 years ago, I learned that the same publication in JBC now turned out to be positive also in Brazil for many snakes. And in this country, I don't know, I know there are many snakes here, and possible that this evolution of the capillary, okay. Now we come to the big discovery that was bringing me to the hypoxia is when Greg Semenza identified the hypoxia-inducible factor 1 alpha, and this, which is with the alpha beta, the heterodimer, is now capable to induce many genes. And the tour de force of Greg Semenza was to apply and to look with the erythropoietin gene that is a growth factor for erythrocyte. And then he find where the hypoxia response element in which the complex bind and induce a gene. And we know now that more than 2,000, close to 2,500 genes are induced by the hypoxic component If1. And of course, then from this, you get many ways. You see the erythropoietin going on here, the VEGF-A angiopoietin 2 that induce vascularization, and where we are going to talk this week, glycolytic enzyme, very important, benefree for autophagy, that we did that with Nathalie Mazur, here present. Okay. So we made a specific antibody against the If1 alpha, the human antibody at this point, and we had a fantastic antibody for human, and we wanted to see how this If1 alpha is regulated in cancer, in tumor. So first, this is the culture of fibroblast or any type of tumor cell. Then you don't see too much because this is a parasite, okay? Then when you are in 20% oxygen, but if you go to 1% oxygen, then you see a rapid synthesis of If1 that go to the nucleus with the meet If1 beta and then induce this 2,000 genes. And the beauty of the system is that this is a rapid induction when the oxygen and a very rapid degradation. So if you reoxygenate your culture, you induce, you put the 20% oxygen right away, and you see the protein disappear. The picture of this was made 20 minutes after the reoxygenation. So it's one of the short half-life protein that I know in biology. Very. And this is very important. Oxygen sensing. And oxygen sensing has been done by prolyl hydroxylase. It's the same enzyme that we have also for hydroxylation of collagen. Same enzyme. But this, the PhD1, and the role for that, this, they have the same structure, is a oxo-reduction enzyme with an iron, and when it works, then it hydroxylates the proline residue on If1 alpha. And when you have this hydroxylation here, PhD1, 2, and 3 can do it, and then there is a complex that arrives, the VHL E3 ligase, a very important complex that is now capable to ubiquitinate the protein If1 alpha. And when you get the ubiquitination, then it's finished for the protein because they enter to the proteasome that make a very strong degradation, and the cells recuperate the amino acid here. So that was done by William Kaelin, that discovered this 1, 2, and 3 by Peter Radcliffe, I'm sorry, and William Kaelin also participated in one of the PhD2 and was the one that demonstrated that the von Hippel-Lindau protein is a tumor suppressor. When you have a mutation in the VHL, then the animal, which is the case for the tumor in the kidney, 80% of the renal cell carcinoma have high vasculature, very high. That was when you have the mutation in VHL. And of course, now in the hypoxia or low oxygen, prolyl hydroxylase cannot work because they need the oxygen as a substrate, and if one is not hydroxylate, stabilize, and then induce all the gene. So we made an experiment that I wanted to present to you here. We were shocked to see why we have a free enzyme, 1, 2, and 3. And that was at the same time where in normoxia, shorter pNRNA were demonstrated by Tom Chell in Germany, interfering RNA. We decided to knock down each PhD, okay? And this in normoxia. These are blue staining of the nucleus. You are in normoxia. And when you knock down here PhD1, where you don't see too much. When you knock down PhD2 with the shorter pNRNA, then you see the lightening like if you were in hypoxia. And then for PhD3, very little presentation. So this was the first demonstration that PhD2, and we published in the EMBO journal, that was the key oxygen sensing molecule for the vascularization. Now, when you do a discovery like this, there were, well, in the world of many people working in hypoxia, there was some skepticism, okay, always. That's what we need in science. We were very sure that PhD1 was important. And we get a proof, very important, a genetic approach came by 2 mutations in PhD2, not on the other oxygen sensor. And these 2 mutations were found in PhD2 in 85% of the Tibetans that living at 4,000 altitude. And the reason for this is that this mutation, epistatic, they change the affinity of the catalytic site for oxygen. So you have a reduction of catalytic affinity, and this reduces the expression of erythrocyte and blood viscosity. So at high altitude, now the Tibetan that have this mutation and the woman can deliver babies, they can live early. It's something very big change. But the story is not complete there because last year, or even we got the information that the Tibetan have get by transmission of the Denisovan very close to the Neanderthal, and these Denisovan are living, we are living in the high altitude in the cave. And the cave has the name of Denisovan, very close. And they find piece of DNA that were present in the Tibetan living in altitude. And this was a Nobel Prize for Swan Pabo, Nobel Prize of Medicine last year. Okay. So that story, what I say, the beauty of an oxygen sensing molecule, an enzyme, and you can see that all the discipline of biology were used for physiology, genetic medicine, and now homo evolution. And I want to say this work was done by a PhD student, a surgeon that started a PhD with us, Emmanuel Benizri, with Edouard Nebera, now is doing the work group in Bilbao. Now, we came to the cancer with this and to the nutrient. And you see all this aspect of oxygen sensing, biology, and vascularization, very important. You cannot get any cell proliferation if you don't have nutrients, you know, and you have to control. So in metazoan, it's known that hormone growth factor signaling the network will stimulate nutrient availability. And the way you stimulate this is by inducing the appropriate nutrient transporter. Many transporters like this that we know. And then when you are in this condition, well, the tumors start to perhaps have a deficit in nutrient. And when you have a nutritional stress, then you have a way to stimulate the present vasculature and to increase the vascularity. And the only way to get the stimulus is a drop in PO2. So you see how we are imprinted from the initial nature of life in hypoxia. So with our antibody, we use now a colon adenocarcinoma, one of the very rapid expanding cell line, tumor cell line from human. And you can see now with the antibody on the, so this is not the total tumor, it's a section in which you can do the labeling. And you have a vessel, you have many nodules like this. Each one is developing around one major vessel. And in this case, you can see the black expression of IF1 alpha on the periphery. And this gives you the oxygen gradient in the tumor, and not only for oxygen, but also for the nutrient, glucose, amino acids. Now, we use another antibody that we developed also, and that was developed also by another company first in Germany, and is the antibody against carbonic anhydrase 9. There are 15 isoforms of carbonic anhydrase, and there is one that we have worked on this, which typically induced by hypoxia. And this is the work we have initiated when Joanna Shish was in my lab for a PhD, in which we've done the labeling because it's an enzyme that is a pH regulating system for tumor. That's what we do. And this carbonic anhydrase 9 with a dye, a green dye, you can see that it decorates totally the hypoxic area of the tumor. and we can find in many cases. And this condition, now the tumor, of course, with this hypoxia is ready to stimulate the glycolysis, the Warburg effect, and of course, to make huge ATP for the lactate by the production of lactic acid, which is a problem. Lactic acid is rapidly acidifying, and you need to evacuate the lactic acid to maintain the energy process coming. So just quickly in this cartoon, I just want to tell you where the CO2, which is present here, the CO2 goes like a gas across the plasma membrane, and then it's rapidly hydrated by the carbonic anhydrase anion because it has the catalytic site exposed outside, and this will put all the proton outside and then induce the alkalinization in the cytoplasm. And if you suppress the carbonic anhydrase 9, as we have done in 2 types of tumor, then you strongly reduce the tumorigenicity by 80–90%. So pH has a very important aspect here. pH is not the only one. We have also here with the anhydrous carbonic and the sodium proton exchange, and as we will hear after and tomorrow with the MCT4 and MCT1 that are different. This one is regulated by hypoxia, MCT1 by MYC, and this play a key role in the growth of the tumor. So this is just to recall that the glycolysis and the possibility to get here ATP is very small. We know that 1 molecule of glucose forms 2 ATP. When you compare that with oxidation of a molecule of glucose is 18 times less. And yet, I'm convinced that the glycolysis is making more ATP than the respiration. For a simple reason, is because the quantity of enzyme is important. You make 2 molecules of ATP, but the glucose is still running, and in this case, you get much more ATP, more quicker when you need ATP than from the respiration, but it's one of the major bioenergetic pathways. So if one, as you know, of course, prevent the oxidation of pyruvate by blocking PDH with a PDK1 kinase, and in this case, the pyruvate goes to the lactate and is forced now to produce the energy, okay? Now, this, you know, has been used by many clinicians with an analog of glucose, FDG, to identify the metastasis, and also many sites of infection. All sites of infection are there because they use the glycolysis in this part. So, Warburg effect drives pathogen intracellular infection. And you see for virus, I'm sorry for that, but also bacteria and the metabolism is used for their fast replication. What this pathogen need is replication of the RNA or the DNA very quickly. Well, they need also some of the aspect of the metabolism to make the core and lipid. But this, as you see, is remarkable. It's not work directly, but this is the list of many viruses that have been used and that they employ the glycolysis for the rapid energy source and rapid infection. And I mentioned here, and of course, SARS-CoV-2 is not exempt, is also totally there. He likes hypoxia when you go to the lung, then the hypoxia, then he has all the energy provided from the glycolysis. And just I give Michael Loganoff in Seattle, they have Christoph that we hear perhaps by a lecture, and they have been working on different type of virus. And in France, Philippe Icard that has demonstrated that the SARS-CoV-2 is really using the glycolysis for that. So, well, this is, yes, you can see all the trend. That's only on my computer. Can we repress, or can we stop glycolysis? Oh, this big story also from this, for this workshop. Very easy and difficult. Of course, all companies, since I know about glycolysis for the last 50 years of my research, I know that there are many people and companies who are distributing some compound to block, and they all succeed in doing this to arrest tumor growth, but they induce cell death. And yet, no compound has been approved in the clinic due to toxicity. And of course, I know that there are many programs in this university also for doing this and there. And there is a very interesting approach now that we are going to be discussed in the. Now, we decide to revisit the Warburg effect by genetic disruption of three steps, either the isomerase upstream, lactico-dehydrogenase, or monocarboxylate transporter that export the lactic acid. So first, if we start with first you have the glucose entering, then you have the phosphorylation. Glucose phosphoisomerase into F6P is only one enzyme. So we knock out that gene with the CRISPR-Cas9, no gene, not at all. And then you see, you rerouted all the glucose that is already routing with glycolysis to the PPP, but here in the more quantity. And this, when you look now with the consequence of blocking upstream this enzyme, then you totally stop glycolysis. And the cells are alive, because what I show you is a cell that has no lactic acid formation. When you look here, lactate formation, secretion in the medium is the most simple assay that tells you how glycolysis works. And you see normoxic, hypoxic in blue, normoxic, hypoxic in blue. You see hypoxia, what it does in glycolysis? And all the virus and the infection, they are in the hypoxic area always. And GPI knockout, no lactate, no lactate. And cells alive, and they form a tumor with a rate 2 to 3-fold lower, but they still grow. And they grow because the mitochondria offers now the oxidation and the ATP by OXPHOS. Okay, and you see here the white type in black. When you give glucose, and here you measure oxygen consumption. When you give a glucose, the mutant goes fast, oxidizes very strongly the glucose, whereas in gray, the white type goes down, it makes the metabolite. So, okay. Then we went to the second step, and that was problematic in the way. We make a knockout of LDHA, the key enzyme making the transformation of pyruvate to lactate. And we didn't get the same result as here. We get always 30 to 40% lactic acid still formed. That was a shock, tell you, because no enzyme on gel, no totally, and yet. So we decided to make a second knockout, the knockout of LDHB. LDHB do a reverse reaction. It takes the lactic acid and transforms a pyruvate. But because there is an accumulation of substrate by the knockout of LDHA, we change the affinity for the pyruvate. In this case, we get exactly the same situation, a blockade of the lactic acid and the Warburg effect. When you go to, so all attempt to, all companies, I remember, there have been most of them, all the big pharma, they have targeted the LDHA and very toxic. Well, and this is why no one wanted to use that in the clinic, okay? But this is possible. And perhaps in the discussion, I could show that there is now pharmacology for the PhD, for the LDHA, the same pharmacological compound that identically inhibit the B. So it's the same molecule. And when we published this, we had the people from Genentech that just came to isolate this compound, a double inhibitor of A and B, that confirm our genetic approach here. And when I compare this cell line, colon adenocarcinoma or mouse melanoma, all of this I present to you, I've done in the 2 cell line. So for the colon adenocarcinoma, you have the white type in black, and in red, you see the rate of tumor are formed, but 3 times less. And then we attract now the exit of lactate. So the cells still show what I showed at the beginning. You stop the Warburg effect, tumor are still capable to go at a lower rate. Then now MCT, monocarboxylate transporter. MCT1 induced by by MYC, MCT4 induced by hypoxia. In this case, okay, first I won't show all the data. You see here the LDH and MCT4 knockout cell line. The white type is not present. It will be 3-4 times higher. But when on the top of this MCT4 knockout, we add now to the mice every day MCT1 inhibitor, then this is the rate of growth, 90%. And if you add fenformin, and then you collapse, as you expect, by blocking complex 1, there is no growth. Of course, it's not by genetic that we could enter the clinic, but it's very important to know the way we could do. And this, I will show you with this blockade, we stop growth, reduce strongly growth, because of the intracellular pH, the acidification, due to the blockade of lactic acid and pyruvic acid, prevent, and this block mTORC1 and growth protein synthesis stop. And that was part of the work, that was the collaboration we had with Marina Kretz and Ibtissam Marshik, and one of their PhD students came in our lab, and Ibtissam Marshik has the PhD on the MCTs, okay, and the chaperone on the MCTs, and in this work also. So for the melanoma, we start to use the MCT1 inhibitor. We're perhaps one of the first ones to use this MCT1 inhibitor that normally stop immune response. It was used for preventing graft response in the mice. That's what we knew. When I saw that paper, well, it was perhaps almost 20 years ago, then I called Claire Murray that has done this chemistry of MCT1 and to see. And then we used the MCT1 right away. She sent me, it was about Christmas, and we put in our tumor cells, and we got a beautiful block in the tumor, a tumor that didn't have the MCT4. And if we introduce, because that was fibroblast, if we introduce MCT4, then the cells are capable to grow. So MCT1 in cells, like an immune cell, that has only the MCT1 inhibitor will stop, will have a very strong impact to diminish the immune response. Not. So here, simple experiment, there needs to be a little explanation. These are colonies that you mark after a week. Then MCT1, when we use a 0.3 micromolar, that inhibit 90% of MCT1, no effect. Here, this is how we calibrate this by transport. 3 micromolar of MCT4 inhibitor also will inhibit 90% of MCT4. No effect. But when you combine both, then you get not a surprising, but the synergy of growth arrest. And I say growth arrest, not killing, because if you wash the medium, and you remove the 2 inhibitor, you put a fresh medium, and then after 2-3 days, you see colony starting. And this is why I know very well that accumulation of lactic acid and pyruvic acid are antioxidant, contrary to what has been published in several papers. Antioxidant, and they protect, stop, and they can start again. So it's a cytostatic effect, which is more important than to have the side effect. But it could be side effect. So in this, cartoon, a little bit changed, I won't say this is part of the collaboration, and because we are a little late, I won't go in that, but this has been absolutely great to collaborate with the group of Marina Kretz and also Toby about, and they will show you beautifully, she will show that when you manipulate, you reduce the glycolysis in the tumor, then you reduce, of course, the acidity. And this has a very strong impact to increase the permeability of the immune system in the tumor. And with Tobias Bob, it's a reverse. It's very interesting. Acidity, lactic acid, but any acid will modify the receptor of adenyl cyclase, will activate, and the ICER is capable to reprogram the tumor-associated macrophage in non-inflammatory macrophage. It's not a G protein copper receptor like you see in the literature, it's just the acidity by itself. Okay, and now I arrive almost to the close to the lecture, and you see, this is my preferred slide that I draw where I show a big arrow to make the big change. This glycolysis, fermentative glycolysis, is the most bioenergetic pathway that I know. Of course, the oxidation, the respiratory chain is unbelievable, capable to do ATP, but not in quantity at the speed as the glycolysis is doing. And lactate is not a waste, it's recycled, glycogen, energy substrate, and then this in liver, of course, it's a major organ for stockage, and for the stock here, heart, skeletal muscle, kidney, and brain. Now, when you have a decrease in oxygen, as I said already, you have an inhibition of the enzyme, the PDH, that prevent the oxidation. This is something that you want to make all the advantage to the glycolysis for energy. Also, a very interesting experiment that I saw in the literature, if you stop feeding your mice, then they will activate glycolysis. But at the same time, there is a two transcription factor that FOXK1 and FOXK2, like IF1, but with different kinase, inhibit PDH1. And in this condition, they will favor glycolysis to make a reserve of glycogen when like a signal of energy distress and okay to be served. Now, all cancer, of course, use glycolysis. Only the one that have a high progression, as we know, prostate cancer has a very low use, except at the late stage. But all cancer they use, when they grow fast, they use it. Immune cell, when they are activated by the antigen, well, they need to proliferate to have a very stronger immunoreactivity, and they use a glycolysis. And viruses and bacteria and the pathogen, as I mentioned to you, is also the major source of glycolysis. And also the organ repair, if you cut the tail of the zebrafish, then the stem cell immediately uses the glycolysis to repair the tissue. And this was a beautiful story in Lisbon published in eLife by this group. So in conclusion here, I would say tumor glycolysis growth arrest is fully suppression of glycolysis by GPI knockout or LDHB, double knockout suppress lactic acid production, reactivate OXPHOS, and allowing tumor to grow at a lower reduced rate. Then, although a best fit for cancer, Warburg effect is dispensable for tumor growth. And in contrast, disrupting lactic acid transporter, MCT1 and MCT4, arrest tumor growth by intracellular lactic acidosis, blunting mTORC1. So glycolysis, lactic acid, and immunity, you will have a very nice story tomorrow by Marina. Reduced lactate acidity, MCT1 and 4, offers therapeutic benefit by activating immune response, increase the tumor infiltration by T natural killer, and increase interferon gamma. And glycolysis nourish viral bacterial replication and future glycolysis inhibitors that are going to be discussed quite a lot in this workshop will have a great impact to control tumor growth as well as pathogen infection. So well, we were celebrating the centennial of vote to Warburg last year. This year, we know many times, but that's a great story there. And also, we cannot forget the lactate is not a waste product, but also a mobile, recycled as an energy metabolite. And there was a couple of Carl and Gertie Corey and their lab when they made this discovery, a Nobel Prize. And finally, the congratulations of our recent Nobel Prize. This is my private collection of pictures because I've been in many meetings with them also. I invite Greg Semenza in Paris for PhD. That was in 2007, you see. Peter Ratcliffe at the time where he discovered the oxygen sensing molecule, and another meeting in Italy, this one with William Kelling and his little son. Okay. Now, I had many talented PhD students in my lab, many, also postdoc, and of course, I want to say, of course, thank to them, and also thank to Susan Krishlow, from which I got the first compound MCT1, Marina Kress, Regensburg Hospital, and Tobias Bob. So this view, I don't know if you see, is in between Nice and Monaco, where I have a little activity. And you see, in Monaco, we have been using the CRISPR's knockout to analyze the glutamine receptor, amino acid, essential amino acid receptor, and the cysteine receptor, transporter. And with the last one, the cysteine transporter. That's why we discovered, that was not our discovery, but we discovered under the microscope the ferroptosis. As you see, it's a massive cell death by explosion, and this is what we are working on. And this is the people in the lab, that the PhD student that are finally on the way, and the very little group where I'm very pleased. And you see the red arrow, that's where we are pleased to do all this center scientific work. And okay, and then I think I close here. I don't know if there is any question, it will be a great pleasure to answer, but during the week, we'll be able to do that. Okay. Thank you very much.
Yeah, thank you, Chuck, for the wonderful talk. So,
hi, Jack. So it's always great to hear from the expert. Yes. So wonderful talk, and I really liked how you started from very basics. So my question is about that synergistic effect which you saw by inhibiting MCT1 and MCT4. So that was a colony formation assay, and I hope that was the cell cytotoxicity to the cancer cells. Yeah. But later on, you explained that can be the change in the tumor microenvironment. Yeah. So what's your comment on that?
Well, this is a good question. This is something we are going to discuss in the meeting. Because here we have an MCT1 inhibitor, great. Not MCT4 yet. The MCT4 is very good not in vivo, in vitro. We have still some problem with the utilization in vivo. But when, I know many companies are going on that, when that inhibitor or similar inhibitor we go, that will be great. Because then we can manipulate it. Right. And then it's much better than to have a drug, because here we can manipulate the two systems, the immune system with the MCT1 inhibitor, and the other one, if we want to be more severe, for stopping the tumor, and then releasing.
Right. And I think for the immune system, did you check which type of immune cells were there? Because sometimes there are MDSCs, sometimes there are TAM, different type of cells, and for those immune cells, we have inhibitors.
Well, for this, perhaps I will could return the question to Marina. Okay. You see, all the immunological system, when it is activated by the parasite, whatever. In this case, then you get a very strong stimulation of the immune cell. And the proliferation of the immune cell to become strong to is because at this point, they use glycolysis, the energy, the quickest, the rapidly. So, of course, if you come to that, the combination of both could be difficult. Blocking but it's manageable, we think, but by work and the future, again, will be to be able to have 2 or 3 independent drugs in order we can. And as I mentioned, for the lactico dehydrogenase, the beauty also is that Genentech has made this compound that is now available, we will discuss it, and block both beautifully and mimic, not toxic, at least in vitro. We haven't done the clinical experiment, all of this.
Right, yeah, I think that is another important aspect to see the toxicity, because effect is one, but the toxicity is another problem. So, yeah, thank you so much.
You have to have that in mind all the time. And this is why, after perhaps 40 years or 50 years of research,
yes, I think it's working.
It has not been possible to get a compound in the clinic with no toxicity.
True. Yes, so,
I have a question.
okay.
Here. So, this side on your left.
Yeah,
yes.
okay.
Thank you for the wonderful talk, sir. I have 2 quick questions. The first is you showed some knockout experiments with the MCT, and you talked about the reduction in the tumor size. So I'm assuming these are primary tumors. Did you look at tumor recurrence and metastatic lesions? Did you observe any phenotype?
Well, we don't know that. We have not explored this aspect of even tumor GCM metastasis. Okay.
All right.
You see, this is all of this could be very important question, but at the same time, we need to have the very important and safe drugs. And this is, in fact, the business for the future and for now and the future.
Sure, thank you. And one last question. So talking about hypoxia makes a lot of sense when you're talking about solid tumors, solid carcinomas. Is anything known about liquid tumors or leukemias and the role of HIF in those scenarios?
Well, the same. Well, in the for the leukemia, if you block with the MCT1, then it goes very well. But the problem in the clinic is that this tumor from the immune system, they now acquire MCT4. So then you need to go. You see, the resistance of this tumor, the lymphoid tumor, was coming from the emergence of MCT4.
Thank you so much.
Right. Thank you for your.
I have one just small curiosity. Yeah, this is regarding the Nature Genetics paper you showed. In the Tibetan population, you have shown the mutation of the PHD2, right?
Yeah.
It's a natural mutation. Of course, that is in the natural mutation, take care of the natural cells, right? Yeah. And when that is the mutation, there is a HIP1 is up.
Well, there is something that I didn't understand at the beginning. On the PHD2, you mean?
When there is a PHD2 mutation,
yeah,
in the Tibetan population,
yeah,
that is naturally HIP1 alpha is up,
yeah,
in these somatic cells, right?
Yeah.
And it is taking care of the hypoxia, low oxygen concentration.
Yeah.
So I want to know that is any study of this particular population regarding the metastasis or cancer.
Right. Yeah, I understand.
So that is it will be just, I feel that is just opposite effect, right?
Yeah. Well, I don't know. I cannot answer. But perhaps you will be participating in the meeting?
Yes, yes.
Yeah, okay. So we have perhaps the time to go and further on this point. But I cannot answer.
Thank you, thank you, thank you.
Hi, sir. Hi, sir. Actually, I have one, yes. I have one question and one doubt. So my doubt is like, if we will inhibit this glycolysis, isn't it like the cancer cells will shift their metabolism towards the amino acids?
Yes.
And there will be more glutamine uptake and there will be more cannibalism and complex cannibalism. And my second question is, if we will inhibit this glycolysis, how the inflammation will be affected? Because it's critical for immune cells migration and their polarity that is changed in that tumor microenvironment.
Well, I don't know, by blocking the glycolysis, of course, you block very strongly the aspect also of the immune reaction and the growth, because they work beautifully with the MCT1, okay, for the glycolysis. But the glycolysis coming also from the MCT4 is very important also to help them to go. It's a combination of both. But what is known from the beginning, the beautiful work of AstraZeneca is that the MCT1 suppress graph on the mice, heterologous mice. So that was showing that indeed, typically, the immune response was affected. And yet, if one could be there, perhaps the other part of the question, I have a problem a little bit here and there, but we could go better.
Thank you, sir.
I'm afraid we are running out of time, but there was one question of the president.
Thank you.
So,
what a fascinating lecture it was by Professor Jacks. One comment is the information that we worked on 2-deoxy-D-glucose, 2DG.
Not good.
No, we worked as a radiosensitizer before you give the radiotherapy to the cancer patients. And we were giving this load of 2DG, and then that sensitizes the cancer cell, because cancer cell takes more of the 2DG as compared to the normal cell. So when you give radiation, we can optimize the intensity of the radiation in such a way it doesn't affect the normal cell, but it kills selectively the cancer cell which has taken more of this, which cannot give ATP through glycolysis. So it's a weaker cell. Then the next thing, we repurposed it for coronavirus during the COVID. We repurposed 2DG because it has the same analogy.
Now, the 2DG, as you know, it's a great molecule, but at the same time has many side effects. As you know, by also blocking is not only the glucose transporter, but he has also on the hexokinase. Initially, we isolate the mutant of the glucose 6-phosphoisomerase by not before the CRISPR, okay, just mutagenesis, okay, and we see beautifully when you stop the isomerase, let's say, okay, then you have a feedback to block the glucose transport. So this is why in the part the DG is doing beautifully. Right. But then you have a problem because then you have a chaperone that comes and kill completely and degrade and bring to autophagy the glucose transporter. That's it. But anyway, 2DG is it's a good drug, but to some extent you have to know what you do and what you want to answer. Okay.
Thank you. Thank you.
Thank you very much. I think there are a lot more questions, but we could discuss them in the coffee break probably. So we move on to the next speaker. So it's my pleasure to announce Fatima Balthazar. She's an associate professor of pharmacology at the School of Medicine in Minho, Portugal. So Fatima is well known for her research interest in cancer glucose metabolism. She published many papers on the prognostic impact of MCTs. And Fatima, we are looking forward to your talk.
Thank you, Professor Jacques, for such an enlightening talk. Now I request Professor Silva Murthy, sir, Professor Vineet Kumar, and our session chair to kindly facilitate the keynote speaker.
Okay, so good morning to everyone. First of all, I would like to acknowledge all this very nice reception. As Marina said, we are listed, I'm also listed as a co-organizer, but actually Dr. Vinit Kumar and his team did all the work. So basically we just helped a bit with the program. I'm glad I could come to India. It has been so far a very enjoyable experience, and it's much better to be here in person than just attending from online. So. With this beautiful talk of Jacques Puissigure, he just made my life much easier because I'm going to talk about our contribution to the field of MCTs in cancer. So I come, let's see, if I can make this work. I come from Portugal, from Braga, where the University of Minho is located, from the School of Medicine and its associated institute, which is ICVS. So as a summary of my talk, I will talk a bit, just a short bit, because Jacques has already introduced this subject, about the role of glycolytic metabolism in cancer aggressiveness, and also it is also associated with resistance to therapy. And then mainly focus on the role of monocarboxylate transporters, which are also lactate transporters, in the maintenance of this glycolytic metabolism. Also some work that has been going on about their prognostic value, especially in patient survival. And also some work that we have been doing in different kinds of tumors, different types of tumors, in exploiting MCTs as targets for cancer therapy. That Jacques said already, it's a bit of a difficult job because we have redundancy among the MCTs, especially MCT1 and MCT4. So basically, I'm going to concentrate, as you know, several pathways are upregulated in the cancer cells when we compare with the normal cells, including amino acid metabolism, fatty acid metabolism. But we have been concentrating on the glycolytic metabolism, where MCTs play a role. So Again, Jacques talked already a bit about Otto Warburg that actually started this very nice work. He actually identified or described for the first time this preference that cancer cells have for the glycolytic metabolism, consuming lots of glucose and producing lactate even in the presence of oxygen, which doesn't happen with the normal cells. So basically, cancer cells, and not just cancer cells, also Jacques also mentioned about the immune cells, some proliferating tissues, even some endothelial cells, they actually have a preference for this kind of metabolism in which they take up a huge amount of glucose, and they deviate the pyruvate produced by glycolysis into the synthesis of lactate. So this was already mentioned before that only through glycolysis cells only produce 2 molecules of ATP instead of the 36 molecules of ATP produced by the mitochondria. So why do cancer cells adopt this kind of metabolism? This was also a bit mentioned already before. One of the reasons that was also mentioned by Jacques is the fast production of ATP. So even though it's 2 molecules of ATP, this pathway is upregulated, and cancer cells actually don't produce less ATP than normal cells. They can even produce more ATP. And another important point is that they deviate some of the intermediates of the glycolytic pathway into the anabolic reactions, so they help cells to proliferate. And another aspect of this phenotype, this metabolic phenotype, is the effect they have on the tumor microenvironment. So this accumulation of lactate and protons in the tumor microenvironment actually affects other cells, as it was also already mentioned, namely fibroblasts, endothelial cells, immune cells. All of them are affected by this metabolism adopted by cancer cells. So you have here some examples of cells that are affected by this glycolytic phenotype: immune cells, endothelial cells, fibroblasts, induction of degradation of the extracellular matrix, etc. So all of them will induce all these effects of this in the tumor microenvironment, will induce tumor growth. It will stimulate metastasis. It's associated with chemoresistance and also survival of the cancer cells. So this was already mentioned before, also that the cancer cells have to cope with this metabolic phenotype in terms of pH. So there are several molecules several transporters, several molecules that are located at the plasma membrane, which actually help cancer cells to regulate the pH. So they live happily in this acidic pH. So these pH regulators, when they are active, this increased activity is actually associated with increased cancer progression, cell migration, invasion, and resistance to treatments. So basically, in theory, when we inhibit the pH regulators, we will actually affect all these activities. Here we have identified these pH regulators and also some inhibitors which are already in the clinics, which are here in red. This one I will talk a bit more about because it's the inhibitor of MCT1. So basically, part of our work at my group has been concentrated on MCTs, which actually play a dual role in the cancer cells. On one side, because they are protein importers, They help in the pH regulation, and on the other hand, they are really crucial for the maintenance of this glycolytic phenotype because they put the lactate outside. Okay, they transport the lactate outside the cancer cells. So we know MCTs already for a long time. I think they were characterized about the biochemical part about 30 years ago. And we know that they are, by sequence homology, we know that there are 14 members of MCTs. However, they don't share the same substrates. And actually only the MCT1, 2, 3, and 4 are the true monocarboxylate transporters. And besides lactate, they also transport pyruvate, they transport ketone bodies, and also other drugs, some drugs for which they have affinity. So the most important isoforms in cancer are MCT1 and MCT4. MCT1, in terms of affinity, it's characterized by having an intermediate affinity. It's both adapted for efflux and uptake of lactate, depending on the concentration of the substrate, as well as the concentration of protons. It's more expressed in our body in different tissues. It has more an ubiquitous expression, while MCT4 is a low affinity transporter, which means that it works for higher concentrations of the substrates. It's more associated especially in normal cells with efflux of lactate, and it's mostly expressed in normal tissues, in tissues that perform more glycolysis. Importantly, in order to be expressed as the plasma membrane and work as transporters, they need to be associated with protein chaperones, which in the case of MCT1 and MCT4 is known as CD147 or BASI gene. So it's another way to target MCTs, is also to target the chaperone. So we and others have been studying the expression of MCTs in several human cancers. When I became interested in the MCTs, first of all, because I wanted to target them for cancer therapy, it would be important at least to know if MCTs were upregulated in cancer cells compared to normal tissues, so we wouldn't be, the inhibitors wouldn't be so toxic. So we have been studying the expression of MCT1, MCT4, also MCT2 in several types of cancer, not just our group, but also other groups. And in many tumors, we found upregulation of MCT1 and MCT4 in cancer cells compared to normal cells. In some of the reports, we actually only have positivity. For example, in this case, it was reported that there was positivity for MCT1 and MCT4, but there was actually no comparison with the normal tissue. That's why we could not say it was upregulated. They were upregulated. Nowadays, we live in the area of biomarkers. We like to explore some molecules as biomarkers. They can be biomarkers, for example, of survival, but they can also be biomarkers of therapy response. In this line of thought, we have looked at in different publications. We have looked at the prognostic value of MCTs in cancer, especially in the survival probability of the patients, by comparing the expression levels of these MCTs over time. This is one of the work. Of course, there are many publications already about this. In this work, we actually looked at different databases in which we could get access to the expression of MCT1, but actually these databases have data about mRNA expression and not protein. And that sometimes may be a problem because the MCTs have post-translational modifications, and sometimes the expression, the mRNA expression, does not go in line with the protein expression. But even though we have evidence, this was in glioblastoma, which is a very aggressive brain cancer, and we actually have some data on the expression that I'll show in a minute. The protein expression in glioblastoma compared to normal tissues and normal cells. But here we went to the databases and tried to find also some evidence for MCT1 as a prognostic biomarker of survival. In the several databases, in the different ones, we actually found that patients which have upregulation, cancer samples that have upregulation of MCT1, or these patients live actually less than patients which have lower expression of MCT1. And then we did this combined analysis showing that actually MCT1, at least in terms of mRNA expression, has a prognostic value in glioblastoma. More recently, we decided to do a systematic review on the prognostic value of, again, MCT1 in cancer in general, but just looking at human samples and immunoexpression, so the expression of the protein itself. We used these keywords, we looked for different databases. And then from the first 731 studies that we found, and then we had some criteria for inclusion and exclusion of the work, and we found some in the end some 39 eligible studies in which they actually studied what we wanted to find out. We did an analysis of the quality of these studies. Most of them were of high quality. Some of them, it doesn't mean that the study doesn't have scientific quality. It just means sometimes that the authors, this is actually a good experience to do some systematic reviews, because then we realize what we should say in the papers, in the articles. Some of them are not high quality or qualified as high quality because the authors didn't report all the data that they were supposed to. I mean, they should have reported. And then just to summarize what we found that MCT1 overexpression, this is protein expression, was an indicator of poor prognosis in 16 types of malignancies. I just listed some of them here. GIST, which is gastrointestinal stromal tumors, gastric, bladder, breast, prostate, head and neck, etc. But on the other hand, sometimes we found some contradictory studies which shows the other way around. So in colorectal carcinoma and PDAC and non-small cell carcinoma, we actually found studies that reported that MCT1 overexpression was correlated with with better outcomes, the other way around than the other studies. So in the end, we just concluded that in order to, even though we found this evidence, we felt that we still need larger cohorts of patients in order to make a stronger point for MCT1 as a prognostic biomarker. And now just showing you a bit what we have been doing in terms of MCTs as targets for cancer therapy. We have been studying different kinds of cancers, but one of our favorites, let's say, favorite models is glioblastoma. That's the one I'm going to show you. So as Jacques said, we have now, so for many years we didn't have specific MCT inhibitors. We had some ancient ones were not so specific for MCTs, and sometimes not isoform specific inside the MCTs. And some years ago, we had this MCT1 inhibitor developed by AstraZeneca, which was actually developed, these MCT-specific inhibitors were designed to increase the time of survival of transplants, and not in the cancer field. But then they decided to start to use these MCT-specific inhibitors in the cancer field. And actually, this AstraZeneca inhibitor, this 3965, went to 2 clinical trials, which have finished phase 1/phase 2 clinical trials, which have finished very recently. But of course, they want to carry on the clinical studies. Of course, there was some toxicity reported, actually, about the retina, some eye problems that they reported to be reversible. So they want to carry on with the studies. So I'm going to show you some work in glioblastoma that we have been developed. Actually, this was work done by a PhD student, Vera, who is not in my lab anymore, in collaboration with my colleague Rui Reis, who has been interested in glioblastoma for many years. So about 10 years ago, we decided to study the expression of MCT1, MCT4, and the chaperone in a series of brain tumors, including glioblastomas. We have low-grade tumors, high-grade, low-grade, high-grade tumors, and we also had access to non-tumoral tissue. So in the whole, we found that even though we were probably expecting a different result, as we knew that MCT4 would be more associated with a glycolytic phenotype, and we know glioblastoma is very much glycolytic, we found in our cases, of course, with our antibodies, that the upregulation of, in terms of MCTs, it was stronger for MCT1 and the chaperone rather than MCT4. So this is MCT1 in black, and the chaperone here on this side. So we did some in vitro experiments. We screened some cell lines. We found some cell lines which were more sensitive to, in this case, we used CHC, which is a classic MCT inhibitor, not so specific. And then we decided to choose one cell line which was more sensitive to the inhibitor, one cell line that was less sensitive to the inhibitor. And then we characterized the activity in terms of viability, proliferation, also migration, invasion, interference with the glycolytic metabolism in terms of glucose consumption, lactate production, and of course the most sensitive cell line responded better than the other one. We also see some induction of cell death, which is not so common, as Jacques said. Usually we see an inhibition of the capacity of the cells to proliferate, and not so much induced cell death. And because this inhibitor was not so specific, we also did downregulation of the gene of MCT1 by siRNA. We actually confirmed the results of this inhibition by CHC. CHC can also inhibit MCT4, but with the concentrations that we were using, we were convinced that we were inhibiting mostly MCT1, and then we could repeat the results. Then, in line of what we were discussing like previously about the toxicity of these compounds, we decided to look if there would be some interest in combining the MCT1 inhibitors or the MCT1 inhibition with, in this case, chemotherapy that is used in glioblastoma, which is temozolamides. So in this way, we could reduce the doses of chemotherapy. This is actually a chemotherapy agent that has been around for many years in the treatment of glioblastoma, and we still use it nowadays. And either with the short epin RNA with for MCT1 or with an MCT1 specific inhibitor, also from AstraZeneca, we actually see a significant reduction in terms of EC50 or IC50 of of temozolamides. So, which means that if we combine MCT1 inhibition with temozolomide, we can reduce the doses of temozolomide, and of course reduces the side effects related to toxicity. Then we decided to go into the in vivo model in order to test these results that we had in vitro. And in collaboration with my colleague from our lab, we actually implemented an orthotopic model of GBM. And our first results comparing parental cell line with a cell line in which we did short epin for MCT1, we saw that the survival of the mice increased quite a lot. Here we have the histology of the tumors, in which we see smaller tumors when we excise the brains of the mice, and then we see lower proliferation by using the Ki67 marker of proliferation. Then we did the combination also with temozolamides. So I don't have here the intermediate graphs, but basically when we use the treatment with temozolomide, we see an increase in mice survival when we compared with this black line above. And then when we do the combination of temozolomide plus MCT1 inhibition, the increase in the survival of the mice is really huge. In the end, in most of the mice, we didn't see any tumor anymore in the brains of the mice. And we actually stopped the experiment at 200 days, and some of the animals were perfectly fine. Just to finish, and we must not forget that our targets, it's not only the cancer cells. We know that the cancer, a solid tumor, a malignant tumor is not only composed by cancer cells. We know that the other cells in the microenvironment are very important. So what we did, we try to see what would be the outcome when we inhibit MCT1 in the pair MCT1 and MCT4. I'll show you. We actually try to investigate the crosstalk or the role of MCTs in the crosstalk between a glioma cell line and endothelial cell line. It was actually a brain endothelial cell line. So just a summary of what we did. We exposed endothelial cells, these brain endothelial cells, to glioma cells conditioned medium, and then saw what it did in terms of cell proliferation, migration, and induction of angiogenesis. We actually saw stimulation as we were expecting. Then, to try to investigate the role of MCTs in the cancer cell, we had to block, because this cancer cell had both MCT1 and MCT4, we had to block both MCTs. And then when we give the conditioned medium to the endothelial cells, we see a decrease in all these parameters, cell proliferation, migration, and angiogenesis. And then what we did on the other way around, so here we blocked the two MCTs by the same methodology, siRNA. On the other hand, on the endothelial cells, because they did not express, or we didn't see any expression of MCT4, it was enough to inhibit MCT1. we did inhibition with siRNA and also with the inhibitor of MCT1. So in both ways, we saw a decrease in cell proliferation and angiogenesis. So it means that MCT1, in this case, was very important in this crosstalk in putting lactate outside from the cancer cells and uptaking the lactate into the endothelial cells. So to finish my presentation, I think I showed you some evidence that glycolytic metabolism has an important role in cancer aggressiveness. We and others that there's actually an upregulation of MCTs in cancer, and they may have a prognostic value. MCTs, and of course, not just MCTs, but the chaperone. We actually have done some work together with Jack in which we target the chaperone. It's also a good way because if we target the BASI gene, we will interfere with the activity of MCT1 and MCT4. They can be explored for cancer therapy. Of course, in the different cancers, we see a variety of expression of MCTs. So our approach has to be different concerning regarding the cancer type that we are addressing. And also, of course, we have to be aware that any inhibitor that we use in the clinics will affect also normal cells, will affect the other cells of the microenvironment. Thank you very much for your attention. If you have any questions, I'll be happy to answer if I know. Thank you.
So thank you very much for the presentation. The talk is open for discussion. Yeah, over there.
Yeah, hi, it was a very nice talk. I was just wondering, just before Professor Jacks told off that when MCT1 and 2 both are inhibited, the cells do not survive, the cancer cells. So I was wondering, did you see the same? Because in your conditioned experiment, you took the conditioned media from, both inhibitor treated. So what was your observation there?
You mean what was the effect on inhibiting both MCTs in the cancer cells?
Yes, exactly.
At the time frame we used, they were not dying. Actually, they may adapt. They are flexible in terms of metabolism. What we saw actually in the collaboration with Jacques when they did the knockout of CD147, actually the cancer cells in this case were lung cancer cells. They switched into oxidative phosphorylation. So they might have this flexibility some of these cells have. So.
Yeah, it could be tumor specific as well, because cell to cell, like tumor cell differs in the way they behave. So it could be that as well. It could be that because tumor cells behave differently. So the cells that he used and the cells that you used, they are behaving differently, and maybe the concentration is.
Yeah, it depends also on the flexibility of the metabolic flexibility that they have to use other sources of energy or to proliferate. Yeah,
thank you.
Thank you.
So, dear participants, I have a small announcement because we are running late. So, could it be possible we can take 2 questions right now, and later we can discuss during the interactive session as well in the lunchtime. So, one more question if we can take, or
I think we discussed this subject quite a lot already.
Yeah, we can discuss later on.
Hello, ma'am. Hello. You have a nice talk. But I have one more question. As I'm working with tumor microenvironment, there are a lot amount of cells. There is a niche of a cell population present in the tumor microenvironment. Not only the cancer cell, cancer stem cells, different TAMs that we know because they are playing very major role and significant role in relapse of cancer. So did you have tested this thing again with all those immune cells that are working against our own system?
Yeah, we have some work going on in TAMS actually. But we are modulating the MCT expression to see the switch of terms from pro-tumoral to anti-tumoral, and that happens. But of course, we have to see the inhibition in the whole context, and we have to understand then in vivo how the inhibitors behave, what they do to all these cells, because this is quite complex. We cannot just concentrate on cancer cells.
Because for any drug to work effectively, you have to target all the cells that are present in this niche. So one can say that this drug is effective along with when it is targeting all these cells. That's why this question was that along with your cancer cell, it is also inhibiting this environment cells. So one should get a better in-depth research with the microenvironment thing. Then only one drug can
the
be.
inhibitors will act on the MCTs. I mean, this specific inhibitor of MCT1 will act on the endothelial cells, on the immune cells, on the cancer cells. So we really have to see. We hope by having this disruption of this crosstalk that exists between the cancer cells and the other cells of the microenvironment, that in the end, the tumor will become smaller and will disappear, like hopefully, but it's quite complex, and we really have to have good models to study that.
Thank you,
for your questions and observation.
So thank you very much, participants, to make the session so interactive. I know participants have a couple of questions, and I also have not the questions, few queries, my doubts I want to clear, but I will discuss later. So right now,
Thank you, Dr. Fatima. Thank you for enlightening us with the talk. I request the session chairs and Professor Vineet Kumar to please present our token of appreciation to Dr. Fatima. And Professor Biswas to please join. Professor Fatima, please. Please give a big round of applause. This is just a small token of appreciation from us.
So now is the time for the next speaker. Our next speaker is Dr. Frederick Bost. He is a research director and team leader at INSERM, Nice, France. He received several awards, postdoctoral fellowship from San Diego, USA. His main research work is on the anti-tumoral and anti-metastatic effect of metformin in cancer cells. So he has published several papers, and he is the editor of several journals, and he is the expert for European Union Horizon 2020. So now I invite Dr. Frederick to deliver a talk.
Thank you very much. I'd like to thank the organizing committee for inviting me in this beautiful country, India. It's a great pleasure to be here for the first time, and we have quite an exciting program for this meeting. So thank you, Vineet, for this invitation, and congratulations for this great program.
So today I'm going, as it's mentioned on the title, I'm going to tell you a tale about biguanide. And as it's always the case, a tale starts with once upon a time. So once upon a time, there were one drug, metformin. Thank you. And metformin is a drug that is prescribed to more than 100,000 people in the world for the treatment of diabetes. Metformin was initially isolated from a plant that is called Galega officinalis, also called French lilac. In the Middle Age, this plant was given to people that were suffering from diabetes, and that's only in the 50s that a French medical doctor decided to isolate this molecule that belongs to the biguanide family and give it to patients with diabetes. So what are the action of metformin as an anti-diabetic? First of all, metformin acts on insulin-sensitive organs. It acts on the liver by reducing glucose production. It acts on adipose tissue where it increases glucose transport and decreases lipolysis. But it also acts on muscles by increasing fatty acid oxidation and increasing glucose transport. And all these effects leads to a decrease of hyperinsulinemia and, of course, consequently, a decrease of insulinemia. But so far, so good. And the life of metformin changed in 2005 when a study by the group of Josie Evans in Scotland showed in a large cohort of Scottish patients that with more than 10,000 patients, when you treat this, it was a retrospective epidemiological studies, and what Josie Evans found is that diabetic patients that were treated with metformin had a reduced risk of cancer. Since this pioneering work, several other retrospective studies were done in several cancers, and most of them concluded the same effect. Therefore, these studies offered a new perspective for these old anti-diabetic drugs. And at that time in the lab, we were working with Issam Ben Sarah, a former student of the lab, on prostate cancer. And we decided to apply metformin to different prostate cancer cell lines with different status that were androgen sensitive or androgen resistant. And as you can see here, we observed that when we had metformin to these cells, we have a decrease of cell proliferation. We also did experiments in animals, and we treated these animals with metformin. As you can see here in blue, we have a decrease of tumor growth in animals treated with metformin. Since this work, several other laboratories decided to study the effect of metformin in different cancers, and they found similar results in colon, breast, lung, pancreas, glioblastoma, melanoma, but also in hematological cancers. With Beatrice Dirat, who did a postdoctoral fellowship in the lab, we also studied the effect of metformin on metastasis. We took the most aggressive prostate cancer cell lines, the PC3 cell lines, and we treated them with metformin, looking after 4 hours of treatment at the number of cells that have migrated in Boyden chamber. And as you can see here, we have a significant decrease of cancer cell migration. We also perform orthotopic injection of PC3 cells that express GFP in the prostate. So we injected the cells in the prostate and look at the formation of metastasis in different organs. And as you can see here, we have a decrease of the average number of metastases per animal when we treat the cells with metformin. And here we used as a control docetaxel, which is a chemotherapy used for the treatment of prostate cancers. Several studies showed that it also the case for melanoma ovary, lung metastasis, where it can be, where there was an effect. So we then asked, what are the cellular mechanisms implicated in metformin action? And first, we looked at the direct effect of metformin on cancer cells. So here I summarize a lot of publications that were done by several groups, showing that depending on cancer cells, metformin can have different effects. In some cells, it has been shown that it stops proliferation by inducing cell cycle arrest and autophagy. And this is the case for prostate cancer cells, myeloma, osteosarcoma. But it has also been shown that in some cancer models, such as breast, pancreas, and colon, it directly induces apoptosis. Another important study caught our attention when we were studying the effect of metformin. And this study was published in 2000 by the laboratory of Xavier Leverbe in France that was working on hepatocytes. What Xavier Leverbe showed is that metformin inhibits the respiratory complex 1 of the mitochondrial chain. So we decided to look at the effect of metformin on cancer metabolism. So there's no need to mention something that has been repeated and very nicely presented by Jacques and Fatima. Cancer cells have a different metabolism compared to normal cells. They use aerobic glycolysis to produce ATP and lactate, but they are also able to use mitochondrial metabolism and oxidative phosphorylation to generate metabolites, cofactors, and ATP that are necessary for proliferation and metastasis. Like it was mentioned previously, of course, cancer cells are in microenvironment. This microenvironment is changing, so they must adapt, and they must have a flexibility to adapt their metabolism to this environment. So, pointing on this slide, you can see that oxidative phosphorylation is important also for cancer proliferation and metastasis. So following the work of Xavier Leverbe, we looked at mitochondrial metabolism in our cancer cells treated with metformin. And what we observed is that metformin was also able to inhibit complex 1 activity and OXPHOS in prostate cancer cells. And this led to a decrease of ATP concentration in these cells. Since these works showing that metformin can act on cancer metabolism, several other laboratories, such as the one of Navdeem Chamdel or the one of Matt van der Eyden, demonstrated that indeed the antitumoral effects of metformin could be mediated by its effect on mitochondrial metabolism, leading to the notion that inhibition of mitochondrial metabolism can inhibit tumor proliferation and progression. So we saw the direct effect of metformin, but what you need to know also is that several hypotheses argue also that metformin could act indirectly on cancer cells. Let's go back on this slide showing the anti-diabetic action of metformin. As I told you, this action of metformin decreases hyperglycemia and insulinemia. And insulin is a growth factor. So we can imagine that the decrease of insulinemia may slow down tumor cell proliferation. However, this aspect is very difficult to demonstrate, and we still don't have a clear demonstration that metformin could act through this effect to inhibit tumor growth like we see in our animal models. There are also indirect effects that are reported for metformin. Fatima talked about this, the importance of tumor microenvironment, and it has been shown that metformin can act on immune cells and promote anti-tumoral response on immune cells, but it also acts on inflammation by inducing anti-inflammatory effects. So here is a sum up of all the actions, the indirect action on the tumor microenvironment, on the insulin sensitive organ, the direct action on cancer cells, effects on proliferation, migration, metastasis, and the action on energy metabolism that is induced by metformin. So all these effects could argue to the fact that metformin could be a good drug with anti-tumoral effects. And several laboratories in the world started to do clinical trials with this drug that is easily available and easy to prescribe by doctors. So if you look at clinicaltrial.gov, today maybe there's more clinical trial, and if you enter metformin and cancer, you will find that there's more than 400 clinical trials ongoing, trying to show if metformin is suitable for cancer treatment. But few of them are published. There's about 20 clinical trials. So I'm not going to review all these clinical trials and just summarize two of them. One that was successful and published in JAMA Oncology in 2019 on lung cancer, and showing that there's a benefit of treating patients with TKI inhibitor in combination of metformin. We didn't have that luck with our clinical trial in prostate cancer, the French clinical trial called Taxomet, where we combine metformin and docetaxel, the chemotherapy. We were a little bit disappointed, but it's important to know here that we were dealing with a very advanced stage of prostate cancer. And so that's why we maybe didn't get the expected results. So if all these clinical trials have mixed of outcome, it's also because maybe of some issues that we have with metformin. To act on cells, metformin requires transporters to enter the cells, and that's the main problem. But also, all our studies were done with high concentration of metformin in vitro and in animal models. So we decided, and this is unpublished results that were obtained by Abigail Mazou, an engineer in our lab, we decided to collaborate with Stéphane Rocky, who has developed with chemists biguanide derivatives that can work in the micromolar range instead of the millimolar range that we are using with metformin. This compound, the CRO15, was shown to be 1,000 more active than metformin in melanoma and has a better bioavailability. So we asked the question, what about the effect of CRO15 in prostate cancer, the pathology we're working with? And what we showed is that when we treat PC3 cells, human prostate cancer cells, with micromolar concentration of CRO15, we strongly decrease cell numbers, cell proliferation, compared to metformin at 5 millimolars. We also induced at 20 micromolar a strong decrease of viability, and similarly, we observed a decrease of cell migration after 6 hours with 20 micromolar of CRO15. We also looked at the effect of CRO15 on apoptosis using annexin 5-PI assay. And as you can see here, we have an increase of early and late apoptosis when we treat PC3 cells with 20 micromolar of CRO15. As I told you previously, metformin acts on inhibits the complex one of the mitochondria. This leads to a decrease of ATP and induce an energy stress in the cells. Then we ask whether or not CRO15 or biguanide derivative will affect metabolism of cancer cells. So we did this horse experiment that measure oxygen consumption rate. And as you can see here in red, we have a decrease of oxygen consumption rate when we treat our cells with metformin, CRO15, but also, yes, with metformin is in green. We looked at complex 1 activity, and once again, in red, when we treat the cells with CRO15, we have a decrease of complex 1 activity. So similarly to metformin, but at lower concentration, CRO15 is able to target and to inhibit mitochondrial metabolism. To go further, we perform steady-state metabolomic in collaboration with Issam Ben Sarah, and we noticed that we have a decrease of several intermediates of the TCA cycle, such as aconitate, alpha-ketoglutarate, and citrate in this steady-state experiment when we treat our cells with CRO15. So yes, CRO15 induces apoptosis in prostate cancer cells. It inhibits mitochondrial metabolism, and it induces apoptosis. But what was surprising in our steady-state metabolomics is that we also showed that CRO15, unlike metformin, targets pyrimidine synthesis. As you can see here, we have a decrease of L-carbamyl L-aspartate and dihydroorotate, two major intermediates of de novo synthesis of pyrimidine. But what was also very interesting is if we look at the key enzyme of this pathway, we also see that at early stages, starting at 6 hours, we have a decrease of CAD expression, and after at 24 hours, other enzymes such as UMPS and PRPS2. While at the same time, metformin did not affect the expression of these enzymes. So, as I told you, CRO15 has a strong action with lower concentration. And if we compare the two molecules, CRO15 induces apoptosis, metformin not always. CRO15 and metformin affects mitochondrial metabolism. CRO15 affects pyrimidine synthesis, but not metformin, and we can use CRO15 at much lower concentration than metformin. Is CRO15 more efficient than metformin in vivo? We don't know yet, and the results of this experiment will probably lead to the decision of whether or not we can start clinical trials. So I'd like to thank the member of the teams, and Nathalie Mazur, who is present here, will speak this afternoon. I'd like to thank our collaborators and our financial support. And I also would like to invite you to our Metabolism and Cancer symposium that will be in November in Nice, France. So we are here close to the Mediterranean Sea. We have a very nice program. So you are welcome to come in Nice in November. Thank you very much.
So again, thank you. We have time for 2 questions, and we decided to
am I audible to you?
Questions.
It was a very nice talk. I have a very basic and simple question. As you're showing, metformin is decreasing the proliferation of cancer cells. Did you happen to check its effect on normal cells as well? Because I feel metformin is a very common drug. Okay, am I audible?
Yeah.
Okay, as it was a very nice talk, by the way. I have a very basic question. You are showing that metformin is affecting the proliferation of cancer cells. Did you happen to check its effect on normal cells? Because metformin is a very common drug used by all the diabetic patients. So what is its effect on the, yeah.
So normal epithelial prostate cells, and we didn't see any effect. Besides, when we treat mice with metformin, they are perfectly healthy, and there's no effect on these mice. It's important to notice that metformin is really very safe in most of cases on animals and even in humans. If you don't have diabetes, you can take metformin. It won't decrease your glycemia. It only acts on hyperglycemia. Okay, so there's one risk to use metformin is when you have a problem with your kidney and you have insufficient kidneys, because it can, in this case, leads to lactic acidosis. But it's one patient out of 10,000. So it's really a very safe drug that we're using since more than 50 years now. So, but it didn't do any effect on normal cell proliferation and
but I think you showed in one slide it's affecting cell cycle of cancer cells.
Yes.
So why not on normal cells? Why only cancer cells?
Why it does not affect
normal cells?
Well, probably because they don't have the same metabolism than the cancer cell that we are using, and they are not affected by metformin.
So you feel it's safe to use,
Oh,
and
yes.
it is
Metformin,
not having
yes,
any
it's
effect
safe.
on normal cells.
Whether or not it will have an anti-tumoral effect in patients is another story, but it's safe to use it. Metformin.
Okay. Thank you very much.
You're welcome.
Yeah, I have, in continuation of these studies, what my other colleague asked. So what are the actual adverse effects that were seen in the animals when you checked it with the metformin and the CRO15, the drug that you looked at?
What are
adverse effects in the animals? What were the side effects of the drug in the animals?
Sorry.
You can't hear?
No, I don't hear you very well.
What are the adverse effects of these drugs seen?
The side effects.
Side effects.
Okay, the side effects. Okay, so as I told you, for metformin, the side effects are lactic acidosis. For CRO15, so far, our collaborators tried to, treated mice with CRO15, and they didn't notice any side effect. But of course, this was mice, so it's not studied yet in humans.
Did you check the dose at what level these drugs are safe?
Yes, with CRO15, we are lucky to work with much lower dose. Even in animals, we treated the mice with a lower dose of CRO15. Our collaborators treated the mice with a lower dose of CRO15, and they didn't see any toxicity, hepatic toxicity, or any effect on glycemia, also basal glycemia, because that was one of the concerns, because metformin is supposed to affect hyperglycemia. So far, so good. But
usually in the acute toxicity studies, you go up to at least 400 mg per kg body weight. Did you any test of these things? Actually?
No, we did not.
You did not. Thank you.
So,
Hi, sir.
sorry, but we have only time.
We can discuss after.
Okay, we have to discuss during lunchtime, and we decided to move the next talk of Dr. Sarin after, and we will hear it after the lunch break, and now have a lunch break. Yeah.
Enjoy your lunch.
before-
Enjoy your lunch, and then we will discuss.
Before we break for lunch, I would request the session chairs and Professor Bishwas and Professor Vineet Kumar to please present a token of appreciation to Dr. Frederick. Please give a big round of applause. I take this opportunity to thank the session chairs, Dr. Marina Kurtz and Dr. Reshma. Thank you so much. And as just announced, we now break for lunch. We'll have a lunch break from 1:30 to 2, half an hour. So we'll assemble at 2, and we'll have to wait to hear from Dr. Sareen, who has joined us from INSTEM India. So that talk has been moved to next session. So student volunteers will be there to take you to Wall Street, where the lunch has been arranged. So please make sure that we have a lunch break of half an hour and we assemble back at 2 p.m.
Okay, so I'm sorry for this delay, and I'm sorry to Dr. Sareen, we need to shift your talk. So please proceed for lunch session. So I invite session chairs to start the session, please.
So now I invite Dr. Professor Apurva Sareen. She is distinguished scientist in INSTEM Bangalore. She also served in ISC Bangalore and NCVC TIFR. She is currently associated with Institute of Stem Cell Sciences and Regenerative Medicine, INSTEM, and her research area focused on cellular homeostasis, metabolic regulation of cell fate in immune system. She is recipient of several awards like International Senior Research Fellowship in Biomedical Sciences in India. She is awardee of Wellcome Trust, Swan Jayanti Fellowship in Biological Sciences, and the list is too long. I am not able to read the all awards in her credits. So now I invite Apurva Sareen. She will deliver the talk on metabolic regulation of spatial architecture of signaling cascades. So over to you, Dr. Apurva Sareen.
Thank you very much indeed. And I'd like to begin by, is there an echo? Yeah. I'd like to begin by, first of all, thanking the organizers, particularly Vineet, for the invitation to participate here. This is an audience which is quite actually a little different from the one where I normally present my work at. So it's wonderful to be able to speak to you about this. As the title of my talk indicates, is the echo only for me? As the title of my talk indicates, we're going to be, towards the second part of my talk, look at the integration of metabolism and signaling. And I'll show you a little bit of data on how changing or tweaking the metabolic environment of a cell can indeed give rise to adaptations which are brought about by signaling pathways. And the pathway I'm going to focus on today is the Notch pathway, which my laboratory has been studying for several years. So just as a brief background, I mean, signaling is something we've all encountered in almost any aspect of biology that we work at. And one can see it in very sort of gross, obvious forms, gross in the explicit, obvious forms during, let's say, the transition, during metamorphosis, in organisms as distant from us as dictyostelium, Drosophila, of course, and then at a very much finer level, at the single cell level, an area that my laboratory has studied much more in the context of the T cell lineage. But the point of all of this is to say that we know that these cascades are highly orchestrated, highly coordinated, and must therefore be regulated and responsive for these very complex outcomes that we see, especially given the fact that we have a relatively small number of signaling nodes that are known to us. The question that has always been addressed and is revealed by much of the work that is done in this domain is how do you get so many outcomes and such a broad range of outcomes from a fairly small and limited set of signaling molecules. So this is just a summary to show the sort of the different mechanisms that that have been described in the literature. And the one I want to focus on today is the spatial localization of signaling components, illustrated here in the JNK pathway, published extensively in the RAS pathway as well as in ERK amongst others. As I said, though, at the beginning, that we look at the Notch pathway for today. This is a molecule that was described first in a screen that was done by Jani Nusslein-Walhat and her colleagues, where the loss of the gene resulted in this notch in the wing, which is how Drosophila biologists name genes, and that's how the gene has got its name. We know since then that this is a family of transmembrane receptors illustrated here, which function in response to ligand. And what is unusual about this pathway, and I'd like you to keep it in mind, is that the core pathway is actually extremely simple. The components are very few, and therefore it is quite remarkable when one looks at the wide range of outcomes that Notch has effects on. So the core pathway is initiated by the interaction of the receptor with the ligand, which results in an intramembrane proteolytic event, which causes the release of what is called the Notch intracellular domain, which is typically the signaling component that is studied. This has very well-defined functions in the nucleus. And for the longest time, these were largely transcriptional. Much of what I will tell you today is not to do with the transcriptional functions of the Notch intracellular domain. We also know today that there are several Notch receptors in mammals. There are 4 known, and there are several ligands as well. And the fact that we have multiple Notch receptors is also meaningful for what I'm going to tell you today. I felt that I should mention here that apart from its many roles in development, homeostasis, proliferation, it is not surprising that Notch is also implicated in many cancers. And of course, there have been attempts to manipulate and use Notch as a therapeutic target, none with great success thus far. But there is some excellent work and reviews that I've tried to list here for those who might be interested in looking more closely at the literature. So our interest in Notch began because we were interested broadly in the process of homeostasis and in trying to understand how signaling nodes engaged with molecules that trigger and are well understood to have well established roles in the context of death. And I'm sorry this movie is not going to play for a technical reason, but really what the experiment itself was really simple. It adapted and has been used by many laboratories across the world. In green in this cell over here, you're seeing the expression of the protein BAX, which works at the mitochondria and is a pro-apoptotic protein tagged to the fluorescent protein GFP, green fluorescent protein. Therefore, you see green. The red intricate network is that of mitochondria, which has been marked with the dye MitoDS red. Now, if I could show you the movie, which I cannot, but I can tell you about this later, you can trigger these cells in about an hour to undergo the process of or trigger apoptosis in these cells. And when you do that, if you focus on this particular image here, what you get are cells where mitochondria are completely disrupted. The nucleus, which is shown here in blue, is fragmented, and these are all classic features of the apoptotic pathway. Of interest to us in the screen that we were performing in cells that were overexpressing the Notch intracellular domain, in this case it was Notch1, we found that mitochondrial integrity was preserved. The nucleus, as you can see in this pale shade of blue, looked just fine. And that is what began our initial interest in trying to understand how Notch brought this about. And again, in data that is derived from slightly different assays, what I'm showing you here is that this beautifully sort of network view of mitochondria of healthy cells which is broken up into little fragments in dying cells in this particular model. This fragmentation was also arrested in cells which were already had active notch in them. So this was, a part of a body of data which gave us a sense of excitement about the possibilities of understanding how notch functions in diverse contexts. It also is sort of allows me to show you the assay that we could use, and as I said, have been used across laboratories to score for death. We don't use such complicated microscopy for that. It's fairly simple, but basically you will see this repeated in much of the slides that I show you, where the y-axis is a readout of death. The conditions are shown below, and over here what you're seeing is the induction of death in cells where BAX is active. And here you see the low levels of apoptotic damage in cells which had notch active in a BAX-triggered cell. So this linkage with mitochondria took us to many directions, and I'm going to just talk about one of those today. And this is the work of my graduate student, Neetu, who's now, when she was in my lab, she's postdocing elsewhere. We've known for a very long time that the mitochondria, of course, coordinate responses to apoptotic stimuli. We obviously understand them as sites of where energies and many of our bioenergetic pathways play out, but they're extremely important also in this process, often marking sort of the irrevocable commitment to death. And Neetu has been interested in looking at and understanding how genomic damage plays out in cells and the pathways that connect to these. And connections have already been made in the literature about how molecules such as the BCL2 family proteins integrate here in this pathway. So she performed a fairly simple experiment in established breast cancer cell lines. She knocked down the Notch4 protein and using a silencing approach, which we've already heard about today. And what you see over here is that, and treated the cells with these two drugs, etoposide and 5-fluorouracil, both of which would actually trigger genomic damage. You're looking at an early time point here. This is about 24 hours in the course of this assay. At this time point, in cells which have intact notch function, you can see that there is a certain amount of death shown on this axis here. But in the cells where Notch4 was knocked down, in both conditions, in response to both stimuli, you see this dramatic increase. The point here is that the death pathway is accelerated. So there is a sensitization. It's not as though in 36 hours, we'd probably find everybody looking very much the same. But she was performing this kinetic, and this was the indication that she needed to go in and ask what did notch look like in these cells? So we are staining here for endogenous notch, and this is where we got our first surprise. Looking at Notch4, we could find it in the nucleus, of course, as we expected, because we're looking at the intracellular domain. But we also found it clustered in these substructures, which co-localized with nucleolin, which marks the nucleolus of cells. And this was slightly unexpected. This was not just an outcome in a single cell line. We saw this in a variety of, it turned out they were all breast cancer cell lines that she was looking at. And we did not find it in cells which are not transformed. For us, this was a great advantage that we could indeed overexpress the notch intracellular NIC4 domain and find that even in overexpression, it co-localized with nucleolin. So you're seeing cells over here which are just marked, in this case with fibrillarin, which is another protein found in the nucleolus, tagged to the red fluorescence protein. Here you have the notch intracellular domain tagged to GFP, and the overlap is shown over here in the yellow. So in the overexpression system, sometimes you've got this rather dramatic overlap, but as you can see in other systems, it's a tendency to localize in the same domain. So the question, the nucleolus, as you must all know, is associated with ribosome biogenesis. It is, of course, a membrane-less structure within the nucleus, but it has a certain organization, which is depicted here in the schematic. We wanted to try and understand. Now, I should say that the nucleolus is implicated in a variety of functions that are necessary for homeostasis. So it was not a surprise to find the protein in the nucleolus. It was surprising for us to find notch being positioned in the nucleolus because this had not been reported to our understanding. So the question that we then asked is, we used a very standard biophysical assay, which is fluorescence recovery after photobleaching, to try and understand what is the mobility of this molecule. Is Notch4 stuck in the nucleolus? Can it move elsewhere? Because there is also a nuclear compartment. And all that this experiment shows you is that if you photobleach and look at recovery, if areas are connected, you will see a recovery of fluorescence. If there is no recovery, it would indicate that the two units are somewhat distinct. Yeah? And when we look at that, we could see that there was a recovery with Notch4, which suggested that Notch4 had the capacity to move in and out of the nucleolus, or at least a subset did, whereas fibrillary, which was our control, showed a much lower motility, which was expected in the conditions in which we were performing this experiment. So the question, having satisfied ourselves that we were looking at a bona fide location in the nucleolus, we asked what, if any, is the functional consequence of this particular localization. And the mRNA complex is a group of proteins, which is illustrated in the schematic here, which are implicated in the cell's response to genomic damage. So it made sense to ask, is that how Notch functions? Because we are seeing that in our experiments that Notch4 had a tendency to protect cells from genomic damage. And that is what is shown over here. And if you look at, these are just looking at a whole series of these proteins. I'm showing you only two here for simplicity, and we can just look at the panel on the left here for convenience. In this experiment, we've knocked out nucleolin using siRNA approaches. When we do that kind of an experiment in cells where we have a scrambled control, where we've generally not perturbed a protein of interest that we know of, we find that there is induction of death, again, in response to these two triggers. And in cells which express NIC4, there is protection. However, this protection is abrogated in cells where there is no nucleolin. So this told us that NIC4 required nucleolin to perform this function, or at least the availability of nucleolin. And we essentially confirmed that using NCL, RAD50, fibrillary, and a couple of other proteins which are part of this complex. Since the knockout of each of these proteins gave us a similar loss of function, we concluded that Notch4 was functioning as part of a complex and could not function with any one of these partners interchangeably. From there, we went on to ask that is this truly because of a Notch, how did Notch4 get to the nucleolus? And using software which was available, Neetu basically identified a putative nucleolar localization sequence within the Notch4 domain, the NIC4. Every time I've said Notch, I must correct myself. This is NIC4. And these are obviously charged by, marked by the expression of highly positively charged proteins. So there's an amino acid. So there's an enrichment of arginines in this domain, which you can see over here. So we did this sort of standard experiment when you want to try and address this point as to whether the nucleolar localization sequence is functional and active, and the reason why NIC4 went into the nucleolus. We generated a mutation, a side-directed mutations, where some of the arginines were converted to alanines. And this would therefore reduce the charge on the protein. We also, and I'm not going to show you that data, also attached a nucleolar localization sequence taken from NF-kappa B to the NIC4 construct, and we asked how that functioned. You're seeing images here of these two mutations. In the protein where we have converted the arginines to alanine, you now find that the nucleolus localization of Notch4 is impaired, of NIC4 is impaired. And obviously where we gave it an additional tag, the protein is forced, larger amounts of protein are found inside the nucleolus. And when we looked at this, these cells, so first I'm showing you only the data from the one where the arginine has been converted to alanine. The prediction is that since it's not going to the nucleolus, it should lose the ability to inhibit apoptosis if nucleolar localization is important for function, and that is exactly what we see here. The unperturbed Notch4 protects from death. The one where you disallow entry into nucleolus, we are no longer able to protect from genomic damage. And we see this in more than one cell line. We did this in several lines. I want to emphasize here that the molecule is not inactive per se. It is just unable to function and perform those activities that are associated with its nucleolar localization. It functions perfectly well to protect cells from ER stress-induced apoptosis, where a nuclear localization is more than sufficient. So point being, we are not killing the molecule, we are showing that it has distinct functions in distinct spaces within the cells. And so to just summarize this part, we showed that Notch4 can in fact regulate sensitivity to genomic damage, that it is doing this by its localization in the nucleolus and where it functions to protect cells from a variety of signals that trigger genomic damage. I only showed you a few. And data that I did not show you, we indeed established that NIC4 makes stable associations with specific proteins, which are typically found in the nucleolus. And so that was also a confirmation that the molecule does indeed have activities associated with proteins there. And for us in community, it was important for us to also understand, because it opens up other avenues of questions, that the fact that these activities are quite uncoupled from the well-known, well-established transcriptional functions of Notch4. Now, while this was very interesting for us, my laboratory has spent much of its time looking at Notch1 functions, because these are what regulate functions of primary cells in the lineage that we had been studying. And Notch1 had in fact shown us, or we had learned, that in the T regulatory cell compartment, which is what we primarily work with, it functions from different locations within the cells to essentially help cells adapt to nutrient and metabolic stress. And so I'm not going to be showing you that data today. So the question was that, does Notch1 also function in a manner similar to what we had seen for Notch4? And the answer was quite unequivocal, I think, over here. We did the exact same experiment where we knocked down nucleolin to essentially take away the function of Notch4. But we found that, and this is what is shown in the gray bar here, that this is Notch4, which protects otherwise, cannot protect in the absence of a nuclear component. But Notch1 continued to do just fine. Yeah? So it seemed to have no role that we could identify in the nucleolus. This was intriguing because it's not as though Notch1 did not have, NIC1 did not have a nucleolar localization sequence, albeit brought around by a bioinformatic analysis. But the evidence was indeed there that this had a nucleolar localization sequence in its RAM domain, but the distribution of the protein was very consistent with what we were seeing in a functional assay. And at this point, a closer look at the sequence showed us that instead of the arginines, the Notch1 nuclear localization sequence is indeed enriched for lysines, which also give a positive charge but can be modified. And for that, we went back to this literature, which we had encountered before, where work by several groups, particularly this group, had identified 14 lysines in the Notch intracellular domain, Notch1, which were targets of the acetylation, deacetylation modification systems, and had shown that sirtuin-1 was a modifier of Notch function through the modifications of the deacetylation of these lysines on this protein. And in fact, we ourselves had identified a role in the T cell compartment through this interaction. And the NIC1 NOLS, just before I go ahead, is not just unique to the human NIC1. We could see it in other mammalian contexts as well, and also, of course, in zebrafish, which I'm not showing you here. So we asked then, quite, okay, before we go to the experiment, just for those who may not have at all ever heard of this molecule, sirtuin-1 is part of a very large family of the histone deacetylases proteins. These are well characterized, well studied, and there's a huge wealth of literature on them. So I cannot possibly do justice to this, but just to say that it is a metabolic sensor. And we know today from the amount of data that has come out and the interest that it has evoked that the sirtuins, and particularly SIRT1, plays a very, very important roles and is implicated in a variety of conditions associated with inflammation, adaptations to stress, a cell's abilities, efforts to maintain homeostasis, etc. So this is really a very passing remark on a massive field, but sirtuins are key players in those trying to understand metabolic responses in cells. And so we asked that if Notch were being modified by sirtuins, if we overexpress the sirtuin 1 protein or its inactive, catalytically inactive partner, this one does not have function, would we convert Notch into something that was NIC1 now into something that functions from the nucleolus? And the simple answer is that we could now at least confer a dependence on nucleolar proteins in cells which co-express not only Notch1, but co-express Notch1 with sirtuin. So for us, this was the first indication that if you express Notch and elevate sirtuin activity, artificially done in this case, you indeed confer a dependence on the nucleolus, which suggested that the lysine residues in Notch1 were indeed a target of sirtuin-1. And the images here would suggest that in the presence of cells, in cells where we have elevated sirtuin-1, you can actually see NIC1, which is here again GFP tagged, entering a domain which is also occupied by a nucleolar protein. So the question then was, can we demonstrate that it is the nucleolar localization sequence which is being so modified, and therefore we essentially made an alanine substitution of the lysine, and this molecule now, as you can see, is cleanly excluded, nowhere near where fibrillary is. And if we look at the functional assay now, what you see is that in the Notch molecule, where we have now taken away the ability to be tuned by sirtuin, it no longer has any dependence on nucleolar proteins. So this told us that the response to sirtuin, the modification of Notch, NOLS by sirtuin, was indeed responsible for its ability to move into or out of the nucleolus. And obviously the entry into the nucleolus expanded the repertoire of partners that the Notch protein could function with to protect cells from death, although the protection may not be desirable from our perspective. And like so, we made a lysine to arginine mutation, which is also cannot be modified by sirtuin, and looked at that function. And now you can see that that molecule, once you modify your NOLS to arginine, it behaves like NIC4 now, and it is completely dependent on the nucleolar components for its outcomes. And so I will stop there to just summarize that what we have shown is that that Notch4 has an NOLS, which was not known before. We showed that it is a functional NOLS, and that this takes it to the nucleolus, and we've established the partners and interactors in the nucleolus, which allows it or promotes the ability of cells, protects cells from genomic damage. This is, of course, a pathway which is an adaptation to stress. It is one that you might see very likely in transformed systems and may well be one of the contributors to treatment resistance. We, of course, have not yet investigated fully the roles in ribosome biogenesis, which we think might well also be a component. We have some preliminary data. We haven't looked at that in greater detail, but these are functions which are independent of transcriptional activity. The Notch one, in fact, continues to provide, I think, new information about the enormous pleiotropy that this pathway has demonstrated across multiple systems. And what we show is that the nuclear localization, which is triggered in response to a metabolic stress, in fact, contributes to protecting cells from genomic damage, which, as I said, may not be truly desirable, but that is indeed a capability that this molecule now confers on cells. It clearly expands the repertoire of signaling. And of course, there are questions that we need to address about how this might be brought about in terms of ligand dependencies, etc. But at this point of time, we have not looked at those questions. So I will stop there and acknowledge my graduate student, Neetu, who executed much of the experiments that I showed you with Geeta and Manjula. But I must acknowledge Lakshmi, who is a graduate student now in an independent faculty position, who really got us started on thinking about the Notch pathway in its varied contexts. I did not talk about this group of people who have all moved on from the lab, but have helped us map metabolic outcomes of perturbations of Notch signaling in primary T cells. And of course, I'm part of a larger group. We function in connected thematics in INSTEM, and I'm part of the regulation of cell fate group, which includes individuals asking different questions about in systems as diverse as hematopoiesis to muscle stem cells. And so there is a wonderfully enriching group that we work with. We have excellent facilities and several funds from many funders who made this work possible. So I will stop there and thank you very much indeed.
So thank you. The talk is open for discussion. Yeah, over there.
Excellent talk. I just was wondering that nucleolus, because it's a house of small nucleolar RNAs. So whether Notch is also involved in the small nucleolar RNA synthesis or snRNP's assemblies in the nucleolus?
Yeah, right. So we have some evidence that it's, okay, let me put that correctly. We have asked whether it has a role in ribosome biogenesis. We have some indication that that is possible. We haven't looked at any of the other aspects, and that is only for Notch 4. Notch 1 appears not to engage with the ribosomal either assembly or biogenesis components.
So very nice talk. Actually, it reminded me of my PhD work. So I worked with NPM1 and you showed some data with nucleolin. Do you see similar effect of NPM1 or nucleophosphine knockdown on your Notch functions and nuclearization? Because NPM1 also has a lot of lysine residues which get acetylated, and SIRT1 is the enzyme which deacetylates it and helps in the shuttling from nucleolus to nucleoplasm. So I was wondering whether Notch has some connection with NPM1.
So we did look at nucleophosphine. What we see is that in the complex that Notch forms, Notch 4, NIC4 forms with nucleophosphine and includes nucleolin, it in fact excludes fibrillarian. So we think it might give us some idea of where the Notch 4 is located. So our interest in nucleophosphine was to try and position Notch physically in terms of its partners. So indeed, yes, we did. We haven't looked at SIRT2 in modification of any of the other proteins.
Okay.
That wasn't something that we were looking at that time.
Thank you.
Yeah, thank you.
So time for one more question. There was one here in the front row.
The epigenetic landscape regarding to Notch 1 as it connect with sertulin, and second one is that does it has a complementary function to Notch 1, which is highly mutated in leukemia and also act as a tumor suppressor in other tumors.
Sorry, I think I missed that. So the second question you're asking us, you're asking about the leukemia is what?
Like there are Notch 1 mutation which are there in the leukemia, but I'm not sure whether Notch 4 has a complementary role or compensatory role over there.
Yeah, so the Notch 4 work was largely restricted to breast cancer cells and cell lines because of a colleague who was more interested and had been investigating Notch 4 signaling in the context of breast cancer. And in fact, Notch 1 protein in all the cell lines that we looked at appeared to be rather low. So it did not, and knocking it down did not, at least in our assays, change outcomes. The mutations in Notch that are described in NIC, in the leukemias, the work that has been done by Esther and others, does not include these residues. These are unprotected. I mean, these remain as so.
So this is totally different.
So it's quite likely that these molecules, these regions are available for modification in the leukemic state. Because I'm not saying these are oncogenic, these are pro-survival. They're not proliferative mutations. They don't give a proliferative advantage. They will promote survival, which is often, I think, equally
Thank you so
troublesome.
much.
Thank you.
Thank you.
Now I invite Dr. Sonia, please.
Thank you, Professor Salim. I request the session chairs and Professor Biswas and Professor Vineet Kumar to please present a token of appreciation to Dr. Salim. Please give a big round of applause.
She can hear us, huh? Yeah, please.
So with this, we close the session. I thank all speakers for the interesting talks, and we move on to the poster session. Thank you.
So actually the next talk, originally there was poster session, but as we are running late, so now we will have talk of Dr. Mazure, and after that there will be poster session and oral session will be overlapping, means poster and oral together. So for this, I would invite Professor Subhrajit Biswas and Dr. Elisa Jivanoti. So I guess Dr. Elisa, could you hear us?
Yes, I can hear you.
Hello. Elisa, how are you?
Fine, thanks. Thank you very much for allowing me to be online. It was a pleasure to see the session of the Congress.
It's good to see you, but it would have been great if you could have come here.
Yeah, it's true.
Okay. So just let me briefly introduce our session chairs. So Elisa is presently in Cancer Center, Amsterdam. And before that, she's also scientific researcher in research, and then she has been postdoctoral research assistant in Division of Pharmacology in the University of Pisa from 2007 to 2011, and she basically works on this metabolic and glycolytic inhibitors. And together with Elisa, Professor Biswas from MET will be the session chair. So Professor Biswas, please. So I guess, Elisa, you got the CV of Mazure?
Yes.
Okay. Okay, or otherwise I will ask Professor Biswas to introduce Mazure. Okay.
Okay, thank you.
Thank you, Dr. Binit. It's my pleasure to introduce Natalia Muzer, and she is a senior scientist and research director at the CNRS, at the Center Mediterranean D Medicine Malika-Reddy in France. And I will not take too much time just to introduce already Jack's tell about a lot about the hypoxia. So it's kind of, we'll know a lot of more about the hypoxia, and she is focused on a protein is called VDAC, and all of you know VDAC is very important protein that is voltage gated anion channels, protein 1, and it is present in the mitochondria. So personally, I am also the third generation from the Korsmeyer lab who work in mitochondria elaborately in the United States. And we also working on the VDAC. And after that, Dr. Frederick also talked about the prostate cancer PC3 cell lines. So I think Natalia will highlight the kidney cancer as well as the prostate cancer also, with special emphasis on the VDAC protein as well as hypoxia, metastasis, and other cancer. So we are eagerly waiting to listen to you. Please.
Can somebody organize my presentation? I'm not sure where it is. How is the So first of all, thanks everybody for this very nice meeting, and I would like to thank the organizer for giving me the opportunity to present our work and to allow me to come for the first time in India, that I totally felt in love, especially yesterday as we get the chance to visit the Taj Mahal. So today I will present something that this is the first time that I'm presenting these results about medulloblastoma, specifically in hypoxia. So first of all, let's get some point about hypoxia. So when you are in Nice, but also in Noida, because I check for the altitude, you will breathe an air at around 21%, depending on the pollution or the fog. And as soon as you will increase in altitude, you will have a decrease in the concentration of air. And when you reach the Mount Everest, at this moment, you will breathe only a 7% oxygen concentration. And this is why you will need an oxygen bottle. But let's get back to Noida. You breathe your air at 21%, but very soon all the tissue will not be at the 21% of oxygen. Your lung will be in between 13 to 19%. The arterial circulation will be at 13% of oxygen. The venous circulation will be at 5%. And the tissue will be, some tissue will be mainly in between 0.5 and 2.5% of oxygen. And in the brain, it's important to know that the concentration of oxygen is mainly in between 4 and 7%. But I am working for now 30 years almost in hypoxia, specifically in the solid tumor. And in this solid tumor, you will have concentration of oxygen very low, such as 0.1 or 1 to 2% of oxygen. So how does it work, hypoxia? I would like you to understand that it's a dynamic process. It's not a picture at one moment. It's more than that. So when the oxygen demand is equal to the supply, there is absolutely no problem. But your tumor cells, they divide quite fast compared to the normal cells. And at this moment, the cell number will increase and the oxygen demand will increase also. And in this case, your oxygen demand will be superior to the supply in oxygen. And this is the moment where you will reach this hypoxic concentration in the tissue. So quickly, the initial response will be for the cells to alter the metabolism and to switch to an anaerobic glycolysis. And the cells will stop dividing, or at least they slow down the proliferation. And they will go back to the oxygen demand and the supply, no problem. But it's not always like this. And if the first response is not enough, cells will try to increase the blood supply, like Jacques presented before, and increase angiogenesis. And in this case, the adaptation, you will have adaptation, selection, and cells will go back, and it's like a loop like this all the time. So Jacques presented already a very nice regulation of EF, and I decided to present a very light scheme of the regulation of EF. I'm not going to go into this regulation. as you understand that which is the master and the master commander of the hypoxic response, is extremely important in the hypoxic response, is highly degraded in normoxic condition, and it's completely stabilized in the hypoxic condition. But this scheme is very simple, but represents almost 30 years of work that have been rewarded, as Jacques said, but I do not have the same collection of pictures as Jacques. So they has been rewarded by a Nobel Prize to Bill Kellin, Sir Peter Ratcliffe, and Greg Semenza. So it has been a great pleasure for me for these past 30 years to be part of the story of hypoxia and to spend almost 20 years in Jacques' lab. Okay, so you understand now that hypoxia is a dynamic process. So we have close to the capillary, we have what we call the normoxic zone. Normoxic, people are thinking about 21%, but now I guess you understand that that will never be 21%. The normoxic zone, 21%, it's what you will find in your lab, in the incubator, but that will be more correct to call, to speak about the physiologic zone. Then you have the hypoxic zone, and then you have this possibility to reverse and go back to the normoxic zone. But if you go a little bit too far, cells will die and you will reach the necrotic zone. What is important to know is that the cells that are in the hypoxic zone are the cells that are the most resistant to radiotherapy and chemotherapy. Why? Because chemotherapy has problem to reach the hypoxic zone, and for the radiotherapy, you need oxygen to break the DNA. So I have passed the last 30 years to try to understand the mechanism by which these cells are resistant and trying to fight the hypoxic tumor cells. So as Jacques said previously, more than 2% of the genome is regulated by hypoxia. And different processes are also regulated by hypoxia in my glasses. Treatment resistance is regulated by hypoxia, vascularization, dedifferentiation, metabolic reprogramming, genomic stability, immune response, survival, invasion and metastasis. And you will certainly find a process that interests you in this nice scheme. And in the lab, we are mainly interested on the treatment resistance, on the metabolic reprogramming, and on survival. So let's start the story about the medulloblastoma. So behind a disease, there is always human being. And this story started once when I met Denis Macario, the president of the Fondation Flavien. His son died of the medulloblastoma, and he started this foundation. And when I was discussing with Denis, I just realized that not that many research were done with the pediatric cancer, that not a lot of things were known about medulloblastoma, and not a lot was known about metabolism, and medulloblastoma, and less about hypoxia and medulloblastoma. So we decided to start the story together and to try to understand what was the role of hypoxia in this disease. So the origin of medulloblastoma is from medulla, the Latin for marrow. Blastos means germs, and oma for the tumor. And it has been described first by Cushing and Bailey in 1930. And at the beginning, it was described as a spongioblastoma cerebelli, which was a soft and suckable tumor that is localized at the level of the vermis of the cerebellum. And then they switched to medulloblastoma because they were thinking about multipotent cells. So the cerebellum is divided in two hemispheres with, as I said, the vermis, in the middle, and it's part of the brain where you can find the Purkinje cells, and a type of neuron which is essential for the functioning that allows the integration of the information it receives. So you can understand that if you have tumor in such an area in the brain, you will affect the motor movement, you will affect all the voluntary movement, the posture, the balance, the coordination, and the speech. Unfortunately, this is the primary malignant neuroectodermal tumor for kids. This is the first cause of brain tumor for children. I didn't find any numbers in India, but I guess you have medulloblastoma also in India. But in France, we have around 150 new cases per year in France, and it's diagnosed at the age of around 6-year-old. So to get this very simple, the classification has been done for the medulloblastoma, and they found 4 subgroups, and in which, I didn't put this on this slide, in which you have subgroup, almost 3 different subgroups in each subgroup. So it's a very heterogeneous disease, and you will have 4 groups with the WINT group, 10% in the prevalence, metastasis with a low rate, and the prognosis is quite good with 95% after 5 years. Now let's move to the sonic hedgehog. 30% of the kids will have this, will be classified in this group. Metastasis low, local recurrence, and the prognosis is intermediate with 75% after 5 years. The worst group is the group 3, with 25% of the kids that will present this classification. Metastasis high level, recurrence metastasis, and a poor prognosis, the worst prognosis ever, with 50% after 5 years. Group 4, 35% with a high level also of metastasis, but the recurrence is also with metastasis, but the prognosis is intermediate. So we decided to study the role of hypoxia in the medulloblastoma, to focus on the group of sonic hedgehog. So we used 2 different cell lines, the DAOI and the ONS76, and the group 3, in which we used 2 cell lines also, the HDMB03 and the D458. But because of the time, I will present only 1 cell line, but you have to imagine that we obtain exactly the same result for each of the cell line for each group. So how do we treat medulloblastoma? So first, it's let's say a normal surgery, and after radio and chemotherapy, but you understand from what I told you just before, that because you touch the cerebellum, that is very essential for the motor function and coordination, that will have a big impact on the mobility, the cognitive function of attention, language, and mood to all the kids that will got surgery and radio and chemotherapy. We have some hope with so sorry, I just realized that it's in French, the last part. So we have radiotherapy, which is the normal way to treat kids. And very recently in Nice, but also in other parts in France, we have the proton therapy, which is more focused and with less side effect. So we have a lot of hope on that. But you understand that we definitively need a lot of new treatment to fight against this disease. So with Dr. Julie Contenti, who was done a PhD thesis in my lab, she was very interested in the role of hypoxia and in the medulloblastoma. And this is the hypothesis that we have done based on the fact that we have different localization of the subgroup in the cerebellum. So the group 3 is more in the middle part of the cerebellum, and you can see the sonic hedgehog, which is more in this area. So when we overlap the vascularization, our hypothesis was that we will have differences in the tissue oxygenation, and because of that, we will have different way to act the cells of the different group will have different way to act in the hypoxic condition. So we know that ATP is produced in condition of glycolysis, but Julie and I were more interested in the couple of NAD plus NADH. We didn't work that much on NAD plus NADPH, but they are essential for maintaining the cellular redox homeostasis and modulating several biological processes, including cellular metabolism. So we decided to focus on the NAD plus NADH. So cells are using 3 different mechanisms to oxidize NADH and to regenerate cytosolic NAD plus. So this is the first one in red that you can see here. This is the cytosolic and mitochondrial glycerol 3-phosphate dehydrogenase component of the glycerol 3-phosphate shuttle that I will call after G3PS. They are also using the malate dehydrogenase 1 and the glutamic oxaloacetate transaminase, the component of the malate aspartate shuttle that I will call MAS because it's easier, that are represented in yellow right here. And also, and you have heard of that already this morning, the reduction of the pyruvate to lactate with the lactate dehydrogenase, the A and the B, that is here. And we have decided, instead of using CRISPR or siRNA, to use different inhibitors, IGP1 to block the first shuttle, the G3PS, the AOAA to block the second shuttle, MAS, and the GNE140 inhibitor to block the reduction of the pyruvate to lactate. All these data are unpublished, so please no dissemination. It has been sent for reviewing, and we are waiting for the answer quite soon. So just this figure to put this 3 shuttle in the big figure. So you can see that here we are in the glycolysis pathway, and these 2 shuttles are more into the mitochondria stuff. Okay, so the first thing that we have done was to look at the expression of the GPD2 and MDH2, the 2 main enzymes from the 2 shuttles, compare this to the group of SH, the sonic hedgehog, and the group 3, using an Affymetrix array with 285 primary medulloblastoma samples. So in red, here you can see that these 2 enzymes, the GPD2 and MDH2 enzyme, are highly expressed, whereas they are less expressed in the group 3. So based on that, we checked what is the level of expression in our cells, and we checked in normoxia in white compared to the kinetic of hypoxia, 24, 48, and 72 hours. And you can see that the cells respond nicely in hypoxia when we look at the expression of the GPDH. The GPDH is induced under hypoxic condition. The same for in the ONS 76, so the sonic hedgehog group, whereas we saw absolutely no variation of expression in hypoxia in the group 3. We saw also no variation of expression for the MDH2. We looked also at the protein level, and we saw something similar. So, of course, so this is a steady state metabolic analysis, and you saw absolutely nothing. So I will help you trying to understand. So what we have done, we took the 2 main cells that I will show you, the ONS from the sonic hedgehog and the HDMBO3 for the group 3, and we culture them in the presence of the inhibitor for the first shuttle and AOAA for the second shuttle. And you can see that when we use the inhibitor IGP1, there is not that much of modification at the metabolic status. We are losing the deoxyribonucleotide synthesis, a little bit of amino acid metabolism that is more expressed, pentose phosphate pathway, and fatty acids. However, when we block with the AOAA, so the mass shuttle, you can see that there is a huge difference. We have more nucleotide synthesis pathway, and you can see also we have less of the other pathway. Now, when we check, we use the same inhibitor in the group 3. The inhibitor of the G3PS does not change too much, more pyruvate and asparagine. We saw less metabolic pathway, also a little bit in the pentose phosphate pathway, adenomethionine metabolic pathway. But one more time, AOAA completely switched to something which is more into the mitochondrial metabolites. So based only to that, we can say that both shuttles seems to be very important, but when we look at the profile of what we obtain with the steady state metabolic analysis, the mass, the malate aspartate shuttle seems to be more predominant. So I will show you only the viability because proliferation, almost all the cells had a low level of proliferation with the different compounds. But what is interesting is the viability. So if you check here with different concentration of the IGP-1, 24 hours in gray and in yellow it was 72 hours, you can see that the group 3, the sonic hedgehog cells are absolutely not intact. Here it's 21% of oxygen, 6% of oxygen, 1% of oxygen. They don't care. Now you can see that for the group 3, more or less, they don't care at 21%. You can see that at 6%, if you compare just the control here versus the control here, they grow less at 6%. But what was very bizarre and unexpected is that when we use this compound at 1%, we saw an increase in the viability at 24 hours, but also after 72 hours. So we looked at trying to understand what was the reason for that using the Sears analysis. You can see that with the sonic hedgehog ECAR, so looking at the glycolases, there is absolutely no impact of the inhibitor. And here, when we looked at the respiration, we saw a slight increase in the respiration. Same fun, even better for the HDMB03 group 3 in physioxia, so 6% versus 1% of hypoxia. And you can see that we increase the metabolism when we add this inhibitor. And it was really obvious that when we add this inhibitor, we had more respiration in 6%, a little bit less obvious at 1%. So this is why these cells, they live better in hypoxia when we block the first shuttle. So we try to understand the reason for that. And by reading a lot of literature, we have seen that when the GPDH is active, this will generate a lot of reactive oxygen species. So the idea was that when we block the activity of the GPDH, we block also the ROS production, and that this case will promote the high viability and a better proliferation under low oxygen condition. And this is indeed what we obtain in both cell lines from the group 3. You can see here that when we block the ROS by using the NAC, we increase the viability. When we add the IGP-1, we increase the viability, and if we use both the NAC and IGP-1, there is no effect anymore because we already block the ROS. And here it was just the production of the ROS that we were able to block in the same way with the NAC and IGP-1. So blocking the first shuttle was by itself was not a good idea as the cells proliferate and they don't die. So what about the second shuttle? So we used it by itself, and For the first time, we saw a slight effect on the viability on the sonic edge-up group cells, very light, but at least something. We saw also a light impact on the group 3, so we decided to block both the MAS and the G3-PS shuttle. And you can see that at this moment, it has absolutely no impact on the sonic edge-up group. But with the group 3, we were able to decrease a little bit better. We don't kill completely, but we decrease from, let's say, 20 to 30 to 40% the viability of the cells under hypoxic condition. Same, we looked at the metabolic profile using the CRs, and you can see that in this condition for the sonic hedgehog, if we block just the second shuttle or both of them, we have exactly the same profile. We block the respiration, but the same way. And we block also the metabolism, but this has absolutely no impact on the viability. However, here for the group 3, you can see that by itself, the inhibitor in blue does not block the respiration, but when we use both, we block slightly, but we block statistically, significantly, statistically. We block the respiration and we block also the glycolysis. So the group 3 require both the shuttle, the MAS and the G3PS. And when we block these two under hypoxic condition, it's working. So let's talk about the last one, the LDHA pathway that we blocked with the GNE 140. We use also the same Affymetrix array analysis with the 285 patient. I forgot to put the legend, but here this is the sonic hedgehog group in green, and in blue this is the group 3. And you can see that there is more LDHA in the group 3 and less LDHB expression in the group 3. So the same study, we looked at the viability, absolutely no impact on the sonic hedgehog group. And we saw a slight impact, but significant impact in normoxia, same in physioxia, but very bizarrely, we found no impact in hypoxic condition, where I thought that I will see the best impact. And if we check here, we had a very nice blockage of the glycolysis in the ONS76 and a nice blockage also under hypoxic condition, but not enough really to block and to kill completely the cells. So of course, we decided to use the big combo and we blocked the 3 different shuttles. And you can see here, so this is the cell proliferation. So of course, we block almost everything, but you have to look at here that in hypoxia, we didn't block as much as we were able to block the proliferation in normoxia or physioxia. In the group 3, we were able to block completely, and we started a little bit to kill the cells, specifically in the sonic hedgehog. And what is interesting is that in normoxia, you kill almost 50%. You kill 30% in the physioxia, and you barely kill 10% in hypoxia. I told you that the hypoxic cells are very resistant. And in the group 3, we were able to kill more in physioxia and a little bit also in hypoxia. And you can see here, it's a clonogenic assay. When we were doing this for 7 days, finally, we completely abolished, so we don't know if it's completely proliferation that kill everything or if we block completely the proliferation, but we were able to block the progression of the cells. Okay, so this is all in vitro experiment, and we decided to go a little bit on the in vivo using the organoids, and for that we have done a collaboration with Luca Tiberi, from Italia in Trente, and what he has done was he used the protocol of Muguruma to obtain some human some cerebellar tissue in 3D, and after transfection of the OTX2 and MYC, and he published that this was able to recapitulate the group 3 profile. After transfection with the Venus, he obtained some organoid derived from the model of human group 3 medulloblastoma, and all the tumor cells will be expressed in green. So we decided to use our different inhibitors. So you can see here, this is the day 0, where you can see all the green tumor cells. And we use IGP-1, AOAA, and GNE140 inhibitor, and the big super combo. And you can see that after 6 days already, so there is no impact on the control, no impact with the IGP-1, but we start to see a slight impact with AOAA and GNE140, and a little bit with the combo. Now, after day 8 and day 11, we have almost no green cells in the AOAA inhibitor, the same for the LDHA and with the combo, and it's more obvious after 14 days. So now we used IMARIS to reconstruct the green tumoroid, organoid, and you can see that we have plenty of green cells in the control, a lot of cells in the IGP-1, and this is not completely strange because in vitro we obtain exactly the same, but we almost completely kill the cells using the AOAA, GNE, and the triple, the big combo. And this is the volume that we measure. And to finish this, what we have observed is that by using the cleavage of the caspase 3 plus the Venus, we have done the merge, and we can say that we have cell death due to apoptosis in the case of the different inhibitor, but not with the IGP-1. Okay, so to conclude and to give you the perspective, remember that at the beginning we thought that we had a certain area of hypoxia and that the group will react differently depending on hypoxia. And what we found is that the group 3 is very sensitive to hypoxia. So our hypothesis now is moving a little bit. Maybe these cells are not that much under hypoxic condition, but more in physioxic condition. And this is why they are that sensitive to adapt to hypoxia. However, what we demonstrated is that by using different inhibitors that play both on the glycolysis or OXPHOS, we can propose some anti-cancer, new anti-cancer therapeutic targets. That the 3D model that we use is an heterogeneous condition where we have normoxia, physioxia, and hypoxia. So that's very interesting to test the reality of your compounds. And of course, we need now to test these different drugs with the drugs that are used already, like the cyclophosphamide, the gemcitabine, axitinib, etc., etc. So I would like to thank the team 5, and Frédéric Boss that you have listened this morning. Also Julie, who has done part of this job and that has been helped by Yingbo also. So we are in Nice, so if you are interested to come and to see Nice, we are here, and we have this very nice view, not from our lab, but almost. And I would like to thank all the sponsors, and also all the old-timers that have been during this 4 last year in the lab, and also to thank all our collaborators to help us for this story. And I will be ready to take your questions. Thank you.
Thank you. Natalia is completing talk. It's a time for question and discussion. And I like to invite also Dr. Eliza, if you are online, please interact. Session chair, Dr. Eliza, you are here?
Yes. Can you hear me? Perfect.
Yeah. So please, any questions? Yeah. We cannot see Dr. Eliza.
I think
I'm
here.
Yes. Hello.
Well, if now there are no questions from the audience, I would like first of all to congratulate, because this was really an excellent presentation. Thank you very much. And it's nice how you guide us through your studies, and really fascinating. And I really like also the way you underline that hypoxia is dynamic. And since I am a pharmacologist, I would be very interested in the next step that somehow you already anticipate in the last slide. Because of this dynamic process of hypoxia, and because of course, also unfortunately the aggressive behavior of these cancer cells, which do you think could be indeed a best cocktail? Because you made a cocktail thinking about essentially the inhibitors of the specific process that you described, but then typically in the clinic we are dealing with chemotherapy, and you said of course there is resistance to chemo and radio, but what do you think could be somehow the best cocktail which can exploit the results that you found in your studies?
So that's a very good question.
With something with a typical anti-DNA drug, or something with target therapy, because you suggested a little bit both in the last slide.
So as a scientist, I was super happy to find 3 different compounds that I can use to kill cells in hypoxic condition. That I am totally aware that there is a big difference between the scientific world and after going back to the clinic. I am totally aware also that all these compounds, I don't think you can use them directly to the clinic. Some are with side effects, but for me, it was more a way to show that, okay, hypoxia, we need to be more aware of the role of hypoxia in this disease, and that metabolism, we can play on metabolism. That should be the next way. So using this compound maybe not the best way, but maybe we can find new compounds or use some compounds that are already known or better known to block this pathway, and maybe we can play with this. I am totally aware of the big gap that there is between what I'm showing right now and the clinical, but I am very optimistic that if we discuss more with the big pharma, or if we discuss also with the clinical part, we will be able to find a pathway to meet and to find the better treatment for this kind of disease. But I don't have the solution yet.
No, of course. No, but it's really good that indeed you are proposing and presenting so many strong data that can essentially...
I'm not sure that a doctor will agree right now to take these 3 compounds and to give it to a kid.
No, indeed, I think you have to think a smart combination with what is available now to add these.
Yeah, at least we know in which direction we have to look. To my feeling, for sure.
Absolutely.
Question for audience? Any question from audience? We can have 1, 2 questions.
I have one question.
Oh, yes.
Dr. Nathalie, so how long you culture your organoids?
So I'm not doing myself the organoids. It's Luca Tiberi in Italia, and he sent me the organoids, and I can culture them for at least 2 weeks.
2 weeks?
Yeah. Okay. So when
it's too early, actually.
So when he sent me, yeah, I agree. What will be so when he sent me the organoids, they are already big, as you can see on the picture. It's not at the early beginning of the organoid development. But I guess your question will be, can we delay this and put this treatment a little bit later? We can try. It takes a long time to obtain this organoid, so we depend always from Italia, from the lab, the collaboration of Luca Tiberi, and sometimes it can take him 3 or 6 months to obtain this organoid. So it's difficult for us to play as much as we would like to play.
And which patient sample you used for deriving these organoids?
So they used...
like fact, blood or any other?
This one was more related to the group 3.
Sorry?
The group 3 patient. But in fact, they used the cerebellar and they modified it to make it look like a group 3. And when they compare the patient and the organoid they obtained, it was the same profile.
Okay, thank you.
Forgive my ignorance, the categories that you showed us, the sonic hedgehog and the other groups, are these all uniform in a particular tumor, or do you ever find a mixed presentation?
That's a good question because looking in the literature, there's nothing clear on that. What they say is that it's heterogeneous in the group, for sure. So in the group 3, you will have 3 different subgroups. And I didn't find a clear answer if sometimes you have different groups together. It's not clear to me. And I am asking very often, and people are not comfortable with this.
So I wonder if your organoids will give you that direction. If you can generate organoids of all types, do they stay true or do you see differences emerge? I wonder.
That's a good point. I have no idea.
Yeah, I mean, till you do it,
that's
you
a
won't know.
good point. Thank you. Yes.
Thank you. It was a lovely talk.
Thank you. If there is no question, so we go for the next session. Any more questions? Okay, so next announcement, please.
Thank you, Dr. Nathli, for such an wonderful talk. Now I invite Dr. Subhajit Biswas to please present a token of appreciation to Dr. Nathli. Now the poster session and oral presentation session will be commenced simultaneously. So all the poster presenters may please stand their poster, and I request Dr. Priyanka Jain to start the oral presentation session.
So, good afternoon, everyone. To start with the oral presentation session. So, the first speaker here is Mr. Michael Athmer. So, I please welcome him to give the talk.
So thank you very much for the kind introduction. My name is Michael Althammer. I'm a PhD student in the lab of Professor Dr. Kreutz. And I'm going to talk about the potential immune regulatory role of the local vitamin D3 metabolism in tumors. Vitamin D is mainly produced endogenously in the skin by means of ultraviolet light. This precursor is further converted in the liver to calcidiol 25 vitamin D, and then further converted in the kidneys to calcitriol, the biological active form 125 vitamin D. This is catalyzed by an enzyme called CYP27B1. Calcitriol then binds to the vitamin D receptor VDR, which is present in almost all kinds of human cells. So this is textbook knowledge. However, CYP27B1 is not only expressed in the kidneys, but also in epithelial cells and immune cells, but as well as in tumor cells. The main function of vitamin D3 in the immune system has an anti-inflammatory or more tolerogenic phenotype to induce this. For example, or it has effects on the adaptive as well as on the innate immune system. On the adaptive immune system, it, for example, upregulates Th2 as well as Treg response and downregulates a Th1 and Th70 response. In the innate immune system, it promotes M2 macrophages, but on the other hand, downregulates antigen presentation and CD80, CD86 regulation in dendritic cells. So with this knowledge, we asked ourselves now, if tumor cells have CYP27B1, if they can produce active vitamin D, and this active vitamin D, if this has an effect on the immune cells in the microenvironment. and so reduces the immune response against the tumor. First of all, we did some analysis of effects of active vitamin D on T cells. Therefore, we treated T cells with 5 nanomolar of 125 vitamin D, and we detected a high upregulation of CD38 as well as CTLA4, which are both or indicates a peripheral Treg phenotype. Those effects were both gone when we did the VDR knockouts, so we proved with this that the upregulation is done over the VDR 125 axis. Next, as I already mentioned, if tumor cells have CYP27B1, is it possible that they produce from the biological inactive precursor 25 vitamin D, 125 vitamin D? For this, in a first step, we analyzed the CYP27B1 expression in renal cell carcinoma patients, and we found that a high CYP27B1 expression correlated with a worse survival in patients. Additionally, we found a positive correlation between CYP27B1 expression and FOXP3 expression, which again shows us a more Treg phenotype in immune cells. Then we did a CYP27B1 and VDR staining in different tumor entities and found that also in mammocarcinomas, pancreatic carcinomas, but also in head and neck squamous cell carcinomas, there were some tumors which had a very high CYP27B1 expression. However, the highest expression we found in clear cell renal cell carcinomas tumors. This is also depicted in an immunohistochemical staining on the right-hand side. Interestingly, VDR, the vitamin D receptor, was expressed at a very low level in all tumor intensities. To mimic this in a good model, we then generated spheroids from two different cancer cell lines, for one colon cancer spheroids and the other one head and neck squamous cell cancer, and also found there that those cell lines express high levels of CYP27B1 and low levels of VDR, so they mimic the tumor situation well. What we also did is that we treated those cell lines with inactive 25 vitamin D and measured 125 in the supernatant. And we found that there was no downregulation of CYP27B1, as well as no upregulation in the vitamin D receptor, as it's, for example, known in T cells. This contributes to our hypothesis, so the tumor is not affecting itself negatively in regard to proliferation or differentiation. Of course, we then wanted to know, do those tumor cell lines also produce 125 of 25, and under what circumstances? For those, we treated again the cell lines with 100 nanomolar of 25 vitamin D with different medium supplements, and we saw that the presence of serum independent of AB or FCS was critical for the conversion of 25 to 125. We also checked for if there is a difference in 2D cell culture versus spheroids, and we saw that both are able to produce 125 from 25. So the spheroids really mimic the tumor situation best. To summarize, so we found that tumors, as well as our tumor cell lines we've analyzed, express CYP27B1 at a high level and VDR at a very low level, and our cell lines can produce 125 in the presence of 25 vitamin D. With this knowledge now, we plan to do a co-culture model with tumor spheroids and immune cells, and check then the effects of the active vitamin D, the 125, by flow cytometry, but also live cell imaging. Also, we plan to do measurements in primary human tumor material of 125 vitamin D. With this, I want to thank all my colleagues and my team, as well as the collaborators and you for listening. Thank you.
So thank you, Michael, for the wonderful talk. So here he's open for the question answer session for 2 minutes. Yes, sure. Thank you. That was very clear. I'm intrigued by your data about the Tregs. What is your understanding of the Treg infiltration there?
I'm sorry?
The T regulatory cells that you told us infiltrate are found in your tumor microenvironment?
If we found some, no.
You found Tregs, right?
No, we found a higher FOXP3 expression, but this was just data analysis.
Oh,
we will stain more tumor samples on our own, and there we'll also check for if there is or if Tregs correlate with a higher CYP27B1
okay,
expression.
so as yet you don't really know why you pick up that signature. Okay. So any more questions? Okay. Thank you, Michael.
Thank you very much.
So now we will welcome our next speaker, who is Professor Subhash Chandra Bose, and he's in online mode, so I'll just connect him. Yes, Professor.
Hello.
Can you hear me?
Yeah, I can hear you. Am I audible?
Yeah, you're audible and your slide is perfectly visible.
All right, thank you. At the outset, let me thank the organizer and thanks Priyanka for allowing me to present through online mode. Sorry that I could not join you as a person. So yeah, so what I would be speaking for next couple of minutes. So
if you can on your camera, we can see you.
Let me turn on the. Is it okay now?
Yeah. Yes.
Yeah. All right. Yeah. Thanks again. We were recently moved from NCL Pune to NIMANS, the Department of Neurochemistry, and what I would be speaking about how tau oligomers are internalized in microglia during the internalization. What are the key receptors were involved, and upon the receptor, how they undergo the tau to phagocytosis or the endocytic trafficking, and in the end, how this tau oligomers are degraded, or the receptor based or the non-receptor based. That's what I would be seeking for next couple of minutes. The overview of Alzheimer's disease, there are two important proteins. One would be the extracellular protein called amyloid beta, the intracellular protein called tau, which largely involves in microtubule assembly and disassembly of microtubules. That's what I would be speaking on, the intracellular, and also tau has a dual role. Also, it involves in extracellular propagation. It has been found that it may behave like a prion-like propagation, one cell to another cell. So how this tau behave in microglia, I would tell you in a minute. The overview of microglia is the microglia has an important property in the brain. It also helps and also it both arms. So one would be the neuroinflammation, and if they figure out any of the pathogen, they trying to engulf and they will eat the debris, they will throw them out of the cell. And the third property would ultimately remove the toxic proteins. Then further they undergo phagocytosis, migration, and other processes. On the other hand, once it's phagocytosed, all the cytoskeletal protein are majorly activated. For example, actin remodeling and the tubulin and also the other cytoskeleton networks. On the other hand, what would be the prime function of tau is one of the natively unfolded protein. It binds to microtubules, and also it has a role, intra and extracellular role in terms of disease condition. So I would display what the three are important cascades of tau is that once it forms the monomer, it also makes the multi-cellular and also the dimeric and also multimeric tau protein, which would be important role in terms of propagation and also the synaptic plasticity and whatnot. You could see the various structure of tau which involved in terms of Alzheimer's disease and also other proteinopathies. So with this, I would like to start with the very first. We have prepared the longest isoform of tau, which is 441 amino acid, would play important role in terms of aggregation and also propagation. We have fully characterized and stabilized this oligomers, and we have also done the high-resolution tomography for helical filaments and also for the global oligomers. What you see, they were nicely stable, and we wanted to know, once you expose this oligomers, how they involve or how they internalize in microglia. So this is where the N9 microglia, and also we have prepared the primary cultures. You could able to see that there were specific antibody have been used, and you could nicely see that the oligomers were nicely internalized and also possibly involved in terms of migration and other actin remodeling work. And also there are specific markers have been used to understand their microglial activation, that is called one of the channel ion channel calcium channel binding protein called IBA1. It also co-localized majorly in terms of oligomers, then comparatively the monomer and also the aggregates. This clearly depicts that the oligomer has important property in terms of migration or the activation of microglia, for example. So the second part, what I would like to say that any protein to they enter into the cell, there would be a driving force. That is where we have screened almost more than 22 receptors. Out of 22, we have taken further into consideration to understand their molecular mechanism and also cellular signaling cascade. There are important receptor. One would be the P2Y12. On the other hand, the chemokine receptor 3. So today I will be discussing on only the P2Y12. So we also tested their interaction and also their interaction ability. So they clearly interact, and also they have the interaction affinity, which clearly suggests microglial migration and also interaction takes place via this tau oligomers instead of aggregates and the monomer. And also we looked at their remodeling, because once it microglia activated, we want to know which direction they are moving, what would make them, either what are the driving forces, are they only actin involved, are they tubulin also moving or pushing them towards their migration or the orientation property. So you could clearly see that most of the the lamellipodium and also the pilopodial structure majorly have been increased in terms of oligomers. This is P2Y12 dependent. We have also blocked the P2Y12, and also on the other hand, we also silenced. We could see that typically they are the P2Y12 dependent, and it involves in pilopodia formation and also the migrative structure. This we have published in way back in 2021 Traffic. And the second point, which I was more interested, once it migrates, what would be their fate? How they, endocytose, and how they undergo protein degradation, or they have other classical degradation like armors massively undergo the endocytosis and the vesicular trafficking and also degradation. So we thought that the very first, the GPCR is the beta arrestin, the tau can get in and also undergo the endocytosis, then the late endosome, then finally they try to choose by the lysosomal degradation. So let's see what are this, the studies suggesting us. So we have done the time-lapse study with the various time point. We exposed this oligomers, monomer, and the aggregates to the microglial cultured cells, and we looked at which time point they were, better phagocytosis or the P2Y12 dependent phagocytosis. We could see that at the early less than 5 minutes, we could massively see the increase in terms of phagocytosis, and also they were dependent by P2Y12. This also have been, as I said, been silenced, and also we have the blockers we have synthesized. We could clearly see that in terms of monomers, there is a rapid signaling which influences the time-dependent endocytosis. And further, we went ahead to check with beta-arrestin dependent. Yes, of course, they are massively co-localizing with only in the oligomer case. In terms of aggregates and monomer, we don't see very little. And this also done by time dependent, and the quantification also clearly suggests there is a oligomer dependent with the beta-arrestin. Further, we tested either what would be the early endosomes with beta-arrestin as well as P2Y12. This also clearly suggests the oligomers are massively, co-localizes, and also this has been tested with the blockers also. It clearly say that less than 5 minutes the oligomers can internalize and also involve in the endosomal pathways. Further, we tested with the mature and also the late endosomes for RAB7 and also RAB11. It clearly suggests that the P2Y12 is mediating the endosomal trafficking and also involves in lysosomal degradation. On the other hand, we have the positive signals. It comes from the LAM2A, and also this has been proved by biochemically and also the microscopy studies. So with this, what I would like to summarize that the P2Y12 involves in the endosomal trafficking, and also it involves the late endosomes. Finally, they degrade by LAM2A, and this is important in terms of the migration and also the trafficking, as well as for the intra and the extracellular role of tau. With this, I would like to conclude. The microglia can phagocytose by P2Y12 mediated by endocytosis, and also during this process, the beta-1 arrestin is assisting for the desensitization and also follow up with all other endosomal trafficking, and this may also involve in terms of the accumulation with the late endosomes. With this, I would like to also display from this area, we had few of the cover art, which is from traffic and other with this. I would like to thank all my students who are majorly worked by the Rashmi Das, and also few part of the study were done by Ari Krishnan Sidambaram, and now she's already submitted thesis, and soon she's graduating and is also going to submit her thesis. At the outset, I would like to thank all the funding agencies from NIMANS and also from DBT and CSIR, and also my past institute NCL, all our collaborators whomever they part of this study. And I would like to thank the MBO also for giving me the chance. If there are any questions, I'm happy to take.
So thank you, Professor Subhash, for the elaborative talk. So I would welcome any questions for this session. Okay, so no questions. So thank you so much for your talk. So now I would like to invite Dr. Sanjini Dasgupta of EMSA for her talk.
A very good afternoon to everyone. I'm Dr. Shinjini Dasgupta, Assistant Professor and DBT Wellcome Trust Fellow from Amit University. So today I'll talk on P53 amyloid load is highly correlated with cancer grade, leading to tumorigenesis. But before going into the topic, let me brief you about what are amyloids. So amyloids are protein peptide aggregates. They are highly ordered and stable structure because of the cross beta sheet structure, which gives them a distinct characteristic features as well as a distinct morphology when observed under the electron microscope. So generally, these amyloids are associated with neurodegenerative diseases, whether it's Alzheimer's or Parkinson, where the key protein is responsible for forming amyloid and is responsible for the disease condition. Now, parallelly, when we talk about P53, the aggregation and accumulation of this protein was seen several decades ago in many primary subsets of tumors, where both the mutant and the wild type were shown to sequester either in the cytoplasm or in the nucleus. So this excited a lot of people, and many started working on the prion-like and the amyloid property of this protein. So separate domains were purified. People started studying the amyloid forming propensity, as well as it was shown that when P53 aggregates, it can sequester its family members P63 and 73, rendering them non-functional. While these studies were going on, we hypothesized that amyloid formation of P53 causes loss of function, gain of tumorigenic properties, as well as spread from one cell to another, similar to the prions. To validate our hypothesis, we worked with the animal and the human biopsies, and we showed that P53 protein was co-localizing with the amyloid-specific antibodies as well as amyloid-specific dyes. We isolated the entire pool of the amyloids from these biopsies, and with immunochem, we could specifically say that some of them were from P53 origin based on the nanoparticles. Then we developed this cell model, which we have patented, and this cell model we used a formed in vitro peptide of P53, which was transfected in the cell. Now, generally, P53 either is expressed in the nucleus or it's not detected due to the negative regulation by the MDM2. But once transfected, the entire endogenous population can be converted into amyloid, giving them a stabilized expression in the cytoplasm. And such puncta or these sequestrations are co-localized with the amyloid antibodies. To confirm that this is not a non-specific approach, we took control with the alpha-synuclein fibrils as well. This P53 amyloids were shown to display loss of function, which was shown by FACS analysis, where actinomycin D was used as a DNA damage marker. So P53 was not showing apoptosis, as well as the ETBR staining decreased. Further, interestingly, they displayed a lot of tumorigenic properties like increase in the wound coverage, adhesion. A lot of those genes were upregulated, which were anti-apoptotic or which had a proliferative markers. Then we displayed that this particular amyloid has prion-like properties, which can show cell-to-cell transmission from the classic co-culture experiments, where the protein was labeled differently in both the different cell types. And therefore, we validated this entire process and published. Now, after this, the next question that came to our mind was, how is the entire thing related to disease progression, or how is the entire thing related to cancer grades? To study that, we took some patient samples. We studied a small cohort of oral cancer as well as stomach cancer of different grades. And we found that P53 amyloid was highly correlated with cancer grades. We used multidisciplinary approach like CPRION, ELISA, FTIR imaging to calculate the percentage of beta sheet by scanning the entire tissue sections. We isolated the amyloid fibrils, and indeed the amyloid formation was highly correlated with the cancer grades. Now these tissues generally they harbor a lot of P53 mutations, and to study whether the mutations can play any role in this correlation, we subjected these tissues to next generation sequencing. We characterized them, we found a lot of mutation, but these mutations were not correlated with the cancer grades. Though SNPs were high in the higher cancer grade, but the overall picture was not correlated. And therefore, whether the protein is wild type or it is mutated, both of them were able to have the propensity to form amyloid in the patient samples. Then we wanted to study the effect or the status of the family members, P63 and 73, and we found that the P53 amyloids were able to sequester both the family members, and this sequestration was higher in the cancer grades. It was also a grade-dependent manner, as evident from the immunoprecipitation studies. CHIP analysis also gave us an idea of the functional loss, where the P53 amyloids were not able to interact with some of the key interacting proteins. So in summary, I like to say that unlike in neurodegenerative diseases where amyloids are toxic, P53 amyloid is not toxic because it gives a growth advantage, and therefore it leads to tumorigenesis as well as it can contribute towards cancer progression. So I would like to acknowledge Tata Memorial Hospital, Central Facility, IIT Bombay, my mentors and my collaborators, students, colleagues, and thank you, and my funding agency, India Alliance. Thank you.
Thank you, Dr. Shinjini, for this wonderful talk. I would ask for any questions in the session. So, ma'am has a question.
So I have just a small question. So do you think it's the multimer of the tetramer, the functional piece is the tetramer? Multimer forms the aggregate, or it's the...
So all the domains can separately form aggregate. So people have shown that even the N-terminal can form aggregate, the DNA binding domain can form aggregate, as well as the full length. Even the C-terminal has been shown to form amyloids. So even the individual domains have capability.
So size of aggregate, do they vary across the different patient samples or with the mutations that you observe?
Yeah, so we are doing that structural function analysis. That's ongoing work right now. But what we saw that if it is a mutant, then the kinetics of aggregation is much faster. So that we have also published that in case of mutations, especially the structural mutants, they can, structurally refold the protein and unfold the protein, and therefore that will help the kinetics to be faster than the wild type ones.
Thank you.
So, no more questions? Okay, thank you, ma'am. So the next speaker here is Mr. Sabal Saha.
Good afternoon, everyone. I am Shoibal Shah, a graduate student from ICMR NISET, Kolkata. I would like to thank the organizers to give me the opportunity to present my work here titled as Induction of Autophagy in Breast Cancer, Human Breast Cancer Cells by a novel peptide derived from non-canonical activation of PAR1 by hemagglutinin protease isolated from Vibrio cholerae. Before going to describe my work, I would like to give you a brief glimpse about cancer and microbial protease. So why microbial proteases are so pertinent for cancer research these days? Because there are so many conventional therapies for cancer treatment, but they have plethora of drawbacks, including drug resistance and many others. But because of that, in the past few decades, various microbial proteases have been explored to exhibit anti-cancer property by controlling multiple cellular processes like proliferation, differentiation, etc. Now, in order to combat cancer, a protease needs to have certain properties, like it should cause cell death or it should cease the cell proliferation process. Now, cell death may occur by generally three types of mechanism. First one is apoptosis, that is the programmed cell death, and this is a late response. Second one is necrosis, that is uncontrolled cell death, and it occurs due to sudden injury or trauma. The third one is autophagy. This is an early response, and autophagy is generally known for a cell survival mechanism. But at extreme case, autophagy may also cause cell death. Now, autophagy plays a very interesting role in cancer. It plays a bipartite or dual role in cancer. Like in early stage of cancer, it degrades the misfolded proteins and pathogens that may eventually lead to cancer development, and thus it suppresses cancer. But at later stage, cancer cells themselves exploit the machinery of autophagy for their own survival, and thus it promotes the survival of cancer cells. Now, my study is based on these two earlier publications from our lab, where we have shown that HAP induces apoptosis by selectively targeting PAR1 in breast cancer cells, and a novel peptide, PFI-SAD, originated from alternative activation of PAR1 by HAP, is a key regulator of the HAP-induced apoptosis. As I've earlier mentioned that apoptosis is a late response and autophagy is an early response, we have speculated here if HAP has a potential to induce autophagy in human breast cancer cells at earlier time point and at low doses. And also we have planned to check the mechanism of action of that HAP-induced autophagy. So before going to show my work, I'd like to give you a brief insight about the molecular mechanism of autophagy. mTOR is the master regulator of autophagy, and that phosphorylates COL-K1 at a particular serine residue, and it inactivates that. On the other hand, AMPK competes with mTOR, and it also phosphorylates COL-K1 at two different serine residues, and it activates COL-K1. When ULK1 is activated, it forms a complex and it starts phagophore formation. Phagophore is a double membrane vesicle, and when it starts forming, then it starts encapsulating various materials which are subject to degradation. That may be pathogens or misfolded proteins or something like that. Now, when this total formation is complete, this whole structure is called autophagosome. Now, in this process, Becklin-1 helps in the lipidation of LC3-1 to LC3-2. Inside the lysosome of autophagosome, LC3-2 is present. Now comes the very pivotal part of autophagy, that is the fusion process. Because in order to degrade these materials, it needs to be fused with lysosome, because lysosome contains acidic hydrolysis. Now on the membrane of lysosome, LAMP1 is present. Both LAMP1 and LC3B or LC3-2 facilitate this process of fusion. After fusion, this fused body is called autophagolysosome. And now comes the final process, that is the maturation. When these materials are degraded, then lysosome releases cathepsin inside the cytosol of autophagolysosome. So here are my findings. We have checked all these experiments in a model breast cancer cell line, human breast cancer cell line, that is MCF7. We have all the data these are showing blank. Oh, all the blocks. Can you bring your? Yeah, I can bring.
Yeah. Just hold for 1 minute.
Bring your.
You just spend that. Presentation on the front. Yeah, now is it okay?
Now comes to my findings. So we have checked all this data in model breast cancer cell line, that is MCF7, and we have checked the potential of HAP to induce autophagy in terms of the expression of two flagship markers of autophagy, that is LC3B and LAMP1, in a dose and time dependent manner. As you can see here, this dose 0.5 microgram per ml of HAP at 60 minutes of time point showed the best autophagic response here. In order to further reconfirm that, we have done lysotracker staining assay and acrin-orange staining assay in the MCF7 cells treated with HAP of the particular dose with or without autophagy inhibitor. As you can see, the green puncta and red puncta are increased here when treated with HAP. Also, we have checked the release of cathepsin in the HAP treated cells. in presence and in absence of autophagy inducer 3MA. So next, our earlier study from our lab that HAP induces apoptosis by selectively targeting PAR1 in human breast cancer cells, we have speculated that if PAR1 also have any possible role in our study, that is HAP-induced autophagy in MCF7 cells. So in order to check that, we have checked the expression of PAR1 in MCF7 cells treated with HAP of different dose and different time points. And very interestingly, at the same particular dose and time point, we found the best expression of PAR1 when treated with HAP. In order to further reconfirm that, we have done the knockdown assay. So we have knocked down PAR1 in MCF7 cells and treated that with HAP of different doses. You can see here by means of P62 expression, when we have checked the expression of P62 in MCF7 cells treated with HAP, and in the knockdown PAR1 knockdown cells treated with HAP, there is no significant change when we treated the knockdown cells. But in normal MCF7 cells, there is certain decrease in P62 expression. That means autophagy induction was there. But in PAR1 knockdown cells, there was no significant change in terms of autophagy induction. Also, we have further reconfirmed that by means of lysotracker staining and then analyze that in flow cytometry. You can see here the increase of lysotracker intensity is there when the MCF7 cells were treated with HAP. But in knockdown cells, there was no significant change in the intensity of lysotracker. So further, another study from a lab that a novel peptide P5ACD originated from alternative activation of PAR1 by HAP is a key regulator of the HAP-induced apoptosis. So PAR1 is basically a transmembrane G-protein coupled receptor, and our protease HAP cleaves PAR1 at a specific site and generates a peptide called P5ACD. The sequence is P5ACD. It then activates G-protein, and G-protein further carries on subsequent cellular processes. So we have checked here if in our case that particular mechanism of PAR1 activation is being followed. That means P5ACD is being generated by HAP or not. In order to check that, we have treated our cells with that specific peptide here and checked autophagy induction. So by means of P62 expression and LAMP1 expression, you can see here, when we treated the cells with the target peptide, there was significant induction of autophagy. But into unrelated scramble peptides, when we treated the cells with those, there is no significant induction of autophagy. Further, we have checked all these molecules that I have earlier mentioned involved in the pathway of autophagy in MCF7 cells treated with that particular peptide P5ACD of different doses. And we have found 50 micromolar dose of that particular peptide showed the best autophagic response. And very interestingly, it was earlier reported that PAR1 activates the mTOR, that is the phosphorylation of mTOR. But here in our study, we found that this alternative activation of PAR1 inhibits mTOR activation and subsequently induces autophagy. Next, on the very crucial part of autophagy, there is autophagolysosomal fusion. So there are so many molecules which can initiate autophagy, but they fails to carry on the process up to the fusion. But in order to degrade the materials, fusion is very much needed. So because of that, we checked by colocalization study of LAMP1 and LC3B. You can see here the yellow puncta is there when we treated the cells with peptide of that particular dose. But chloroquine, which is known for the inhibitor of the fusion process, we have checked that there are plenty of lysosomal vacuoles there, but they are not co-localized. That means the process is initiated, but the fusion is absent there. That means green and red puncta are present there separately. Also, we have checked the autophagy flux by autophagy assay kit from ABCAM, and we have adapted two approaches here. One is confocal microscopy, the other one is flow cytometry. You can see the green puncta is increased in plenty of numbers when we treated the cells with that particular peptide. That means the total number of autophagolysosomal vacuoles is increased in a particular number of cells. In flow cytometry analysis, also you can see the same kind of data. So lastly, we have checked cell proliferation assay and cell survivability assay, because already I have mentioned that in order to combat cancer, a protease or peptide needs to cause cell cessation in cell proliferation, or it needs to decrease the cell survivability. So by Ki67 expression, we have checked the cell proliferation, and when the cells are treated with that peptide at particular dose, cell proliferation was significantly diminished. That means the green fluorescent was so much quenched here. But very interestingly, when we inhibited autophagy by 3MA and then treated that cells with that particular peptide, then cell proliferation again restored. And there was no significant effect on the cells in terms of proliferation when we treated the cells with scramble peptides. And similar data we have found in cell survivability assay by MTT. Cell survivability again decreased when we treated the cells with that peptide, but it restored when we treated the cells with the autophagy inhibitor 3MA and then treated with peptide. And lastly, which is very important in cancer cell research, that is the cancer cell specificity of our protease. So we have checked the autophagy induction in MCF10 cells, that is a non-cancerous breast epithelial cell line. Because it lacks PAR1 expression and our HAP, our protease, targets PAR1, and by mediating PAR1, it is inducing autophagy. So that's why, as expected, we didn't find, very interestingly, we did find almost no expression of autophagy here in terms of LAMP1 and LC3B. This is my future work. So we know that PAR1 activates G protein and then it induces autophagy by inhibiting mTOR. But we don't yet know G protein inhibits which MAP kinase. That is ARC or P38. That is our next study. So hereby I would like to conclude that HAP can induce autophagy in breast cancer cells in a dose-dependent manner. And HAP-induced autophagy in breast cancer cells is mediated by non-canonical activation of PAR1 by HAP. A novel peptide PFICD originated from a HAP-mediated cleavage of PAR1 induces autophagy in breast cancer cells in a dose-dependent manner. And lastly, this peptide-induced autophagy aggravates proliferation of breast cancer cells and eventually leads to cell death. So I'd like to hereby acknowledge my PhD supervisor, Dr. Amit Wal, for his immense support and guidance. Dr. Shantarattu, Director of NICED, ICM and NICED. And I'd also like to acknowledge all my lab members for their continuous support. And I'd like to thank UGC for my fellowship and ICMR for the project grant.
So thank you, Sepil. Any quick questions, please? So I feel there are no questions. Thank you so much. I'll give you. So the next presenter here is Ms. Preetha Ganguly. She's here.
It was a Sunday afternoon back in 2020. My phone was ringing. I picked up the call and the voice from the other end said, "It's your aunt calling. I have just called you to let you know that the cancer has reoccurred." It was devastating for us. I said, "Aunt, what are you talking about?" She said that the time has come and I have to go now. The next few months were very much struggle for both my family and me. One side there was COVID and the other side there was cancer. She died. At the age of 54, my aunt died of breast cancer, struggling 7 long years, and this cancer has occurred in her body thrice. I failed her. The medical community failed her. The scientific community also failed her. But she is not the only one. Every 5 seconds, one person is being diagnosed with breast cancer, and out of 2, one woman is dying. So I, Preetha Ganguly, a third-year student from IIT Delhi, is working on carbon nanodot loaded with bioactive molecules for breast cancer treatment. If I particularly talk about the government of India, then the government is spending $1 and trillions of money on cancer research. But as we can see, the progress is limited. So clearly, whatever we are doing till now is not working. Let's talk about medicine now. What do we do in medicines? We send firefighters. You might be thinking why I'm talking about firefighters. Because the cancer is like a big fire, and these firefighters are the drug molecules. But as we can see that 99% of these firefighters or the drug molecules never reaches to the fire, that is cancer, because they lost their path or get excreted out of the body because they don't have proper equipments. And here come the picture of nanoparticles. There are a lot of nanoparticles present, commercialized, like mesopores, polymeric, lipid-based. But here I want to particularly put the highlight on carbon nanodots. Why? Because they have high biocompatibility, photostability, and most importantly, autofluorescence. This carbon dot can be synthesized chemically as well as they can be derived from biomass. If we could derive this carbon nanodots from biomass, then they are nature friendly, they are inexpensive, abundantly available, and most importantly, the waste is converted into wealth. Now let's talk about the overview of my project. So what we did, we took curry leaves as a source and extracted the materials from it, and then hydrothermally converted them into carbon nanodots. Now, these carbon nanodots were loaded with two drug molecules or two bioactive molecules. One is curcumin and another is quercetin. Here there is two questions that might be coming in everybody's mind. First, why not commercial drug molecules? Why is the bioactive molecules being utilized? This is the reason is that the drug molecules which are present commercially can be utilized at the later stages of cancer. They are very much harmful to the normal tissues at an early stage of cancer. So we have used curcumin for killing of the cancer cell. Now quercetin. Why quercetin? As I have already mentioned that the reoccurrence of cancer is very much prominent. So this quercetin blocked the PGP channel, which is one of the major cause of multi-drug resistance. Once the carbon dots are prepared, we have looked for the morphological changes in the breast cancer cells, their gene expression change, how the death is taking place, as well as cell cycle arrest. So once the carbon dot were prepared, we have gone for physical characterization. First of all, we have gone for UV spectroscopy and found that there is a peak at 273 nanometer, which confirms the presence of carbon nanodot from the literature. Then we have checked for their stability at different pH temperature. After, in the figure E, we can see FTIR images, which confirms the co-loading of both the drugs to the carbon nanoparticle and then XRD. Once the carbon nanodots were prepared, the most important question which came to our mind is whether these dots are biocompatible or not. So for that, we have used two cell lines. First is MCF7 and the other is NIH3T3. MCF7 is a breast cancer cell line, whereas NIH is a mouse fibroblast cell. When we have checked the MTT, we have found that carbon nanodot do not neither kill the breast cancer cell nor the normal cell. So they can't be used as a therapeutic drug molecule. So they can only be utilized as a biocarrier. Now, after that, we have loaded curcumin and quercetin on them and found that if we use a dose of 32.59 microgram per ml, then normal cells will be alive around 85 to 90%, whereas the breast cancer cells will be reduced more than 50%. So we have chosen this IC50 value for further studies. In order to prove our MTT assay, we have gone for the live dead assay, and from that we have found that when we have used the bare carbon nanodots or single loaded carbon nanodot, then the death is very less. But in co-loaded one, after like 48 hours, the death was 99% and only 0.700% of live cells were present. All the studies were performed on MCF7 cells. Once the live dead assay was proved, now the next point is how the morphological changes are taking place, whether the cytoskeleton is being affected or the nucleus. So we have used trypsiphalidin dye to check the cytoskeleton fusion and found in the figure that the fusion of the
cells are very prominent in co-loaded one, whereas membranes are specifically having boundaries in co-loaded bare carbon dots. Now, after that, we have checked for whether the killing is being apoptotic or necrotic. So, in the control, bare and quercetin, we can see that the majority of cells are live after 48 hours, whereas in co-loaded, there is a shift from the normal cells to the apoptotic phase, and also 43.2% of cells are in the late phase of apoptosis. Next, ROS production was checked by DCDF dye, and we have found that yes, a high amount of around 100% folds of curcumin co-loaded produce ROS production. Finally, we have checked for cell cycle arrest, in which phase this co-loaded carbon dots are stopping the cell, and we have found that G2M phase, the cells are being arrested. Once these basic studies were done, we have also checked for gene expression and found that the two genes which are very important, like P53, which increases the process of apoptosis in cancer cell, is increased by the co-loaded one, whereas BIRC, which is a triple negative biomarker, is significantly reduced around 10 folds by the co-loaded one. Finally, as I have already mentioned, that I am checking for the chemo resistance to SOP, so PGP protein should be not present by the co-loaded. We have gone for Western blot, and from the figure we can see in control there is a prominent band. In series also, bare series there is a prominent band, but in co-loaded there is no band present. These are some of the references, and I would like to thank my professor, Professor Prashant Mishra, for guiding me, supporting me in the entire process. Thank you. I'm open for questions.
So thank you for your talk. So any questions, please? Yes, there is a question from the back.
Thank you. Thank you very much. You used as a control the empty carbon dots. Were you able to control for quercetin or curcumin on their own as a control?
Yes, from the data, I have, so we have used 4 combination. One is the bare carbon dot, then we have used single loaded quercetin carbon dots, then curcumin carbon dots, and then co-loaded. And we have checked for the entire 4, all the data are in the set of 4. So from that, we have concluded that the co-loaded is the best. They are showing synergistic effect to each other, like the carbon dots, the quercetin, and curcumin.
Thank you.
Thank you.
So any more questions? So there is one more question.
You are taking the drug concentration based on IC50. Don't you think IC50 will already kill 50% of the cells? Don't you think that will be too toxic for the cells?
Yeah, IC50 is the inhibitory concentration at 50 for MCF7, means breast cancer cells. But for normal cell, 85 to 90% of cells are alive. So we can use this concentration for further use. They are not affecting the normal cells. They are only affecting the cancer cells.
But it's already killing 50% of cells, right?
IC50 is for the MCF7 cells, MCF7. Not for the normal cells. Thank you.
Thank you for your presentation. So you just said the synergistic effect is there. So did you check the synergistic analysis, means by Chow-Talala test or something? Means how did you conclude that this is additive effect or synergistic effect? So did you check that?
Okay, so we started with, so we know that curcumin is highly when it is exposed to any of the environment, it just denatures its property. So we started with the UV spectroscopy. So we checked how the curcumin is getting absorbed. So first we have checked for curcumin, then we have checked for quercetin, and when we have used a combination, then the stability of this curcumin was increasing significantly. Then we have loaded this carbon dots on, we have loaded this curcumin and quercetin on the carbon dot, and then we saw that the stability is increasing 10 more folds. Then other studies were also performed, as I have already shown you, that APOP process or the like ROS or cell cycle. In each case, the synergistic effect of these three are doing some wonders than the single ones. So from that we have chose.
No, actually what I'm asking that how did you conclude that this is not an additive effect, this is a synergistic effect? This could also be additive effect. Like two things are being combined here, so it may be additive effect. So have you done any Chotalala test or something to check the synergy is present there or not?
No, we haven't checked. Thank you. We will surely do this.
Yeah, you could check that with Chotalala test.
Thank you.
So I have one question. Did you check the IC50 value of independent quercetin and independently with the quantum dot, and then you are checking the
Yes, sir. Yes, ma'am. We
synergist?
have checked it for.
Okay.
Like, so curcumin having a very high IC50. It's around 16 mg per ml. It's killing normal cells around 50 to 60%. So when we are loading it, and carbon dot, as I have already mentioned, that carbon dot is having no effect. Similarly, we have also found that quercetin is also not having any effect on MCF7 as well as NIH. So when we are attaching these three molecules together, only then we can find this good effect, or we can say this magical effect.
Okay, so you are saying quercetin have no anti-cancer effect on the MCF cell line?
It has, but it take a lot of more hours to perform, like more than 72 hours. But here we are performing all the tests within 26 to like 30 hours. So the time is reduced a lot.
Okay, and what about the toxicity of carbon nanoparticle?
It don't have any toxicity, is highly biocompatible. It's even increasing the growth of the cells, normal cell as well as like MCF7 cells.
Okay, thank you. It's a nice talk.
Thank you.
So thank you. If there are any more questions.
Yeah, hi. Basically, I'm working with coumarin derivative, and this coumarin, curcumin, charcoal are all the flavonoid products. Okay, and they are known for their increasing intracellular ROS levels. Okay, then you are saying that your coumarin is not causing toxicity. I have a doubt at that point. Along with it, you're also stating quercetin. Quercetin is proclaimed drug, and it has been currently used in the market to curing the cancer. So
I would like to tell you that yes, quercetin kills cancer cell. But if you will have this literature survey, you will find out that the quercetin takes a lot more hours to kill the cancer cells. Like it's 72 hours or it's more than that.
So you are focusing on basically the
decreasing
drug
the time
concentration
also,
or
yes.
the time study. Also, did you have evaluated any pathway through which this your multiple colloided drug is working?
So I have started my PhD work, so I will be focusing on that era also. So the next objective is working on the pathways and decoding them, how they're working, how the synergistic effect is working.
Okay, best of luck.
Thank you.
So thank you very much. Thank you, Preetha Ganguly. So the today oral talk session is over. So you can proceed for the next coffee break. Is that fine?
Thank you, Dr. Westwell and Dr. Bost, for evaluating the oral presentations. So now the oral presentation session is closed, but we have time. So there is a poster presentation is going on in the lobby. So we can join that. You can join that. And from 5, we will have the last to talk. So we have 20 minutes. So I invite Professor Lori to chair the session along with me. And Professor Lori is a professor in Broad Stem Cell Center, and he's also Associate Director for the Technology Transfer. So you will get to know when he will present and he will give talk, so you will get to know his research. So now I invite Professor Lori to introduce our speaker, and let's start. Thank you.
Thank you. Thank you. It's a pleasure to be here. And I'm excited to introduce Stephanie Bayek, who's presenting today on transfer of mitochondria from presenting her data on transfer of mitochondria from astrocytes in glioblastoma. She's currently at the University of Miami in the Sylvester Comprehensive Cancer Center and been studying the immunotherapy and immunomodulation of brain tumors. She's won a number of early career awards, including the Barlin Early Career Investigator awards from the Cancer Stem Cell Conference, Women in Neuro-Oncology, Elsa Albrecht Breast Award, many awards, and it's worth noting that she's a recipient of NIH K99 Award, which is a very difficult and prestigious award to get, and has published a number of high-impact publications, up to 30 papers, impressive for such a junior person. And so I'm excited to hear what Dr. Bayek has to say. Is she ready?
Yes, thank you so much for the kind invitation. It's my great pleasure to share our work on mitochondria transfer in the context of glioblastoma. I'm a very junior investigator, so all the data I'm going to share with you today was done in the laboratory of Dr. Justin Latty at the Cleveland Clinic in collaboration with Dr. Herboye Miletici's group in Norway. So this was a highly collaborative study. And the premise of this study is the lack of treatment opportunities for glioblastoma, which is the most common primary malignant brain tumor. This is a very deadly disease, and the standard of care has not changed over a decade. It involves surgical resection followed by radiation and chemotherapy, and this treatment modality. With this treatment modality, patients usually survive somewhere around 12 to 18 months on average. More recently, there are clinical trials that test tumor treating fields, and this treatment approach was able to extend the survival up to 20 months, but it's still the outcomes are still very grim. And there are several reasons why it's so hard to treat glioblastoma. This is a very complex disease, and its interactions with the microenvironment is very important. So obviously there is the issue of blood-brain barrier that effects, effective delivery of treatments. But when we focus on the tumor microenvironment, we see that glioblastoma tumor cells interact with numerous neural cells, as well as infiltrating immune cells. This is a highly immune suppressive tumor, involves infiltration of tumor-associated macrophages and resident microglia. But one of the most common tumor cell types in adult brain is astrocytes, and these cells also arise from astrocyte precursors. So interactions between the tumor cells and astrocytes is quite important for the progression of these tumors, but we don't have a good understanding of what this interaction involves and how astrocytes in the tumor microenvironment, normal astrocytes, can drive tumor progression. And as we all appreciate, there are multiple ways tumor cells can communicate with their environment. In the context of immune regulation, for example, we know that the tumor cells can express immune suppressive receptors, and that does prevent them from getting eliminated by anti-tumoricidal cells. We also know that tumor cells can secrete cytokines, chemokines, other soluble mediators that can reshape their microenvironment to a more permissive environment. And that is true for extracellular vesicles. Tumor cells themselves can secrete extracellular vesicles or respond to extracellular vesicles that are secreted by the stromal cells by increasing their proliferation stimulus and so forth. But is there an option for a different mode of communication, and could that involve transfer of organelles from the environment to the tumor cells? And there is a reason why we think this could be a possibility. Existing literature suggests us that glioblastoma cells can form networks, and they can transfer mitochondria through interconnected networks. This is from one tumor cell to the other tumor cells. But we also know that astrocytes have this capacity. In the context of stroke, it has been shown that astrocytes can give their intact mitochondria to neurons to prevent them from further damage. And there's also literature in other solid tumors that suggests that cancer cells without mitochondria, these are the rose cells that are depleted of mitochondria, can acquire mitochondria from host environment and restore their metabolism. However, this is a quite artificial system and really does not encapsulate the tumor scenario in which we know that they do have an intact mitochondria. So the questions were to understand whether mitochondrial transfer occurs in the context of glioblastoma. If so, which cells are the donor cells and what the mechanism of transfer is. And finally, we really wanted to understand whether this mitochondria has a downstream effect on the tumor cell metabolism and biology. And that would be important so that we can drug this process, either the transfer itself or the downstream effects, for development of next generation anti-glioblastoma therapies. Long story short, what I will share with you in the next couple of slides suggested that glioblastoma cells can acquire mitochondria from the microenvironment, mainly from astrocytes, and this leads to metabolic reprogramming and drives tumorigenicity. So the first experiment we really did was to understand whether this transfer is a feasible approach. And we have some syngeneic glioblastoma cell lines tagged with GFP, and we orthotopically implanted these mouse tumor cell lines into wild-type mouse, which are controls, or MK2 mice, which have red mitochondria due to COX-8 promoter and an MK2 fluorophore. And when we looked with immunohistochemistry whether mitochondrial transfer is occurring, I hope these images appear high resolution on your screen, but we were able to detect this red signal encapsulated within the GFP positive tumor cells, suggesting that there were mitochondria coming from the tumor microenvironment into the tumor cells. And furthermore, when we stain with a membrane dye with glutamine, we were able to show that the mitochondria trafficking is occurring through microtubes, and we can see that there are mitochondria aligned here that are coming from stromal cells that are not GFP positive to tumor cells which are GFP positive. We further validated this observation with flow cytometry, and we were able to actually show this is a very frequent event, and almost 20 to 30 or 40% of the tumor cells had exogenous mitochondria obtained from the tumor microenvironment. So we wanted to really understand whether this was driven by the immune cells. As I mentioned briefly, myeloid cells are very prevalent in the tumor microenvironment. And to test this hypothesis, we did bone marrow chimeras. In this setting, we obtained MITO-MK2 bone marrows and put them into wild-type mice, so only bone marrow-derived cells in this setting express the MITO-MK2 mitochondria. And when we again implanted tumor cells into these mice, you can appreciate that the transfer rates were super low. The dot plots are shown on the left side, where we observed 20 to 35% of uptake in MITO-MK2 mice, but the bone marrow chimeras, the ratio is around 1%. And this is the quantification for multiple animals on the right side. So this really suggested to us that, at least in vivo in this setting, that it was the resident cells, neural cells, that were the main donors, mitochondria donors, and not the infiltrating immune cells. And we also wanted to do more mechanistic analysis, so confirm them in the in vitro setting. We obtained astrocytes and microglia from brains of mice, and also macrophages. We polarized macrophages from bone marrows and performed a co-culture experiment. And over the course of 4 days, we observed that again, that the macrophages were not the main donors, shown here in pink, whereas microglia and astrocytes were transferring high rates of mitochondria into tumor cells, and especially the rates in astrocytes were slightly higher than microglia. So what about human cells? Is this something we observe in mouse? And we tested that, in collaboration with Dr. Herboy Milettich's group in Norway. And they used this model in nude rats, where they injected MitoDS lead tie virus into the brains of these mice. And later they came back and injected human tumor cells, patient-derived xenografts, P3 cells, into the same spot. And what they were able to show here is that, again, the GFP cells marking the tumors had red mitochondria within the cells. And this is the reconstruction of the image. And here they observe that this is actually, again, very frequent event. And the yellow dots, which are marked with white arrows, are the mitochondria that are encapsulated within GFP-positive tumor cells. So, which cell types are responsible for that? To test this, we went back and stained with the astrocyte marker GFAP. And again, looking close-up images, you can see that there is an astrocyte projection here that is right by the tumor cells. And again, internalized mitochondria is shown in yellow here and highlighted with white arrows. And again, image reconstruction shown here. This is purple, is the GFAP astrocyte projection, and right at the intersection of the astrocyte projection with tumor cells, we were able to detect internalized mitochondria by the tumor cells. And this again holds true across many patient-derived xenografts, and we can show this in vitro by obtaining different lines and co-culturing them with immortalized astrocytes that are transduced with microenvironment vector. And in this setting, similar to mouse models, we observe that there are 30 to 40% of mitochondria transfer into patient xenografts from astrocytes. What happens and where does this mitochondria localize? So we see that the internalized mitochondria is scattered throughout the tumor cells. There are some foci that are enriched with mitochondria, but it is mostly around the periphery of the nucleus. And in fact, we wanted to determine whether this was really integrated into mitochondrial network. So we did a TOM20 staining in which we marked all the mitochondria. And again, MitoM-Cherry here shows the exogenous mitochondria in the L1 patient-derived xenografts. And we were able to see that the acquired mitochondria are at random places in the mitochondrial network, but was within the part of the network. And in fact, when we look at the signal localization, co-localization of TOM20 and mitochondria, we see that these mitochondria do express TOM20, suggesting that they are in fact mitochondria likely, and they are part of the mitochondrial network. But the important thing is that what is the mechanism of transfer? And can we drug this? So this is the area that we are still actively working on. But what the initial results suggested that this is energy and contact dependent. To test the mechanism, the first experiments we did was to, maybe starting with the right, is to culture the cells at 37 degrees where there is the active energy-dependent mechanisms versus 4 degrees where we kind of halt cells and metabolically. And when we culture the tumor cells, patient-derived xenografts with astrocytes at 4 degrees, we didn't observe any transfer, suggesting that whatever transfer is happening was not a passive diffusion event, but involved active transportation mechanisms. Furthermore, to understand whether the mitochondria are secreted into microenvironment within extracellular vesicles and then subsequently uptaken by tumor cells, we did the experiments where we co-cultured tumor cells with astrocytes and separated them by a transfell, or we put them into the dish and they are contact dependent. And in this setting, we observed that transfer, in the setting of transfer, there was virtually no transfer of mitochondria to tumor cells, suggesting that the cells needed to be in close contact and close proximity. And this wasn't just like excretion of the mitochondria from the environment, the stromal cells. And to better understand how this trafficking occurs, we investigated multiple mechanisms, but the one we identified to be prominent is through an actin-dependent network. And here we can observe, again, a human patient-derived glioblastoma line co-cultured with astrocytes, transduced with myeloid DS red virus, and the images suggest to us that there is a actin network connecting tumor cells with the microenvironment. Here shown in yellow is the actin cells, and there is the projections that are highlighted between a stromal cell on the left and a tumor cell on the right. And this image is, I guess, is more prominent, but it basically shows that there is a line of mitochondria along through the actin network that is again coming from an astrocyte towards tumor cells. So we wanted to target this and to understand its importance, and we use an inhibitor of actin polymerization, cytokalasin B. And in this setting, we observed that when we treat the cells with cytokalasin B, we completely abrogate the transfer of mitochondria from astrocytes to the tumor cells. Vincristine here serves as a control, and it is an inhibitor of tubulin polymerization. And we observed that vincristine treatment did not prevent mitochondrial trafficking, suggesting that the mechanism is actin-mediated. In the context of glioblastoma, GAP43, growth-associated protein 43, has been previously identified to be important for formation of connections between the tumor cells. It is an actin-associated scaffold protein. It is important for neuronal axon regeneration, but it is also upregulated in reactive astrocytosis, which is what we observe in the setting of stressed astrocytes. And in fact, previous studies had indicated that knocking down GAP43 prevents formation of this in tumor networks. And this is what we were able to confirm in our experiments as well. When we knocked down GAP43 in the glioblastoma cells in this setting, we observed that there was a reduced formation of microtubes between the tumor cells and astrocytes. And subsequently, this reduced microtube formation translates as reduced mitochondrial transfer rates. In this setting, we knock down GAP43 both in astrocytes and tumor cells to prevent this network from completely forming, and we observed that the mitochondrial transfer rate was significantly reduced, more than 25%. So this result suggests that GAP43 is a potentially druggable target to regulate mitochondrial transfer. But the important is that is this the mechanism that is worth targeting and whether it plays a role in glioblastoma biology. So to understand this, we did a number of co-culture experiments, some of which I will share with you today. We co-cultured astrocytes and tumor cells, and then ended up subsequently sorting out glioblastoma cells that acquired mitochondria from these astrocytes, or glioblastoma that retained their that acquire mitochondria. We did this in both with mouse and human cells, and I will invariably show you the results. So here shown the human PDX lines, and what we ended up observing is that the cells that acquired mitochondria, shown here as mCherry positive ones, had higher levels of ATP production compared to mCherry negative ones from the same co-cultures. Furthermore, when we looked at again using a different human glioblastoma patient-derived line and looked at the metabolic alterations, we observed that those that acquired mitochondria from the microenvironment had higher levels of cellular expression, oxygen consumption rate, again shown here with the red dots, compared to those with low levels of exogenous mitochondria. Or control here is the cells that are not co-cultured with astrocytes. And here, this is also the indication of maximal respiration capacity, showing the same results in a different way. So this really suggested that the mitochondria transfer leads to an increased oxygen consumption and increased ATP production. And what is the functional relevance of that? To further address that, we did a phosphoprotein array. And then I ended up trying to identify what pathways were upregulated in this setting. And we also did some experiments where we did mass spectrometry and identified that there were numerous metabolites that are upregulated in the cells that acquired mCherry mitochondria related to pre-pyrimidine metabolism. This is relevant because our phosphoproteomics also suggested that there was an increased cell proliferation and cell cycle related protein presence in the mCherry positive tumor cells compared to mCherry negative cells. So both metabolically and regarding the protein content, we observed that there was likely an increased proliferation in the cells that acquire mitochondria from the environment. And this was what we were able to confirm in vivo by looking at cells that are at G2M phase. And we saw that those in vivo, in the setting of in vivo, in mouse glioblastoma lines, those that got MK2 mitochondria from their surrounding were more likely to be at the G2M phase, suggesting that they were more likely to proliferate compared to mCherry negative tumor cells. And in humans, when we look at, again, with host staining the cell cycle, we observe a similar result, and those in the co-cultures, L1 cells shown here, those that acquire mitochondria were at G2M phase. And this is something we can recapitulate by transferring mitochondria directly. If we obtain mitochondria from astrocytes and treat tumor cells with this sorted mitochondria, isolated mitochondria, and then look at those cells with or without exogenous mitochondria, we see a similar effect, and those with the mitochondria have higher rates of higher frequency of cells at G2M phase compared to those without mitochondria. So this really suggested that the mitochondria itself rescues the phenotype, suggesting that the transfer likely leads to this result. And I think the final set of data I want to show you is the relevance again. To understand potential in vivo relevance, we again sorted out those with or without astrocytic mitochondria, humour cells, and then implanted these to NSG mice to measure their tumorigenic potential. We did a limiting dilution assay in which we implanted mice with reducing numbers of tumor cells, and we observed that mice that that are implanted with tumor cells with acquired mitochondria succumb to disease earlier than mice that received native L1 cells. So red lines again mark the cells with exogenous mitochondria, and those that are shown in black are the cells that are isolated from the same co-culture but doesn't have the astrocytic mitochondria. If we calculate based on the survival curves tumor initiation frequency, we observe that the MHRA-positive tumor cells have higher levels of stem-like cell frequency or tumor cell initiating cell frequency. So collectively, these results suggested that this is a frequent mechanism in the context of glioblastoma. We observed that astrocytes transfer mitochondria through actin bridges in a GAP43 dependent manner, and this acquired mitochondria subsequently leads to metabolic reprogramming and changes the intracellular signaling pathways that presents an increased cellular proliferation. Subsequently, these tumor cells have higher proliferation, self-renewal capacity, and increased tumorigenicity. So this is really suggests to us that mitochondrial transfer is a fundamental proteomogenic pathway, and we can potentially target either the transfer itself or the subsequent maybe downstream effects that we are currently studying in more detail for potential anti-glioblastoma therapies. So with that, I want to thank the co-authors. This was a very collaborative project. We conducted this research in Justin Latte's lab with Dionysius Dennis C. Watson. It involved a very strong collaboration with Furboya Miletici's group from University of Bergen, and those that help with different aspects of projects were highlighted in black. This was supported by Avellasana, Cleveland Clinic, philanthropy part, and we are looking forward to continuing this work at the Sylvester Comprehensive Cancer Center with the new postdocs who just joined the lab. And with that, I would be happy to answer any questions you have. Thank you very much.
Thank you, Daphne. That was a beautiful talk. I have a question right here in the front. Oh.
Hello. Am I audible?
Yes.
Thank you for the talk. I was interested in this particular piece of data that you showed, where you commented that mitochondria transfer is dependent on energy, right?
Mm-hmm.
And then you showed that you've done it at 37 degrees and at 4 degrees. So my counter argument could be that when you bring down the temperature, everything inside the cell slows down, right? So including kinetics of the proteins themselves. So do you think that's a good way of showing that it's an energy dependent process? Alternatively, can you deplete the cell of ATP or put it under some bioenergetic stress and then show that, the mitochondrial rate of transfer goes down? So
no, that's a very valid point. So just to maybe mention that experiment I did, that's only a 2-hour co-culture. And so it's a relatively short-term co-culture. That's the reason being that we didn't expect the cells to traffic all the way. And we tried to measure those that are like already close to the cell surface. Can they go through or not? So that's why we decided that it's energy dependent. I think it's a very valid question. Your question is very valid. And we did try different inhibitors, but we also need to find a way to deplete cellular energetics without really interfering with mitochondrial network, which is actually a bit tricky because those two are very closely linked to one another.
Right. All right. Thank you so much.
Thank you.
Hi, Daphne, this is Sushil.
Hi, Sushil.
Hi. My simple curiosity is, first of all, good talk, really good work. So does this phenomena happen in the normal context also?
Yeah, so there are different studies that are focusing on its regular role, and that's a great question. So it does seem to be a naturally occurring. We did really try to understand whether there is a trigger to this event in the context of tumors, and we cannot find a trigger. It seems like this is sort of a natural interaction, that is a stochastic event that is happening. But we actually never got immortalized astrocytes and put them together. But my gut feeling, and this is not an evidence, says that this is actually a more frequent event than we anticipate, and it does happen in the health setting as well. I think what we think is that tumors are simply taking advantage of this mechanism, and naturally occurring mechanism, to their advantage.
Yeah, and I will extend my question. So is this like the true for only this organelle, or for other organelle also have you tested?
We have not. There are other groups that tested other organelle transfers, and the idea is that the cytoplasm transfer has been known for a very long time, and part of that cytoplasm transfer, obviously, whatever organelles, small organelles are there, could be transferred. But we didn't test in this setting whether there are additional organelles that are getting trafficked through the actin networks that are formed between the astrocytes and tumor cells.
Okay, and I will extend my question like my previous question. So there you said that, okay, these two cells come close in contact and then one cell transfer mitochondria to other cell and that benefits cancer cells. So what is the signaling or trigger, or is there any released chemokines or something like that which triggers this?
Yeah, so we did try to address that, and we don't believe that there is a trigger. It just happens. So what we did, so we tried to address this in multiple ways, but one experiment we did was that we co-cultured the tumor cells with astrocytes and then sorted out the negative fraction and the positive fraction. And the negative fraction, we recultured them with the astrocytes to see that whether there was something initially with the positive cells that made them acquire the mitochondria, whether there was a trigger event. And what we ended up observing that from that negative fraction, when we recultured them with the astrocyte, the same frequency of cells acquired mitochondria. So it does seem like this is just happening, regardless that it is not something that the cells do, but depending on the nature of interaction, that this happens is what we reached to conclusion as. But we are really trying to understand better what mediates this, whether there are inducers of this event. That's something that we are currently extensively studying. And we couldn't, I can tell you, as of now, we couldn't find a mechanism.
Okay, all the best. Thank you so much.
Thank you.
Well, I really enjoy your lecture. We had a lecture of, do you know Jiri Neuzil? No, from Australia. We had a lecture in Monaco 3 days ago, and he was showing the translation of mitochondria into the cell, well, in the raw zero cells, okay? Like if it was a pure selection. From what you show is totally different, is even much, much, much better. Okay. But I am still a little bit confused for the reason, not for the work we've done, but for the interpretation. We have been working in glioma cell. These are the most hypoxic cell in culture that are. And then in this condition, I will have a predict that the amount of ATP that these cells are producing, they will never need, I won't say mitochondria, they will never need the ATP from mitochondria. This is why I'm a little disturbed.
Yeah, so that's a great point. So glioblastoma is very heterogeneous, meaning that there are hypoxic niches, there are normoxic niches, right? Perivascular niches and hypoxic niches. What I can tell you is that these all experiments that I've shown you are done all in normoxic conditions, but we did do the experiments in hypoxic conditions as well. And under hypoxic conditions, we still see that the transfer occurring. So it is not really dependent on hypoxia and normoxia, but it does seem to be that is really happening under hypoxic conditions as well.
Because in the low hypoxic condition, if you go to 2% oxygen, there is a huge amount of ETH produced, high glycolysis. And then I was wondering whether at this point, you got the transmission, you show nice oxygen response, so it's functional, but in terms of rate of proliferation, do the mitochondria increase the rate of proliferation when you have done the transfer? You see?
Yeah, so but that's the isolation experiments that I showed you. We isolated mitochondria, and in that setting, there are no astrocytes. And when we put the isolated mitochondria directly on the tumor cells, we were able to recapitulate the effect fully, the G2M phase effect. So it is the mitochondria that gives that proliferative phenotype.
Okay. Thank you. Thank you very much.
Thank you.
Question.
Hi, Daphne. This is Yogita, and my question is almost related to Dr. Sushil's question. So I was wondering, because astrocytes are normally considered as the support cell. They nourishes neuron. They clear the toxicity. They help in the survival of neurons. So why they are transferring the mitochondria and enhancing the tumorigenicity? I was just confused about it.
Yeah, I think this is a mechanism that tumors opt out, right? This is happening, as I mentioned at the introduction, astrocytes donate mitochondria to neurons as well, as part of their support mechanism network. But in the setting of malignancy, this just becomes a protumorigenic effect. It's not that, it is not really counter-argument to the role of astrocytes. But what I can tell you is that this is definitely not limited to astrocytes either. We were actually part of another study which got recently published as well in the setting of breast cancer, in which we showed that macrophages in that setting were transferring mitochondria, and that group from Mineral Johnson's group from University of Utah was able to show that there is again an increased proliferation in that setting as well. So this is something that is not widely studied, but it is more common. It is definitely not related to astrocyte glioblastoma interaction. It is happening in other tumor types with other kinds of environmental cells.
Yeah, it might be possible that the GBM cells themselves, they are releasing again the environmental factors which are inducing those surrounding astrocytes to release mitochondria.
That's certainly a possibility, but also one way to think about is that astrocyte, this interaction happens from astrocytes to astrocytes in the normal setting, and glioblastoma are astrocytic cells. They come from astrocytic lineage, so it is maybe part of their inheritance, so to speak.
Yeah, thank you so much.
Thank you.
One more question.
Thank you for such an enlightening talk. I have a simple question. Is there anything known in which way the added mitochondria changes the metabolism of these tumor cells? Do they produce more lactate or less lactate, or how do they change their metabolism?
Yeah, we did actually mass spec analysis to address that point, and we were able to see that a lot of prin and pyrimidine related metabolites getting upregulated. We didn't see potent lactate per se, but we saw alpha ketoglutarate getting upregulated as well. So we are currently trying to sort out that subsequent metabolic downstream events and how they are linked to the altered cell phenotypes.
Thank you. We better stop there. Very stimulating seminar, obviously. So let's thank the speaker one more time.
Thank you very much.
Okay, so for the next speaker, we have Sarah Marie Fent from Belgium, from University of Leuven in Belgium, in the Center for Cancer Biology. She's well known for her work in particularly cancer metastasis, and she's won numerous prizes, including the ERC. She recently became a member of EMBO. She won a Bug Prize, an EMBO gold medal, and prior to all that, an ERC Consolidator grant. She's published over 100 papers. She is a hero of mine, actually. I've never met her, but I've always admired her papers. So it's great to see you virtually, and I'm looking forward to your lecture. Title is coming, I guess. Thank you for being here, Sarah.
So thank you very much for inviting me. Sorry that I cannot be there in person. And I also would like to apologize that I will now turn off the video because I'm in a hotel room and the internet connection is not super stable. So I rather prefer that you hear me speaking and see my slides than seeing my video. Can you see my slides?
Yes, we can. Go ahead.
Okay, perfect. Then I will go ahead. So thanks again for inviting me. And today I will talk about metabolic rewiring as a driver of metastasis formation. So as you all know, metastasis formation is the leading cause of death in cancer patients. But you may now wonder, why do we think that metabolic rewiring is so important for the metastatic process? And there are actually two main reasons I would like to share with you. So the first one is actually that cancer cells need to change their phenotype when undergoing metastasis formation. Because when you look at the primary tumor and an established tumor, then you will notice that most cancer cells within these two tumor entities are in a kind of proliferative mode. But proliferation is actually less important once cancer cells are leaving the primary tumor. They need to survive in the circulation, seed and colonize in a distant organ, and only then they slowly get back into this kind of proliferative phenotype. So what this actually tells you is that only cancer cells that can undergo these phenotypic shifts are the cancer cells that are proficient in undergoing metastasis formation and grow in distant organs. Moreover, we cannot necessarily assume that the same nutrients are available to the primary tumor than to the growing metastasis, because they're simply growing in different organs, and these organ microenvironments may provide different nutrients to these cancer cells. And since metabolism is now the biological process that connects the nutrient microenvironment with the cellular phenotype, we actually believe it is very important to understand the metabolic rewiring that occurs during metastasis formation. Because if we can target this metabolic rewiring, we can stall cancer cells in a certain phenotype and therefore prevent metastasis formation. So, but to understand basically whether this is indeed the case, whether this metabolic rewiring is indeed important, we first need to actually ask, is it really sufficient to change metabolism and we then initiate metastasis formation? And this is a question Matteo Rossi and Patricia Alteo Manzano from my lab actually decided to ask. They decided to ask, is metabolic rewiring a driver of metastasis formation? And they basically argued, if metabolic rewiring is a driver of metastasis formation, we actually should find intratumor metabolic heterogeneity. Because we know that not each cell of the primary tumor is actually having the same metastasis initiating capacity. So if metabolic rewiring in any way is important to initiate metastasis formation, we should see a heterogeneity in the primary tumor that is linked to a metastatic phenotype. So what they therefore did is they actually analyzed the patients with breast cancer, and they looked in over 100 of these patients that had triple negative breast cancer, and they analyzed the primary tumors for metabolic intratumor heterogeneity. And what they actually found was that there is heterogeneity in some metabolic enzymes. And one of the most pronounced one was in the enzyme called PHGDH. So this enzyme is the first enzyme of the serine biosynthesis pathway. And what was so intriguing was that only PHGDH showed heterogeneity, but the other enzymes of the serine biosynthesis pathway, such as PSET and PSPH, did not show heterogeneity in expression, but rather a homogeneous expression. So therefore, we focused on the question, is there a role for PHGDH heterogeneity in metastasis formation? So to address this question, what we did is we silenced PHGDH to get a model of PHGDH low cancer cells. We used control cancer cells and we injected them to mice in a mixture. And then we performed intravital imaging. And intravital imaging is a technology that allows us to monitor the movement of the cancer cells at the tumor extracellular matrix border. And the idea is that metastasizing cancer cells are more migratory so that they can leave easier the primary tumor. And this is what we looked into in the next video I show you. And you basically see in green the PHGDH silence cancer cells, in purple, the control cancer cells. And I hope you can appreciate from this video that the green cancer cells are moving much faster than the purple cancer cells. And when you quantify this, it becomes actually very evident that loss of PHGDH increases the fraction of migratory cells and also their migratory distance. So meaning these cancer cells have all signs of cancer cells that should be able to leave the primary tumor. In line with that, we see when we go back to the patients, that patients, those primary tumors are heterogeneous or low in PHGDH expression, have more metastatic events. And this unfortunately also translates in a decreased metastasis-free survival time in these patients. So that was very interesting, but we obviously also wanted to know the underlying mechanism. So what is the mechanism driving that the metastasis initiation up in PHGDH loss? And for this, we decided to look into the phenotype of the cancer cells. And so what we basically did is we used again patient data, and where we had from 14 patients single cell RNA sequencing data of their primary tumors, and we looked what kind of phenotype do PHGDH low cancer cells have. And what we found was that they had a phenotype of an induction of an epithelial to mesenchymal transition, and also an integrin activation, a matrix degradation phenotype, an NMP activity phenotype. So all phenotypes that are pro-metastatic. So then we went back to the cancer cells, we deleted PHGDH, and we asked, do we see the induction of the same pathways? And indeed, this is what we see. We see the same pathways we had observed in the patients now coming when we look at PHGDH silence cancer cells. And what we then in the consequence did is we asked, well, is there maybe a common upstream regulator of these pathways, which could actually link the loss of PHGDH to the activation of this pro-metastatic gene expression program? And when we predicted upstream regulators that can basically control all these pathways, what we found was that one of these upstream regulators is integrin alpha V beta 3. And we were actually quite excited about this because integrin alpha V beta 3 is a pro-metastatic integrin. So then we actually looked, is it indeed the case? So do we actually, can we actually block the integrin alpha V beta 3 and decrease the pro-metastatic capacity of the cancer cells? So what we did is we used a blocking antibody against the integrin alpha V beta 3, and we treated cancer cells that were in an invasive situation in vitro. So they were plated into matricel. They can invade into this matricel, what you see here in the upper control. And when you do this in control cancer cells, you actually do not see any impact of this integrin alpha V beta 3 blocking antibody. So the invasiveness of these cancer cells is the same. But if you actually then delete PHGDH, you first of all actually see that silencing PHGDH increases this invasiveness into matricel, so they're basically more pro-metastatic, these cancer cells. But if you now use the blocking antibody for the integrin alpha V beta 3, you see it decreases the invasive capacity of these cancer cells back to the level of the control. So this actually suggests that the whole pro-metastatic phenotype of loss of PHGDH is actually mediated by integrin alpha V beta 3. But how is actually integrin alpha V beta 3 connected to the loss of PHGDH? So what is the metabolic connection we are looking at? So when you look into this, you actually will find that the integrin alpha V beta 3 can be regulated by a post-translational modification called sialylation. And obviously the precursors for the sialylation are coming from metabolism. So we therefore looked, is it indeed the case that upon loss of PHGDH, you have actually more sialylation at the integrin alpha V beta 3? And indeed, when we pulled down sialylated proteins and we looked for the integrin, we actually do see that in control conditions, there's hardly any CR-related integrin, but when we silence PHGDH, you see this increase in the CR-related integrin, alpha V beta 3. So that was quite exciting, but we also were wondering, is this now the real link? So can we actually inhibit CR-relation and therefore actually inhibit the integrin function and consequently this pro-metastatic phenotype? So what we therefore did is we decided to focus on the last enzyme of the pathway that is providing this precursor for CR-relation, and this enzyme is called CMAS. So we basically silenced CMAS and asked, does this now prevent the pro-metastatic phenotype of PHGDH silenced cancer cells? When we first look into the in vitro situation, we actually do see that in control conditions, we do have some basal invasiveness, loss of PHGDH increases this. Loss of CMAS on its own does not impact the invasive capacity of these cancer cells, but when you combine both, you actually see the induction of invasive capacity based on the loss of PHGDH is actually abrogated once we silence CMAS. And this is not only true in this kind of in vitro situation, but this actually also happens when we look in vivo, because when we look at the number of early metastatic lesions in this mice, we actually can see that up in loss of PHGDH, this increases. CMAS on its own has no impact, but when we combine CMAS silencing and PHGDH silencing, we reduce back the metastasis initiating capacity in vivo in the mice back to baseline level. So what this actually suggests is that the loss of PHGDH is really a driver of metastasis formation, and that this actually happens because the loss of PHGDH induces a CR-relation, so a post-translational modification at integrin alpha V beta 3, and this integrin is upstream of this pro-metastatic gene expression signature. So that was very nice, but we also started wondering what is actually happening when cancer cells reach their final destination. So when they actually reach a distant organ and they now need to grow in this distant organ, but they are facing a very different environment because they're facing very different nutrients that are available there. And this is actually an important question because when you look into the literature, you will find we know a lot about what nutrients are available in the plasma, but we hardly know actually which nutrients are available in organs. And so Patricia Altio-Monzano actually tried to address this question by measuring which nutrients are available in interstitial fluid. And interstitial fluid is the fluid space between cells and blood vessels. And it's the actual nutrient source cancer cells see once they enter into a distant organ. And so Patricia was not only interested to measure the nutrient composition of healthy organs, focusing on the lung environment, which is a frequent metastatic site in many cancers, including breast cancer, but she was also interested what actually happens if the mouse was exposed to a pro-metastatic condition. And for the pro-metastatic condition, we decided actually to look at the presence of a primary breast tumor, shedding secreted factors, which are known to induce a pre-metastatic niche formation in distant organs, and this is actually promoting metastasis formation. And we decided to focus on high-fat diet feeding, which is promoting metastasis formation in many cancers, including breast cancer. So when we then analyze the interstitial fluid of these lungs that are exposed to this pro-metastatic conditions and the control lungs, we first of all find that the greatest increase in nutrients we see in lipids, and within the lipid species, we got really excited about one fatty acid, and that was palmitate. Because when we looked into the lungs of mice that had received tumor-secreted factors, we actually saw that palmitate concentrations in interstitial fluid greatly increased, and the same actually happened when we were giving the mouse a high-fat diet feeding. So that was very exciting. But you may now argue, well, this is just an increase in a fatty acid in an organ environment. So is this really important? And so we argued maybe we can look into the importance by actually looking are metastases enriched in palmitate compared to the surrounding tissue. And so what we did is we used a new technology called mass spectrometry imaging, which allows us to make a spatial map of metabolite concentrations. So what is happening there is that we can make a section of a tissue or a tumor, we mount it on a glass slide, and then a laser is moving over the tissue. And the laser is basically ionizing the metabolites, and they go in real time to a mass spectrometer to be analyzed, which basically means that we can get these nice images of metabolism, and the brighter the color, the more of a metabolite concentration was actually present. So now we actually looked again into lungs containing metastases, and we ask, are the metastases enriched in palmitate? And when we do this, we indeed see that this is the case. Because what you can see here on the left-hand side is a typical H&E staining, and then we have circled the metastases with this red lines. When you look at the right-hand side, you see actually the mass spectrometry imaging data. And when you compare the location of the very bright spots with the location of the metastasis, you actually see that the metastases are lighting up in palmitate-containing lipids. So basically, indeed, it is the case, the metastases are enriched in palmitate-containing lipids compared to their surrounding. But you may now argue, well, this is maybe just simply the case because we are looking at breast cancer. And breast cancer is coming from an adipocyte-rich tissue, so from a lipid-rich tissue. So is this now really specific to the lung metastasis? So for this, we decided to compare lung metastasis with the primary tumors. And when we do this, we see that the lung metastases are still increased in palmitate concentrations compared to the corresponding primary tumor. And this is really selective against palmitate because what we can see that other fatty acids, such as stearate, are either not changed, or some of them, like oleate or linolate, seem to even be decreased in the lung metastases. So from this, we really concluded that there is something particular about lung metastasis and palmitate enrichment. We then decided to look, can we actually change the phenotype of the lung metastasis or the cancer cells when giving extra palmitate? And for this, we went into the in vitro system and we looked at tumor spheroids. And we gave these tumor spheroids extra palmitate. And when we do this, we actually see that the tumor spheroids are growing better in the presence of extra palmitate. So we see almost a doubling of the tumor spheroid size. But this was again specific for palmitate because when we gave oleate, which is another fatty acid, we just did not see the same increase in tumor spheroid growth. So that was actually very interesting, but we wanted to also know what happens to the palmitate. So how is it actually processed in the cells so that these metastasizing cancer cells can grow better in the lung environment? So what we therefore did is we performed RNA sequencing comparing the tumor spheroids in the control condition and the condition with extra palmitate, and we looked for palmitate processing enzymes. And when we did this, we actually see that the greatest change in gene expression we observed in CPT1A. And this was not only true in this in vitro situation, but when we also looked in vivo, we actually saw that metastasis compared to primary tumors of mice had a higher CPT1A expression. The same was true for breast cancer patients. So metastasis had higher CPT1A expression than the corresponding primary breast tumors. And when we look for prognostic value of CPT1A expression, we unfortunately saw that high CPT1A expression correlated with poor overall survival in patients. So really highlighting that CPT1A seems to be important. So what is CPT1A doing? So CPT1A is an enzyme that facilitates the transport of palmitate into the mitochondria, where it is then converted or can be converted to acetyl-CoA. So we therefore were wondering, is it now indeed the case that we can get rid of this whole growth promoting effect of palmitate on the tumor spheroids when we target CPT1A? So we therefore either silenced or deleted CPT1A, and we looked at tumor spheroid growth. And when we did this, we indeed could see that giving extra palmitate, so the black bar actually increases tumor spheroid growth. But when we then either silence or delete CPT1A, we reduce tumor spheroid growth to the level of the control. Moreover, when we have no extra palmitate in the media, CPT1A deletion has no impact on its own. So that was very interesting because we could connect actually this palmitate promoting growth effect to CPT1A. But is this also now acetyl-CoA dependent? So to address this question, what we actually did is we gave another source of acetyl-CoA, and this can be acetate because it's CPT1A independent. So acetate is converted to acetyl-CoA without the need of CPT1A, and when you give this in high concentrations, you can actually rescue the phenotype. So this actually allows us to say that palmitate-derived acetyl-CoA is important for the tumor spheroid growth. But we were now again actually wondering, why is acetyl-CoA important? Because when you look into the textbook, you will actually find that acetyl-CoA has many, many functions. The most described one is probably its role in energy production, but it then can also be a post-translational modifier when it's on protein acetylation, and when this acetylation is on histones, it can directly impact actually also epigenetics. So therefore, instead of going one by one through all the options what CPT1A-derived acetyl-CoA could do, we actually decided to again look at the phenotype of these cancer cells. And we therefore deleted CPT1A and asked, based on RNA expression, what is phenotypically changing in these cancer cells. And what we actually saw is that upon loss of CPT1A, we also lost a signature indicative of NF-kappa B signaling. And this was highly exciting because NF-kappa B is a pro-metastatic pathway. We then actually also looked if we get the acetate rescue of the signature, and indeed, this is the case. So we therefore proposed that the growth-promoting effect of palmitate is actually coming because NF-kappa B signaling is activated. But how is now NF-kappa B regulated by palmitate or acetyl-CoA? What we found was that there is actually one component of the NF-kappa B pathway, which is called P65, which can be acetylated. And once it is actually acetylated and in the nucleus, P65 binds stronger to the DNA, and selected targets of the NF-kappa B pathway are better transcribed. So we therefore decided to inhibit CPT1A and asked, do we impact P65 acetylation? And indeed, this is the case. So when we look at nuclear acetylated P65, we do see that when we delete CPT1A, we lose this acetylation or decrease it. Moreover, when we again give acetate, we can actually rescue the P65 acetylation. But this is just a change in an acetylation mark. So therefore, we were next wondering, is it now indeed sufficient to increase NF-kappa B signaling and we promote actually tumor spheroid growth? So we decided to test this by giving an NF-kappa B activator called TNF-alpha in the absence of palmitate. So we then don't produce extra acetyl-CoA, and we do actually see that TNF-alpha treatment, so activation of NF-kappa B, is sufficient to increase tumor spheroid growth to a similar level than palmitate. We then also wanted to do the opposite and show that blocking NF-kappa B really blocks the growth promoting effect of palmitate. So we therefore switched to an NF-kappa B inhibitor, now in the presence of palmitate, and when we give this NF-kappa B inhibitor, we actually do see that we reduce tumor spheroid growth to the level without extra palmitate. And in this condition, acetate is actually not any longer rescuing, which basically means that the whole growth promoting effect of palmitate and acetyl-CoA is converging into the NF-kappa B pathway. So that was very nice, but we got a bit puzzled about this because a lot of fatty acids can actually be oxidized to acetyl-CoA. Also, when you basically increase the general acetyl-CoA pool, you actually should increase a lot of acetylation events, and actually not only the P65 acetylation. So where is the specificity of the system coming from? And so we actually hypothesized that the specificity of the system is coming from the acetyl transferase, connecting palmitate-derived acetyl-CoA to P65 as a substrate. So therefore, we looked for acetyl transferases that would increase in expression in the presence of palmitate. And when we looked for that, we actually found there was only one acetyl transferase in the name of CAP2A, which actually increased in expression once we gave extra palmitate. So we hypothesized that CAP2A is the missing link in this mechanism. To test whether this is indeed the case, we deleted CAP2A, and when we then looked at P65 acetylation, we saw it decreases the acetylation of P65, similar to a CPT1A knocked out. Moreover, we could also show that this was really palmitate dependent because we have also access to a CAP2A inhibitor. And when you give this CAP2A inhibitor in control conditions, literally nothing is happening to tumor spheroid growth. But when you just give extra palmitate, same concentrations of the inhibitor, same cancer cells, you first of all see that you have this nice increase in tumor spheroid growth. But now already the lowest concentration of the inhibitor dramatically decreases tumor spheroid growth, which actually tells you that CAP2A is only important in the presence of extra palmitate in this system. So therefore, we next actually ask, can we target CPT1A and CAP2A to inhibit metastasis formation? So therefore, we actually injected cancer cells to mice, and when you do this in control condition, you see many metastases, but when you silence CAP2A, we basically have no metastasis. And a very similar picture arises when you actually delete CPT1A. Many metastases in the control condition, hardly any metastases in the mice that received CPT1A silenced cancer cells. So that was all nice. But this is actually not the real world situation, because now we have actually given cancer to young and healthy mice. And this is not what is actually the case in a breast cancer patient, because breast cancer is connected actually, for example, to dietary conditions such as obesity or being overweight, and this is promoting breast cancer and its metastasis. So we were thinking maybe we can make our mouse experiment actually a bit more relevant for the patient situation. So we therefore put mice for 4 months on a high-fat diet, and we first asked, does this promote metastasis formation as expected from the patient data? And indeed it does. So if you put mice for 4 months on a high-fat diet, you actually do see that the lungs of these mice are now full of metastasis compared to the mice that were on controlled diet. The important question now is, can we actually still reduce metastasis formation by targeting CPT1A. And when we did this, we were very happy because we saw that targeting CPT1A was still sufficient to inhibit metastasis formation, even in high-fat diet mice, where the high-fat diet is drastically promoting metastasis formation. To go even more clinically relevant, we also decided to analyze samples from breast cancer patients. And for this, we made actually use of a rapid autopsy program called UpTiter, which is available at KU Leuven. And in this program, we basically have access to metastases from the same patients, but the metastases are growing in different organs. And so we decided to compare metastasis from palmitate high organs with metastasis from palmitate low organs. As palmitate high organs, we focused on the lung environment, where I have shown you that it's enriched in palmitate, the liver, which is known to have a lot of palmitate, and then we also focused for palmitate low organs on the brain, where my lab and the lab of Matt van der Heijden actually showed that brain interstitial fluid and brain CSF is really lipid or fatty acid deprived. And we focused on the lymph node, where John Morrison's lab has actually shown it's oleate enriched and not palmitate enriched. So the first thing what we then looked is we looked at CAT2A and CPT1A expression. And when you do this, you do see that you have high CAT2A and high CPT1A expression in metastases growing in the lung and in the liver of the same patients. But when you look now at lymph node metastasis or brain metastasis in the same patients, you actually see that CAT2A expression and CPT1A expression are dropping. Moreover, when you look at the NF-kappa B signature that we had identified, we actually saw that lung and liver metastasis had a much higher NF-kappa B signature compared to the brain metastasis, again splitting the metastasis in palmitate-rich organ versus palmitate-low organ. So based on this, we therefore concluded that there are metastasis-promoting conditions, such as the presence of a primary tumor or high-fat diet feeding, which actually increases palmitate availability in the lung environment, which is a frequent metastatic organ in breast cancer and many other cancers, and that the cancer cells that arrive in the lung environment can thrive on this palmitate because they oxidize it to have acetyl-CoA to basically acetylate P65, which leads to the induction of a pro-metastatic NF-kappa B signaling. In the consequence, if you now actually target CPT1A or CAT2A, you can decrease metastasis formation. So with this, I would actually like to wrap up, and I would like to thank the people who did the work. So today I shared the work from Patricia Alteo Manzano, a very talented postdoc who is currently on the job market with you. And the first part of the talk was the collaboration between Matteo Rossi, a former postdoc, and Patricia. We had key collaborators such as Ilaria Malanci from the Cancer Research UK, Jaco van Renen from the NKI, and Christine de Smet, who is actually leading the rapid autopsy program at KU Leuven. We obviously had funding, and I would like to thank you for your attention.
Very nice, Sarah, thank you. Maybe I'll ask the first question. I'm curious, I feel like Salvador Benita Ansnar had a similar kind of story with palmitate, and withdrawing palmitate from the high-fat diet was able to reverse some of those effects. Have you seen the same? Because you mentioned that other fatty acids can be converted into acetyl-CoA, but the specificity for palmitate in your system is really interesting. Do you see if you remove it from the high-fat diet, can you still see the same effect?
Yeah, so we have not looked into a low palmitate diet, and Salvador has focused his research on the metastasis initiating capacity that is actually changing in a palmitate rich environment. And so we think we are actually very complementary to the findings he basically has, but we have not used the lipid low diet or a palmitate enriched or oleate enriched diet. We focused on general high fat diet.
Okay, can I ask one more? Maybe it's philosophical, but when thinking about metastasis, I always wonder if it's sort of survival of the fittest, and what you're detecting at the distant sites, the colonies that grow, are those that have the adaptations that you talked about. But are they 1 in 100, 1 in 1,000, and a bunch of other cells have adapted differently and haven't been able to survive? Is what you're showing maybe the tip of the iceberg of lots of different modifications that could happen, or is this palmitate and the integrin, is that a specific thing that is required, you think, for all metastases in this type of cancer?
Well, I mean, let's maybe focus first on the PHGDH and the integrin. There we do know that this is specific for triple negative breast cancers because they start with actually an amplification of PHGDH, so they can modulate the expression of the enzyme, and many of the ER positive cancers, they do have actually a loss in the region where PHGDH is actually present. So they're basically auxotroph for serine. So they don't have the ability to modulate the integrin with the PHGDH pathway. So there we think this is really, in terms of the metastasis initiating capacity, more specific to triple negative breast cancers. And we have also confirmed part of this data in melanoma because they also show PHGDH amplification. For the second part, when we now go into a distant organ and we see this metastasis promoting effect of palmitate, we see this actually also in ER positive breast cancers. So this seems to be something more general. We have in vitro tested even other tumor types where this also happens, but we have not tested this for other tumor types, the in vivo situation. So we do think that it's one mechanism that allows cancer cells to better survive in a foreign environment. And that palmitate is one of these mechanisms that is helping there, and therefore you can actually target CPT1A and inhibit metastasis formation.
Great, thank you.
Hi, Sarah.
Hello.
Boast, nice presentation. Sarah, I was wondering if you checked insulinemia and glycemia in your high-fat diet mice, and what could be the implication of higher insulinemia, for example?
Yeah, so we have not checked this because the mouse background is actually bulb-C. So that's actually very interesting because they don't get really obese. They just increase a bit of weight and they're still insulin sensitive. So it's really a direct effect of the palmitate in this mouse background, but it would be interesting to use another mouse background and check, is there maybe a combinatorial effect if the mice also get diabetes and getting insulin resistant?
Hey, Sarah, it's very fascinating, and all things is very understandable from beginning intrigue into CPT1A, right? So I have one just technical protocol question, because you have shown one slides having high fat diet and one is low diet and showed the metastasis. Then you have done the metastasis with the CPT1 knockout, right? So this is how you generate this metastasis in the lung. So both way it is written control and control.
Yeah, so basically what happens is we have the mice that are for 4 months on a control diet. So this is not a fat low diet, it's more actually the standard diet that is fed in our mouse facility. We then use an isonutrient high fat diet, and we put also the mice for 4 months on this high fat diet. And then in both conditions, we then in the end injected cancer cells that either have a wild type CPT1A or are silenced for CPT1A. And I have shown you basically only one of the controls, but what you basically see is that in mice that have a control diet, you reduce metastasis formation as we have seen before. And in the mice that had high fat diet, we reduce it to the same level, meaning we can get rid of the whole growth promoting effect of the diet.
Right. Thank you. No, I understood. Any more questions? Thank you.
Thank you, Professor Sarah, for accepting our invitation. And this is Dr. Vinit, and delivering this wonderful talk.
Thank you very much.
So I guess by now today's session is completed. But we can continue with the post-session evaluation, or can we continue? So, okay, so still we have 20 minutes probably. So we can utilize that to continue, to finish the post-session evaluation. And in the meantime, all the participants, we have the speakers here. So now we can have some informal interaction session. So you can interact, you can talk, and if you have any question, you can ask to the experts. At 5:45, bus will start from here, 6:45, sorry, to the dinner venue. And dinner will be in the Crown Plaza. So most of our expert speakers are already staying there. So we have the dinner there for everyone. Okay. So bus will be outside the venue. So thank you, everyone. So now you can stop the live. And I also want to thank all the online participants, those who have joined us today. I guess now. So now we can off the Zoom session.